Hi, my name is Thomas. I have taught over 100,000 people about blockchain development, and I'm the creator of this course, which makes this course number 17. The other courses are also about Ethereum, blockchain development, but also DevOps and AWS. I'm currently working as CTO for Morpher. I have over 20 years of experience as web developer, from hands-on to high-level management. With my background, many people think that I'm super positive about blockchain technologies, and I'm going to blast you with overhyped topics in the course. But I'm not running the hype train. That might surprise you now, since you're here to eagerly learn Solidity and Ethereum blockchain development. After using Solidity and all kinds of other tech in the sector extensively, I know that blockchain technologies are very powerful, but they come with a lot of trade-offs. They won't bank the unbanked overnight, and we will most likely not run around with 3D goggles, and the masses will not consume a blockchain-enabled metaverse in the very near future. What I'm trying to teach you is a set of tools that have proven itself in the real world. I want to give you the skills to succeed in this sector, whether you are just looking to expand your knowledge or completely switch from traditional web development to blockchain development. I will give you an unopinionated snapshot of what is possible with the technologies today, and will make sure you fundamentally understand what this is all about. In this course, we are going through a series of projects from very simple to quite complex, which will showcase a variety of use cases for blockchain technologies. It's a holistic approach to understanding decentralized applications, the tooling, and smart contracts. Well, that's enough from my side. Let's dive right into it, and I'll see you in the next lecture. One question is, are you the right target audience for this course? What level of knowledge am I assuming in this course? In other words, is this course for you? Up front, I can tell you, Solidity is not a language I would suggest to an absolute beginner who never wrote a single line of code. The complexity isn't so much in Solidity. It's how you interact with smart contracts. You need a fair bit of web development knowledge for that. To outline the ideal student for this course, it's maybe simply a Web 2 developer. If you have dabbled around in JavaScript before, or you are a pro who developed websites since Netscape Navigator, you will feel right at home in this course. But also if you come from an enterprise side, Java, C#, .NET, you will find this course the perfect companion to learn Web3 development. The showcase projects we are developing can be uploaded to your GitHub, and the token standards we discuss can be mentioned in your CV. So if you're looking to expand your professional reach, or you're looking for a new job, this is something that will bring you a big step forward. Well, with that being said, who is the course not for? It is not for two kinds of people. First, if you're looking for an introductory course, maybe about JavaScript and programming. When I try to explain every line of code, if you have never written anything, I do not recommend taking this particular course. Second, if you're easy to give up. And that has not so much to do with my course materials, but you have to understand that blockchain development and Ethereum is in constant change. Things break all the time. There isn't a cohesive corporate management leading the way. It's a decentralized, governed set of tools and best practices. So if you like a challenge here and there, you're the perfect student, and you will probably love this course. Before we start, let me quickly tell you how the course is structured so you get the most out of it. There are 7 quick points which I think are necessary to talk about before starting the course so you get a pleasant and efficient learning experience. One question I often get Is the course still valid when ETH 2.0 comes out? The answer is simply a yes. While some aspects of the Ethereum blockchain might change, one thing does not change. That is solidity and smart contracts. By doing this course, you will have all knowledge in place to be a successful Ethereum 2.0 developer. The course is now recorded for the 6th time. I tried to remake a lot of videos over time, but some older ones are still relevant, so I kept them in the course. Since videos are hard to update, we also provide written and updated documentation to most, if not all, practical lectures on Ethereum-blockchain-developer.com. You can get the most out of this course by watching the videos, then doing the hands-on part yourself. If you truly want to know if you understand the topic, apply the Feynman technique. Feynman was a famous and Nobel Prize-winning physicist who had a 4-step plan to truly learn about anything. First, learn it yourself, then try to explain it to others. If you get stuck somewhere, learn it better until finally you can explain it with analogies and simplifications. If you want to put your knowledge to test, head over to the course Q&A on Udemy or to our dedicated Discord or forums and try to answer questions other peers might have. Basically, teach others. If you need help, on the other hand, we have dedicated teaching assistants to help out. Well, I have to admit, in blockchain development, you have to have a thicker skin and a little bit more resilience than in other programming languages. If you really get stuck after consulting Google and Stack Overflow and the other services, feel free to ask questions. One last tip: if my videos are too long, too much babbling, feel free to use the video controls to watch them in 1.5 or even 2x the speed. Also, if they are too fast, slow them down. Also, subscribe to our educational updates, as I'm posting free mini courses to specific topics, for example, a full walkthrough of proxy contracts or NFT secondary sales on our course website. With that being said, I hope you will enjoy the course. Feel free to add me on LinkedIn, and I'll see you in the next lecture. I just wanted to have a quick note on those reviews that Udemy asks for. It's pretty early in the course that they are starting to ask for reviews. There's going to be a little pop-up that asks you to rate this course. If you haven't watched enough yet, please skip it. Of course, my personal goal for this course is to give you a beyond 5-star experience. So we not only have the videos, we also have the labs. We are also active in the course Q&A. I'm trying to keep stuff updated. I'm trying to report on stuff as it comes out, and I'm trying to offer you additional mini courses, which doesn't fit the actual beginner's scope of this course on the platform. But anyway, so my goal is to give you a 5-star experience. And obviously, I would be very happy if you rate this course 5 stars. Where are these stars actually used? The course rating is used for Udemy for the course landing page to get social proof for other students who did not purchase the course yet. So if they are looking on the landing page and they are about to purchase the course, they are obviously going to the review section and they are checking what other people said about this course. So I would be very happy if you leave a comment as well. One thing, this course rating widget, this 5-star widget, is a little bit finicky. A lot of people actually want to give 5 stars, but they end up giving 4.5 or even 4 stars because at the last moment where you click on it, it just skips back to like 4.5 stars. And I don't know why. Seems to be a technical issue. I didn't program that. It's on Udemy side and I have no influence over that. The other thing is, if you have any questions, either technical questions or about the course content, I'm not getting a notification about those reviews. I'm checking them from time to time, but I'm not really reading every kind of comment that comes through. We have over 100,000 students in this course. So if you have a technical question or if you have any problem throughout this course, the review section is the wrong one. It's the course Q&A section where you want to ask questions, where we are getting a notification and where we are checking every few days or every day actually now about people having problems with the course content. So if you have any troubles, course Q&A, if you want to leave a review for somebody else, and I would be very happy, especially if it's a 5-star review, then the reviews. And if you are, well, not sure what you should do, then you just skip it. There's always a skip button somewhere. All right, now off to the next lecture. In this first section, we are going to introduce Remix, which is, in my opinion, the easiest way to get started with Ethereum blockchain development. It's a cloud-based integrated development environment tailored to Solidity programming. It has a plugin-based architecture, and by default, there are 2 plugins already activated, which are essential to blockchain developers like us: the compiler and a way to simulate an execution environment to test the smart contracts. There are also several other plugins like a step-by-step debugger and many more. Many of them you get to know throughout this course. In this section, you are writing your first smart contract. You are learning about the compilation and the execution environment. Remix is very powerful, but in my opinion, no comparison to a real dev environment like a local VS Code with Truffle, Hardhead, or Foundry, which we're going to do later. But there is no easier way to get started with blockchain development. All you need to do is basically open up the browser and get started. And that's exactly what we are going to do now. So start your browser and let's get your hands dirty. Now in this section, I really want to talk about the Solidity basics. And to get even started with the Solidity basics, we have to have some sort of development environment. And I think there is nothing easier than using Remix if you're just starting out. It's an online IDE, and you can reach it on the remix.ethereum.org. And yeah, it's really meant for Solidity development. It's slightly different than what you would have in a normal IDE. Because it's tailored for Solidity compilation, deployment, and local testing of smart contracts. It features a JavaScript console on the bottom over here. And this is really the difference to a normal VS Code environment, which we're also going to use later. But this one makes it super easy to get started with Solidity development. So I recommend to use this. One thing that I tell you have to be careful with is the URL, and especially if you are starting out with the development, and then you go to remix.ethereum.org without HTTPS, and at some point during your development you switch over to HTTPS remix.ethereum.org, so you change the protocol from HTTP to HTTPS, then suddenly all of your content will be gone, because the content of the IDE is stored in your local store, and that one changes obviously with the URL. So be careful with that. And with that being said, we can head over to the next lecture where we talk about the file management inside Remix. Now that you know what is Remix, let's quickly talk about how it works, that you can add files and what are these files that are already there. So in the previous versions of Remix, there were no workspaces, and this is kind of a new thing. I mean, not so new anymore. It's already in there for a year around. But before there were no workspaces. So what are workspaces? Workspaces are like folders. Since Remix is not really opening any folder on your hard drive, I mean, you can technically, I think there's a daemon for that, but internally, it's kind of meant to work around these projects, and they call these workspaces. So when you just open remix.ethereum.org for the first time, then you have a default workspace, and you can add new workspaces like new folders over here, and then you can give them a name, and you can even choose a template if you want to use one of those Open Zeppelin smart contracts, or just a blank one, or the default template, which is this one. I'm not going to create a new workspace now. I'm just using the default workspace throughout our course because I think I don't need another workspace. If you want to create one, if you want to play around with that, fine. The more important thing is, what do you do inside those workspaces? And that is, you can create new files. And since this is not a normal IDE like a VS Code or so, where you can just like right click, it will open the context menu of your browser unless you click on a file. Then you have to, I think, select the folder where you want to create a file, and then you create a new file in there. And you can name this, for example, my contract.sol for a Solidity file. And what will happen, maybe will happen, maybe not, is that it gets directly compiled. And You see now this is really tailored for Solidity development because there's an integrated compiler, there's an integrated test chain, and it is also already highlighting Solidity code. So if you write something like a contract, my contract, and then you make curly brackets, open and closed, you see it's already highlighting the right syntax and so on and so forth. So everything is kind of tailored around Solidity development, which is the nice thing about it. What happens if the contract is compiled? It lands in an artifacts folder. More on that later, don't worry about it. And in Remix, since a few version, you also have the option to script stuff because the whole thing is JavaScript. So it also injects a JavaScript environment. It's JavaScript in JavaScript. How nice can it be? They also give you sample scripts for deploying smart contracts using Web3.js or Ethers.js. If you don't know what it is, don't worry about it. We are talking about those libraries later. And you can run unit tests, which I never used in Remix, and we are maybe going to talk about it in the course. But normally I do testing of Remix inside VS Code in Truffle, Hardhat, or Foundry. Remix also has a JavaScript console over here on the bottom, so it's interactive. You can do Web3 for the Web3 library, .utils, I don't know, SHA free, and then create an KESA hash of this string that I just entered, and that will be the KESA hash. So if you don't know what it is, also don't worry about it. What is important is, you have the files over here, you have an editor on the right side, there's also the small one over here, everything is there, and there are plugins in Remix. And those plugins, the whole thing is a plugin architecture. I think even the File Explorer is a plugin. But then you have a compiler, which we are talking about next, where you have different Solidity versions and so on. And you have a deploy and run transaction plugin where you can actually test your smart contracts. And you have a ton of more plugins if you want to. You can go through them. Maybe we use the debugger later. And I think that's it, what we are going to use in this course, because we are going to move everything off chain, off Remix. If you go to the settings, then in the settings you have a number of things, but if you like, there's also different themes, so you can change the look of Remix to something to your liking. I stay with the dark theme for now, which is a total contrast to the light theme, which we did in the previous course. In the next lecture, we are going to create a little smart contract. We are going to start it, stop it, and see how we can interact with it from within Remix. Now that you have played around with Remix a little bit, it's time to actually get started writing some Solidity code. That's why you're here, after all. So in this video, we are going to write a simple smart contract. And instead of going into Solidity too much, I want to actually talk about the functions of compilation and running, deploying, and interacting with the smart contract in this lecture, because that is basically the base that you need throughout all of the rest of the lectures. So in the previous lecture, we already created a smart contract in the contracts folder. If you have not, then just click on the little create new file icon over here, and it will create a new file and just name it my contract. And the content of the contract is really not that important right now. What is important is that if you open it, that there's a little exclamation mark. And that means that the contract is getting compiled and there is a warning. Now you should also see a little warning over here next to the Solidity icon. If you do not, then click on it, and that will bring up the Solidity compiler settings, and then make sure that auto-compile is on. So I'm talking about this value over here. That one should be always on. And what it does is it automatically, on change of any of your source files, compiles the source files again. And then it will output any errors or warnings both here and next to the actual contract. So what are those warnings? And I'm going to talk about those in the next lectures as well, a little bit more in depth. The one is this contract needs an license, a license identifier or a license. So that one is done with SPDX license identifier, and I'm going to license this specific smart contract as MIT license, so you can do whatever you want with this particular contract. And it also needs a so-called pragma line that tells our compiler, or that tells our pre-compiler actually what kind of compiler version this smart contract was written for. And I'm going to, I don't know, do this for 0814, which I think is the latest compiler. It's 15 already. Anyway, we are going to use some of the language features from 0814 in this course in general, but for our sample smart contract, this one will be more than enough. Okay, and then we have a contract, and we called it my contract, and then we just put in a variable, and we call this variable, well, actually we put in a string, and then we are making it public, and then we call this our string is hello world. Well, great. You saw that during typing, there's little pop-ups over here, or little errors popping up over there in the compiler. And then at the end, it actually compiles again and it says compilation successful. Perfect. Now here you have a couple of options. If you have auto compile off, you can recompile the smart contract. You can see the compilation details. You can see the bytecode that it's actually compiled to. Normally over here, further down. Somewhere is the bytecode, the actual stuff that gets deployed on the blockchain. You see the ABI, which is an application binary interface. It's an array of all the functions, inputs and outputs that your contract has. You see deployment codes, assembly, and so on and so forth. So all of that is the compilation details. Now you have a compiled smart contract, but you somehow want to interact with it. And there are several options for that. Now, option number one is you could deploy it to mainnet, probably pay around, I don't know, $20 to deploy that smart contract. And then you can interact with it from your wallet like MetaMask. But as we are in Remix, Remix offers you an actual development environment to interact with your smart contracts that cost nothing. And that is all in memory that you can find over here in the deploy and run transactions plugin. And you find the environment, you find several environments and several options to deploy your smart contracts. So the first two are actually JavaScript virtual machines that are running directly in the browser. So you select one, you hit deploy the smart contract, and you see over here there's an instance popping up. And you also see on the right side in the transaction log or in the console over here that there is a new transaction being logged, and then you can also drill into the details, which you're going to look at later on. You can open it and you can also debug and so on. But the point is, you get directly a way to deploy your smart contracts onto a test chain. You have like 20 accounts, I think, with each 100 Ether, more than enough to do stuff on this during development. You have different hard forks, London and Berlin. Those are for adding features to the blockchain, which is not interesting for us right now. Then you have an injected Web3 provider, which would be MetaMask. If you have a MetaMask wallet, then it would inject itself as a Web3 object into the browser, and then you can do that. You don't have to follow here because we didn't go so far to actually work with MetaMask, but install it in the course. I still want to talk about it. You have a Web3 provider. That one would be a specific node that actually runs on a port on your machine or on like in Fura or anywhere where you can directly connect to. And then you have Hardhat providers, which is from Hardhat. You have a Ganache provider, which would be Ganache when you run it, and like the Hardhat node and the Garage node, and Wallet Connect, which allows you to connect to with Wallet Connect to another provider. I haven't used Wallet Connect yet. I've used Ganache and Hardhat node and Web3 provider, Injected Web3, Berlin. We are not going to use it, but London, we are going to use it quite a lot. So for this one, make sure you're going to stick with London. And then you hit, again, the deploy button. Make sure you have the right contract selected here. It's anyway just one contract, but if you have 20, 30, 40, 50, 100 contracts, make sure you have the right one selected over here. You don't need to send any value along. The gas is more than enough. We're talking about this later. Select one of the accounts over here and hit the deploy button. Now you have an instance of your smart contract running here. And this is how you interact with it. You basically, from Remix, just need to press a button. Everything is transaction based. So when you press a button, you see over here on the right side, it says now call because it's a reading operation. It doesn't do anything and it outputs hello world. If you change your hello world to hello world on Earth, then you will see that your instance that you already deployed is not changing. You have to redeploy it and you get a different instance at a different address with the same button but a different output. So this is how you interact, deploy, run your transactions, and so on within Remix. The last thing is to clean up. That is either you press F5, so you reload everything and you wipe the memory of this transaction, this VM, or you are just hitting here the little garbage icon to delete everything. But maybe it's even better to just reload everything and we are back where we started. That was a lot to take in. So in the next lecture, we are going to talk a little bit more about in-depth smart contract scaffolding. All right, now that we have our first smart contract in Remix, I think it's time to actually talk about how smart contracts are working a little bit more under the hood. So you have the theory side as well. Now, in general, what is a smart contract? The term itself was coined by a computer scientist named Nick Szabo already in 1994. So it's not particularly new what smart contracts are. They are a piece of code that is running on the blockchain. And the blockchain itself is like a state machine. So it needs a transaction to change from one state to the other. And it can do some logic operations. So that is basically how that thing works. And the state change happens through mining. And the mining is going to take the transactions that are in a transaction pool and then changing the state on the blockchain. Now, the Ethereum blockchain is a Turing-complete blockchain. So that means in theory, it can solve any computational problem. And it's just a theory because it's very limited by the computational power that it has. You will see it later. It's calculated in the gas amount. So if you need a certain amount of gas, which is getting too much, you cannot in practice solve any computational problem, but in theory you can. So in theory you have all the functions and all the logic there to solve anything that needs to be solved. Now there are a couple of programming languages for Ethereum virtual machines, and the most popular one is Solidity, but there's also Viper, which came from Vitalik, wanting a new language that is more secure and a little bit also more for academic purposes. Then there was LLL, which I think looks a little bit like Python, but there's no development for these languages anymore. And then there was Bamboo, and there were a lot of other languages that basically compile the source code into EVM bytecode, and that is what is run on the blockchain. So the EVM bytecode is actually the kind of code that the Ethereum blockchain nodes are executing. And then there's high-level languages, very much like C, C++, what do we have? Go, and so on. So those languages, you can write them in a specific syntax, and you have specific language features, and then they compile down to the actual bytecode or assembly code for the EVM. And this stays constant, and the language features change. Actually, the EVM also doesn't stay constant because there are hard forks, but more on that later. So how about Solidity? I mean, that's by far the most popular language, and this course is also building upon it. We are doing a lot in Solidity, and we are trying to touch on every kind of topic that Solidity has to offer in the projects that we're doing. It is very often compared to JavaScript, and actually it's compared to ECMAScript. And it's like every high language code is then compiled to bytecode, and that is very important to understand. And in the Ethereum network, every node then executes the same code. So you're going to write your Solidity smart contracts in Solidity. It's going to be compiled to EVM bytecode. Then you send the transaction with that bytecode to the blockchain. And then every node in the network is going to execute the same code because every node has a copy of the whole chain. It's very important to understand that. It is not like you're going to send your code to the AWS data center and then there sits a machine that is going to execute the code. It is you send the code to the network and then the network itself takes care of distributing your transactions across all the nodes that are running in the network, and then those are executing the same code again. Now, as I said before, there are other languages. It was Serpent that is similar to Python. LLL is like Lisp. There was Mutant, and now there's Viper, and in between they also had Bamboo. But I still recommend staying in Solidity because it's really by far the most famous language that is out there for smart contract development. Now, how does a Solidity smart contract actually look like? And it's very tiny here, but I want to touch on a couple of features that the language has that are probably very familiar to some of you who are coming from a language like Java or like C# or like C++. So there is a class-like structure, and those classes are, the keyword for the classes are contract. And they contain functions, and the functions can contain control structures like if-else. There's loops, for and while loops. There's different data types. It's a statically typed language, so you have to give it for every variable that you define. You have to tell it which kind of data type is that. There is unsigned integers, Booleans, arrays, structs. There's mappings, which a little bit look like hash maps. There is a special data type called address that is, I think, not available in any other language that I've ever seen. And be careful, there are no floats. So if you want to have some sort of decimal points, you have to make a large enough integer to take care of the decimal places. And more on that also later when we do our first coin. There's inheritance, so you can have contracts extending other contracts. There is special structures like modifiers that, a little bit like go-to statements in BASIC. And then there is also import, so you can fine-grainedly structure your smart contract files and then just import whatever you need. You will also see that later on. Now, as Solidity layout more at the beginning, what you saw now is that one, what we did in the previous lectures with an SPDX license identifier. That one identifies the license of that file. It doesn't identify the license of the project that is running under. So make no mistake, it's not that because the NFT ERC 721 token file is licensed as MIT that the NFT is licensed as MIT. It's about the source code. So this one depicts the license of the source code, as far as I know. Then there is a pragma line. The pragma line is a pre-compiler line that tells the pre-compiler to select the right Solidity compiler for that file, or at least it tells it like this file is written for this compiler version. And that is in a semware style semantic versioning. So in this case, it is clearly 0814, so it's locked into a specific version. And if there was a caret in the front, then it would mean 0814 or larger, but not more than 09, excluding 09. Or you can also use the greater sign, smaller sign, greater equal sign, and so on. So you can use those to tell the compiler or the environment that you're in, the pre-compiler, what kind of compiler version is that file written for. And the reason is that you want to lock in specific compiler version because sometimes the compilers change and they have a different meaning for the same language features. Now let me give you an example. Unsigned integers and integers in previous versions were rolling over, and I will show you this later. So if you hit 0 and then you decrement an unsigned integer, you suddenly hit max int. And this was changed in, I think, Solidity 086 or 3 or something. So be careful that you lock in a specific compiler version that you're currently working on, and then make sure if you're upgrading to a new compiler version that all of your files are still compatible. This is where unit tests come in, which we're also writing. Now, then comes a contract. This is what I told you before with the classes. The contract is depicted with a contract keyword and then comes in capword style. Well, you don't have to, but the official naming convention of Solidity, which you can also find in the Solidity docs, is here's a capword style, meaning the first letter is capitalized and then every other word is also capitalized. So the M is capitalized, and then contract, the Z is capitalized. And then if there would be other words, then you would also capitalize them, at least the first letter. Then there is curly brackets, and then inside the curly brackets this one is a storage variable, which we are talking about later on. It's basically the variable that stays across several transactions. So you can store some value in there. There's going to be events and modifiers and functions and constructors, and all of the other things that we want to do with Solidity are in there. Now for the deployment, we sent off a transaction, and when you had a look, when you opened the transaction field in Remix, then you probably saw that there was a data field or a value field that was populated. It's called input field in Remix, but it's actually for the transaction, it's a data field. And this data field has the compiled bytecode. And that one, if it's not sent to any specific address, if the to field is empty, then the EVM will know, wait, this is bytecode, I have to deploy it to the blockchain, and then it will create a new address, which is a deterministic operation, will create a new address for the smart contract, and then it will deploy the smart contract bytecode that is sent in the data field in the blocks, in the blockchain. That's how it is. And this is what we are going to do now in a couple of next lectures over and over again, so you understand exactly how this works. But this is the basic. So this is the very basic. If you understand that, then you understand already 80% of how smart contracts are deployed, how the interaction works, and so on. Now the key takeaways are the smart contracts are running on the blockchain and they are deployed as EVM bytecode. The blockchain itself, or the EVM, is a Turing complete system. The structure for a smart contract, if you had any prior coding experience, should look fairly familiar. Even if you come from only JavaScript or only PHP, it should still look very familiar. So there shouldn't be much of a new thing other than the addresses and the special edge cases like no floating points. Deployment is done with transactions, and this is going to change the state of what is basically a state machine, the blockchain. All right, I will see you in the next lecture. All right, now you have deployed your first smart contract. You know what is in the compile tab. You have the right compiler, which is the same as in the Pragma line. You have autocompile on, and we ran our transaction in the deploy and run transaction tab on the JavaScript VM. Now, all of this is fine, but we didn't change anything. We didn't do anything with our smart contract. We just deployed a smart contract. And in this video, I want to go and actually change that string to something we can input as a user after the smart contract is deployed, of course. So I'm going to revert this to hello world. And we are going to add an additional function over here. Let me make this a little bit bigger. Okay. Function. Every function starts with the keyword function. And then we say update our string. This one will get one argument that is another string. And in this case, it's important to add the memory location. More on that a little bit later. And we are having an updated string. I like to make these underscores there that you maybe have seen in some of the code that is out there. And the reason for that is if you're interacting with outside JavaScript, then it becomes a distinct difference between getting writing a variable or reading a variable from Solidity to the outside world with the underscore, then directly inside JavaScript. That is just my style. I think there is a style guide for this, and I don't think it doesn't mention anything about underscores or so. Okay. Anyway, so you can name this like a variable. You have of the type string. It's strictly typed, and you even have to give it a location, which in this case is a memory location, which just means that it is our working horse cheap memory that this variable resides in. Now, we also have to give it a visibility. More on that again later on when we are writing the first project. In this case, it is public. It is not going to return anything because inside Solidity, you cannot really return anything to the outside world. You need the events for that. Also, we are going to talk about this more in depth, and then we are ready to update our string to update string. Great. You see everything still compiles, and when we hit deploy, then we can see here in our instance, we have now two different buttons. One is for the hello world, and the other one is to update our string. That actually requires us an input field. So if you just hit update, it still does it, and then it will override the string with an empty string. And if we can also make this a little bit bigger so it's more clear what is going on here, and then we can just say hello from Earth and then hit transact, and then our string is updated to hello from Earth. Now again, you can see everything here is with a call against the blockchain node. The blockchain node in this case is the JavaScript environment, so there is no real blockchain node. You're directly interacting with your browser here. And you can also see that there is one thing with a little check mark and the other one with a little call. That's a major difference between a writing transaction, something that would actually cost you money to get mined. It needs to be sent to the transaction pool, then a miner needs to pick it up, and then it gets mined and it gets baked into the blockchain. And a call. A call is a reading transaction. It is still a transaction, but it's virtually free because it's against your blockchain node, and every blockchain node that is participating in the network has the same information. It's basically the whole point of the decentralized part of this decentralized ledger. So everyone has the same kind of information running on his machine. And in your case, you don't need to query any other thing. You basically have a copy of the whole ledger and you can directly look into it, but it's still a transaction. It's just a free of charge. And that's then called a call. If you open it up, you can see that this is has a from address. It goes to a specific address and it has an execution cost. It doesn't really matter because it's a call, but over here with a transaction, you have an execution cost, which is in gas, which is very much like kilowatt hours for electricity, which you then pay with money. The whole idea there is the same. It's an abstraction. More on that a little bit later. And you have data that goes in, data that goes out, logs, and so on and so forth. Yeah, that's the point of this this video here, to tell you a little bit more about how you interact with your smart contracts, how you read and write to a smart contracts, what is the difference between a reading and a writing function. And with this, we can conclude our Solidity basics and Remix environment section, and we are going into an actual project. Now that you have your first smart contracts in Remix and you have interacted with them, let me quickly summarize the section before moving on to something more advanced. So in this video, I just want to quickly summarize what we did before. And we started off with actually creating files in Remix, and instead of just creating files, you saw that there is also workspaces where you can add workspaces, and you start with a so-called default workspace. And throughout the course, I will probably stay in this default workspace, unless we're doing some sort of specific advanced project where we might gonna add in an Open Zeppelin workspace. But for now, you can safely stay in the default workspace. If you don't have a default workspace, just create a default one. And most likely it will come with a very similar structure like this one. It will have a contracts folder where you guessed it probably correctly. There is the contracts inside, then a scripts folder, which is, I think, a fairly new feature of Remix, that you can execute actual JavaScript scripts inside a JavaScript environment. I mean, that's a pretty convenient thing. If you have a set of smart contracts that you want to deploy and pre-populate with some data, then that's the way to go, I guess. And then you have tests. I have not really used the unit tests there yet. I think they're working just fine. I'm just not a huge fan of Remix unit tests. I rather do them in Truffle, Hardhat, or now Foundry. Now, to add a new file, you don't click the little plus icon here, you click the little new file icon over here, and then it will create a new file in the folder that you selected. So it is a good idea to first select the contracts folder and then click the new file icon, and that one will create a new file in this folder, and you can name it My Contract Sol. Now, with that one, when you click it, you will end up in an editor on the right side, and there you can write your smart contract code or comments or anything else that you want to write there. If you have text files, and it's also a text editor, it's not just for Solidity. If you want to make it bigger or smaller because the font is too small or too big, you can add click the little plus or minus loop icon, magnifier icons there. It is not working with your keyboard where you press Control plus and minus. This will just make the UI elements bigger, but not the actual editor. So be aware of that. Yeah, with that, we have the remix files pane. Now let's get over to the actual compiler. In the compiler, there are a couple of things that you should be aware of. Number one is the compiler version that should be automatically selected based on the pragma line. So if the pragma is 0814, then it will select the compiler 0814. Now, if you have a semver compiler that specifies any compiler between 080 and 090, then you probably have to select the compiler version yourself. So make sure that you are maybe not exactly the latest one, but one of the latest ones, and understand what are those language features. One thing I can recommend you is to turn on the auto compile functionality. So every time you change something, it will run the compiler over here, automatically compile, and then already tell you over here with the little check mark. Or if it's not a check mark, then there's a problem. So you should be aware of that too. Now, the next thing I want to talk about is the deploy and run transactions plugin that you can find as the third option in Remix. And over here you have an environment dropdown. And for now, we are going to stay in the JavaScript virtual machine environment from Remix because it gives us already a couple of accounts over here, so we don't have to do any account management or wallets. That's already integrated. You don't have to worry about the gas amount at the moment. It is the amount of gas that is available for each transaction for computational operations during execution of a transaction. That is the default value from Remix. It is not the default value that has anything to do with Ethereum or whatever. Just somebody at the Remix dev team probably went ahead and said, like, well, 3 million, that sounds like a good number, so we're going to do 3 million as a default. I think the current max amount is around 8 million gas on the Ethereum main chain. You seldom actually send the max amount. You are estimating how much gas the transaction will need, and then it's automatically sending the right gas amount. So you're never, anyway, not overpaying because you get the reminder of gas back to your account, but it is just a better way to do it. The value field, you also have to not worry about it at the moment. It is if you want to send actual Ether together with a transaction with a smart contract interaction to a smart contract. We're doing this later with so-called payable functions. What is important here is the contract dropdown has the contract selected that you want to deploy, and then you can hit deploy. Okay. Next is the Remix interaction. So as soon as you have your smart contract deployed with the deploy tab, and underneath directly, I had no space there, underneath directly will be the smart contract instances. Every time you click deploy, it will deploy a new instance. That is important to understand because you cannot update code on the blockchain. It's immutable unless you're writing something like proxy contracts, which is something where I have a specific lecture about it on ethereum-blockchain-developer.com as an extra material, but it's not content of this lecture or section. Maybe we do something else with proxy contracts later in the course, but I have not planned it right now. So that is very advanced. If you want to update your already deployed bytecode, we are not doing this. We are normally going by having immutable contracts running on the address, and then you deploy a new one so it gets a new address, which you can conveniently copy here if you want to, and you can uncollapse your contract with the little collapse icon here, and then you can start to interact with it with these buttons. The blue ones are, or the greenish, I don't know what is this color, navy color, is for read operations, and the red or orange colors is for write operations, where you most likely also have an input field, and then you can also uncollapse that. And this one over here, the part on the lower end, is for low-level interactions. So if you are doing something maybe in a fallback function, which we are also covering later, then you can use that one. That was named previously differently, and it's very confusing. If you look at old YouTube videos, then this one is actually over here at the top of the smart contract, and is, I think, only called send and not transact. So they changed the UI around. It is a low-level interaction. This is what it is about, and I think the UI now better reflects it, but it is confusing if you are coming from older YouTube videos. Great. Next, we have the logging functionality of Remix on the bottom right, and you can make it bigger or smaller. There is a little, you have to hover with the mouse over here, and then you can drag it up or down. So if the log window is not big enough, then you can make it bigger. There you have a couple of things, and I just want to highlight them. I don't want to go too much into detail of them, because we are doing this later on again. There's two things which are outstanding. The one is a little checkmark icon, which is a writing transaction. And then over here, there's another one, which is called a call, which is a reading transaction. You see from which account, from which address you send it, to which address you send it is something that you should normally see, but Remix is hiding it. So you actually have to open it, and then you can potentially copy the contract address that it is sending it to with the little copy icon, I think. Otherwise, you have to see what kind of smart contract you are interacting with in another way, and I don't know what other way would there be other than the address, because the contract, if you deploy several of them, they all have the same name. Then you see gas and transaction costs, something we are going to talk about later. You see there's a transaction hash. Each and every transaction has its own hash, which is a unique hash, like an AN code for books. You have a transaction hash for transaction. Think about it this way. There's a status. If the transaction is successful, and everything is fine, there were no errors, then this returns true, otherwise it returns false. And there is a data field, which in Remix is called input. I don't know why they called it input, but a native transaction in Ethereum, that would actually be the data field. And that's the thing that smart contract developers are interested in, because this is, when you compare it to the data field over here, that's actually called data, then this is the data field. This is the code that you send to interact, to deploy a smart contract or interact with a smart contract on the low level. And this is something that we are going to deep dive into. Now, with that, pretty much everything is said. There is also a debug button for the Remix debugger. We have a separate lecture on that. And yeah, that's it. I think you can go safely to the next lecture if you understood everything of that. And we see you in the next section, where we actually do our first small project. Can you imagine that? In just as little as 1 hour, what you already learned now, a new development environment, you also wrote your first Solidity smart contract and you interacted with it. Furthermore, you know that Solidity is not an interpreted language. It actually needs compilation. You learned about the compiler and so on. You also know that everything is transaction-based. There are no live updates, and contract code is basically immutable. Every time you want to update or change your contract, you need to deploy a new one. Remix is a perfect tool to get started with blockchain development. And for a little while longer, we are going to use Remix to dive deep into Solidity. That's why in the next section, we are introducing our first project, a simple messaging contract. You learn the first basic types of variables and some very Solidity specifics. Enough talking from my side. I'm sure you're very eager to learn more Solidity, so I'm looking forward to seeing you in the next section. In the previous section, you already set up Remix and compiled and interacted with a smart contract, but you don't have much Solidity knowledge yet. In this section, we're building a smart contract called the blockchain messenger. The goal is very simple. This contract will save a message on the blockchain, readable to everyone, writable only to the person who deployed the contract in the first place. We also count how many times the message was updated. At the end of the section, you should have a better understanding of the most important value types in Solidity, like integers, Booleans, and so on. You will also know a special kind of variable called address. And you will know a little bit about the important global message object and a few of its properties. Of course, you will also know the basic structure of smart contracts like read, write functions, and constructors. In this section, we are going to continue using Remix as well as the JavaScript VM for that. I'll introduce the theory you need to complete the project first, and then we're putting it all together into the blockchain messenger. Or maybe you want to challenge yourself and after going through the theory, try to complete the project yourself first and then simply compare it to my sample solution. No matter what you do, I hope you're here to learn some solid programming with Solidity, so let's dive into it. So the first one, and probably the most easy one to understand of all of them, is Booleans. Booleans have a true or false as a value, and they are defined as a bool, and we're going to start doing that with a sample contract. Just hit create new file over here, and then let's call this example boolean.sol. I'm gonna have again an SPDX license identifier and the pragma line. I just copy it over from our sample contract before, and we are calling this example boolean. Okay, let's define a boolean and just see what happens. Bool, my bool is nothing. Just define it like this. You see it's still compiling. And if we are going to deploy this contract, well, we cannot do anything with it because we have, first of all, no function. There is no interface to interact with this smart contract at all. And our Boolean is also not public, meaning Solidity will not automatically create a getter function for it. So if we are making this public, then it's compiling again, we can deploy it again. And then you see over here, we have now a button, my bool, which has the same name as the variable itself. So it's creating a getter function with the same name. And when we hit it, it says false. And the reason for that is that it's not erroring out. In other languages, you would have to initialize the value. But over here, you don't need to initialize the value with anything. It has a default value. And for Boolean, that's false. For integers and unsigned integers, that's 0, and so on and so forth. And we're going to talk about this later on. I'm going to summarize it later on for you. But let's just keep going over here. So we are going to write a setter function so we can set this Boolean function, set my bool, and then we are having an argument that is also of the type bool. And I just call it the same name with an underscore in this case. Public, it doesn't return anything. And we are setting my bool is my Boolean. So we are overriding that variable. Now let's deploy this again. Initially, let me close the other ones. Actually, let me remove them. It's really not necessary to keep them. Oh, maybe I removed the wrong one. Okay. Now we have a setter function and a getter function. We are calling my bool, then we are setting my bool to true, and then we are calling it again, so it's true now, and then we are setting it to false, and then it's false. Setting it to 1, it's true. Setting it to 0, it's also true, which is a surprise to many of you probably, and the reason is it's actually meant to be written as a false. Otherwise, it will just do a weird kind of conversion between integers and Booleans, and it will end up with a value other than false. It's false again. Okay, there's nothing much more to say to Booleans. In our case, you can do negation, logical negation, meaning that when you set this now to true, it will end up being false. Let me move this again here. So when I set this to true, it ends up being false, and the reason is it's going to negate whatever we send over here. You can do logical conjunctions, so true and something, two Booleans. You can do logical ors, or equals, or inequality. So that is basically everything you can do with Booleans, and that should be fairly familiar for everyone who has ever done anything in any programming language. Booleans are fairly commonly used across all languages. Okay, with that being said, I think we're heading over to the next example. The next thing that I want to talk about are integers and unsigned integers. What are integers? What are unsigned integers? Integers and unsigned integers are full numbers, meaning they have no decimal places, and the difference between unsigned and signed integers is the signed ones can go to negative, while the unsigned integers only range from 0 to something really large. How large can they go? They can go between 2 to the power of 8 to 2 to the power of 256 minus 1. So from 0 to 256, and from 0 to 2 to the power of 256 minus 1. And let's define some. Let's just play around with it, because they have some very particular side effects in specific Solidity versions. So let's just start with a new smart contract over here. Example, let's call this example uint.sol. Bring over the SPDX license identifier and the pragma line. Let's just define an integer, call it uint myint. Let's call it my uint, because that's better. Again, we are going to make this public because we have then a getter function. So if you are just running this, if you are just deploying this over here, and then we are clicking on my uint, by default, it's going to be 0. There's nothing initialized. We can obviously, or maybe not obviously, but we can also define a specific value at the beginning. So if you want to have a storage variable already initialized with a specific value, then you can do this as well. It's going to be the initial value, or you can do it in a constructor, which we are going to do later. There's one thing, if it's just an advanced use case, but if you are assigning a standard value that is already the default value for the uninitialized variable, then it will actually cost extra gas. I know we're not quite there yet with the gas, but maybe something to keep in mind. If you just need the default value, just leave it blank as a habit. So let's write a setter function, set my uint, my uint, public, and then my uint is my uint, so we can actually look at that. Got the wrong one, so we can update this over here. Now, uint alone is actually an alias for uint 256, and this is the size of the unsigned integer variable that you have then. So this one could store values from 0 to 2 to the power of 256 minus 1, which is pretty large. And it's very beneficial that it's pretty large. It's much larger than the max int from JavaScript. That's why you maybe have seen already that some of the Web3 projects are using a library called Big Int or Big Number. So you can actually work with much larger numbers than JavaScript in the integer space gives you. You can also have smaller unsigned integers and signed integers. They are ranging from uint 8 my uint 8 to uint 16, uint 32, uint 64, and so on. So you can have different sizes. And I mean, for a beginner, obviously, it would make sense to leave everything as uint 256, so you have the full space. But if you want to save on storage cost, on gas cost, then you need to define smaller ones. But beware, there might be certain side effects down the road if you suddenly have used up the space, the integer space that you can actually use there. So let's try what happens if we are going to simply increment my uint 8 until it hits the max uint 8 value, which is 256. So let's go function increment uint 8. And then we are going to my uint 8. And instead of writing is my uint 8 plus 1, we are just going to write plus plus, which is the same as just incrementing it by 1. Now let's deploy this. And instead of starting here with 0, we start with 250. So we can, after 5 times clicking on increment uint 8, then see what happens if we hit the max value. So my uint 8 is now 250. I increment it, 251, increment it again, 3, 4, 5. Oh, what happened here? Oh no, it can store 256 values, so the max is actually 255, so it goes from 0 to 255, or 2 to the power of 8 minus 1. So it hit an error here. It says, well, there's like not enough information, blah, 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 and it is a VM error revert, and it reverted to its initial state, meaning the transaction that we sent failed, and it stays at 256. And there's a huge difference to previous versions of Solidity, which were just rolling over back to 0, which is something I want to discuss specifically in the next lecture. For now, let's define an signed integer as a last variable. So we have covered that as well. Let's just define an int, public my int, and just go to -10. And then we are going to increment that integer over to over 0. My int plus plus, and over here you can go from -2 to the power of 128 minus 2 to the power of 128 to plus 2 to the power of 128 minus 1, I think was it. So the address, I mean the number space is just shifted. Instead of 0 to 2 to the power of 256 minus 1, it's going from minus until it hits 0 and then the plus side. And yeah, if you're just running that, then the integer is -10. If we are incrementing that integer 10 times, or yeah, then it goes to plus. On the other hand, if we are trying to decrement an unsigned integer, then you probably guessed it already right. My uint minus minus, so that would decrement it by 1. My uint is 0. If we decrement it, it will fail because it cannot go to negative numbers. Yeah, that's it. Basically what I wanted to cover with integers and unsigned integers. Obviously, there is also comparisons, like is it larger, is it smaller, is it equal? You can also shift, which we are not going to use. And there is arithmetic operations like plus, minus, multiplication, modulo, and exponentiation. exponentiation is maybe a little bit special because it is the double star. So if you want to have 2 to the power of 4, then you would write it like this. And if you deploy this, then you have 16, which is 2 to the power of 4. All right, that's it for this one. I will see you in the next one where we are discussing a special case, the integer rollovers. In this video, I want to discuss something that is very specific to Solidity versions prior 0.80, because prior Solidity 0.80, arithmetic operations would always wrap in case of an under or overflow. And there is a really widespread use of different libraries that introduce additional checks. One of those libraries, SafeMath, which if you become a Solidity developer, if you become an Ethereum blockchain developer, inevitably you will see it somewhere. And if you just work with Solidity 0.8, you will not understand why somebody in the name of God would ever use that. So in this lecture, I want to show you how the wraparound works, and I want to show you what changed in newer Solidity versions, and I want to show you how you can still have that old behavior, because sometimes it is actually pretty useful if you have some sort of counter or some sort of running counter that just counts from 0 to the number up and then back to 0. But let's start with the smart contract first, and then we can talk about the actual stuff that it does. So let's start with example wraparound Solidity file, and we are going to, let me just copy the whole thing over here. Sample wraparound, and let's stick with the uint 8, and the uint, we don't need the integer. That one can go. Okay. So as you know from before, when I deploy this and I'm calling decrement uint, then it will error out. And the reason is that we are starting with 0, and if we decrement an unsigned integer, a 0 unsigned integer, then it cannot go anywhere unless it does a wraparound. So if you're changing the compiler version to, I don't know, 7.5, and it's going to take a little bit because it needs to download the compiler and then it can compile it. So if you're using an older compiler version and if you decrement it, oh, suddenly it works. And now what is the value? The value is really large. The value is the max unsigned integer value of, it's basically 2 to the power of 256 minus 1. That is the value over here, or at least it should be. And in version 0.8, they changed this behavior from an unchecked arithmetic operation to a checked arithmetic operation. So there will be, after compilation, there will be an additional check inside the bytecode to make sure that the increment arithmetic operations are not rolling over the integer or the unsigned integer or whatever variable it is. So in order to get this behavior back from the unchecked behavior back, you actually have to wrap it in an unchecked block that looks like this. And now if you're running in 0.815 or 14 or anything larger than 0.80, if we're gonna deploy this one, my uint is 0. If we are decrementing, suddenly it is also working because it's just wrapping around the value. Now, if we are, for whatever reason, wanting to mix and match this, then you can only for specific functions where you specifically want to have this behavior wrap the arithmetic operation in an unchecked block. And that's basically how it works. There's nothing more to say about this. What these libraries did, SafeMath are these called usually, or I think SafeMath is by far the most popular one, are functions to make sure with require statements if you are adding values, if you're subtracting values from an integer, that they are not rolling over and actually erroring out. But this was all done in Solidity natively now, so there is no need anymore for those libraries. Just in case you're wondering what are those libraries, this is what they're used for. That was the reason that the arithmetic operations in Solidity were not safe. All right, with this, enough said, off to the next lecture. The next thing I want to talk about are strings, and strings are actually arrays and very similar to byte arrays. Now, if that sounds a little bit too complicated, let me break it down for you. So that's somehow also very unique to Solidity. In strings, there are no string manipulation functions whatsoever, except of one, that is you can concatenate strings, you can put them, merge them together. But natively, there are no string manipulation functions. There are a couple of libraries that help you with that, but there is not even a native string comparison possible. You can use the Kaiser cache of two strings and then compare this one, but there is basically nothing there to let you really work well with strings. And the reason for that is strings are extremely expensive to store on a blockchain. Now let's get started with an example. Going to open up our contracts folder again. Let's call this example strings sol, and let me copy over the SPDX license identifier and pragma line, and then contract example strings. And let's simply define a string public. My string is hello world. We had this at the beginning of our course already. If you're going to run this, then you can see hello world. And now let's write a setter function for it. Function set my string. And over here, you already see a difference to the others. Before we just had the type, and then we had the variable name. But if we are going to do it like this, then the compiler will error out and tell us, hey, data location must be memory or call data for parameter in function, but none was given. So we can maybe place this parameter inside our memory location. Memory is an ephemeral data location to work within functions or just during the transaction. The memory location will be gone after the transaction is finished. So in order to make this permanent, to make this stick, we have to bring it over to a storage location, which is where storage variables are stored at. So let's just define this. Let's override our storage variable, redeploy this, and hello world, and now it's ASDF, the string that I entered. Now, in order to compare two strings, and let's just say we are giving a string memory, my string, and then we want to know if this string is the same as our string that is already stored. And in this case, we are doing something that you have not learned, but just follow along. We are not making this only public. We are making this a public view function, meaning it is a reading function and it can actually return something. And we are going to return a Boolean over here. Booleans, you have already learned, can only be true or false. And what we are going to return is if my string, the storage variable, is the same as my string, the memory variable. And normally you would say return my string is equals my string. But our compiler doesn't like that because of something that actually doesn't make any sense. Returns. Okay, now it went to the right location. So it says the operator equals is not compatible with type string, storage ref, and string memory. What can we do here? So the thing is, there is no native comparison. You have to use the KZAC 256 hash of this one, and the KZAC 256 hash of that one. And because the KZAC 256 hash function actually requires a single bytes argument, you also have to ABI.encode packed this one, and ABI pack that one, and then it should work. So then we can actually do a string comparison. So right now our string is hello world, and if you want to compare this to hello Goofy, then it will return false. But if you return hello world, let's hope it returns true. Yes, it returns true. So now we're actually not comparing the strings, we are comparing the hashes of the strings. Now, there is also a difference between strings and bytes. We can very well say bytes public, my bytes is hello world. And if we are going to deploy this one, it will return us the bytes representation of this string. But there's not only that difference. You can technically strings are just the same as bytes, and there's a major difference. Number one is with bytes they have a length, so I can say my bytes.length, and I will get back the length of these bytes, and I can also convert them. But with strings you cannot convert every string into bytes and then get the length, because strings are represented in UTF-8 while bytes are not. That means that sometimes a character is represented by 2 bytes and sometimes by 1 byte. So if you just access the low-level representation over here, then you always get 1 byte, and you maybe, if you have UTF-8 characters, I think like the umlaut, the German umlaut, or specific emojis and so on, they all need 2 bytes to represent the actual character, so you would get the wrong length, and it's actually very hard to calculate this back. So this is why in general it is not very advisable to use strings in smart contracts, but for our project we are still working with strings, and I think that's then pretty much the last time, unless it's something like symbol names for tokens. With that being said, off to the next lecture. One type which is very specific to Solidity is the address type. Address types are storing 20 bytes worth of an Ethereum address or an Ethereum account. So let's run an example and see how that works. I'm going to create a new smart contract, example address sol, and we are going to run this over here. Contract example address. All right, let's make an address type. Address public some address. And let's see how that looks like if we are going to deploy this and have a look what's inside here. It is by default a 0 address. So it's 0x0 and then basically followed by 40 zeros or 20 bytes worth of zeros. How to write those addresses? Well, function set some address some address public some address is some address. Let's kill this one, deploy a new one. And if you're going to write 0x01, it's the wrong argument. So you need the exact characters for an address. Where do you get an address from? Now you can copy it over here from your account. You have 20 accounts, I think, or so. And those are all addresses. They're just abbreviated with little dots here, but those are all addresses. And you basically can copy this one, paste it over here, transact, and then the address is this one. An address also has a member property that is balance. So if you are want to get the balance of an address, then you can do this with the property balance. So function get address balance. And let's make this again a public view function because we want to read something. More on that in a second in one of the next lectures where we are talking about view and pure functions. Just follow along. It's a view function. We want to read something. And it returns an unsigned integer, 256. I'm just writing u into here, the short form. And then we are going to return some address dot balance. You see here from this storage variable, the address balance. So we are going to deploy a new contract. We are going to get address balance. It's 0 because some address is right now the 0 address. Then we are updating our address with this address over here from the dropdown. It says it has 99.99999 something ether. And then we are updating this. And then it says the balance in way. What are way? 1 ETH equals 10 to the power of 18 way. And way is the smallest denomination on the Ethereum blockchain. So everything you do inside the smart contracts will most likely always be denominated in way. So if you want to convert it to ETH, then you need to use 18 decimal places. Yeah, there's a lot more denomination. You can see them on our accompanying website, ethereum-blockchain-developer.com. where I'm going to write down all of the most important denominations. The other one is... Now we have already quite a bit of variable types together. There's one more thing that I want to discuss before actually wrapping it up. That is the message object, and in particular the property message.sender. There's a lot more in the message object, but in general, I want to discuss this first. So let's get started with an example, because I think this is one of the most important parts of Solidity development and Ethereum blockchain development. So this is where it really separates a classical database, like a centralized access system with some sort of authentication, with our with the blockchain-based access where we have private and public keys. So let's say example message sender.sol. And in the previous example, we had the addresses, right? So we are just copy over this whole thing. So we have the pragma line, we have an example message sender, and we have some address over here. And what we are going to do now is we are going to write a function, update some address, but we are not giving it any kind of parameter at all. We just make this public. So it's a writing function, and we say some address is message.sender. And the message object, you already see it here in Remix. It gets a special color. It is a public object that is available throughout all of your contracts that contains a couple of properties. And one of these properties, sender, contains the address of the person who is interacting with the smart contract. It's very important to understand that if an account is calling the contract, then it will contain the address of the account. So let's say an account contract, then message sender is that one. If an account is interacting with a contract and that one is interacting with another contract, then message sender over here will contain the address of the last point of contact what is interacting with the smart contract. We are going through this in more detail later, But I wanted to clarify this right away because there's a lot of mistakes that happened from projects on the web, especially at the beginning, DAOs that had confused who is interacting with the smart contract and then had wrong access lists and so on. Well, let me see how this actually works. So if we are going to deploy this smart contract, then our sum address is 0. And if we say update sum address, then it will become magically this address over here that interacted with the smart contract. If another address is interacting with the smart contract, then that one will still be the old one, update sum address, and now it will be the one that interacted with the smart contract last. Yeah, and that's basically the thing that I wanted to talk about for the message sender. And now we are talking about two more things, that is view and pure function. I just quickly want to show you how they work because we already used them before. And then also the constructor in Solidity, it's a special kind of function. And then we can wrap it up, putting it all together and write our project to have the blockchain messenger done. One thing that you have used already is the view functions, and in this lecture I want to go through the 3 different function types that we have in Solidity, that is writing functions, view functions, and pure functions. So let's start with an example over here, example smart contract, example view and pure. Solidity, let me copy over the first part over here. And then contract, example, view, pure. Okay, let's define any kind of storage variable that you can think of. And I usually use unsigned integer, my variable. Or let's call this actually my storage variable to make this more clear. Okay, if I deploy this over here, then you already know what happens. It has a public, it's a public function. It is a public variable with a public getter function called my storage variable, and I can get this content of the storage variable back. Now, you also saw that these are color coded over here. That is purely for UX reasons, but you also know that this is a call, a so-called reading function. Now, there are 2 kinds of reading functions. The ones that are view functions, and I'm just going to explicitly write a view function now to access this my storage variable. Function get my storage variable, public view, and it returns an unsigned integer because it's gonna return my storage variable. Okay, if we deploy this, then we get the same result, obviously, and both of them are having the same color because both of them are view functions. Now, let me write a so-called pure function. Function get addition, uint A, uint B, public pure, returns uint, return A plus B. Okay, this one is a pure function, and the difference between a view function and a pure function is that the view function can access storage variables, or in general, it can access variables outside of the scope of the function, but it cannot write them. And the pure function can only call variables that are not storage variables or other pure functions. So in this case, we are just having the unsigned integer A and unsigned integer B as parameters, and we are not using any other storage variables or view function or write anything. So this is the major difference between view and pure functions. They have, interestingly, the same color coding, yet they are both called a call because they are reading operations. 5 and 6 should be 11. And they both cost nothing, virtually nothing. You still need gas because they burn some gas. There is some operations that are done, but you wouldn't pay anyone to mine a transaction. This is the difference to a writing function. So if we have a function set my storage variable uint a new variable, and then my storage variable is new var. Then let me clear all of this. My storage variable is empty. I set it to 5. Now it's 5. You had this before. It has no kind of identifier, nothing that says it's a writing function. It is just not a view function. So it's actually writing something to the blockchain. The thing is, in Remix, because it is a simulated blockchain environment, you don't need to wait for the mining. Mining is here instantaneous. So as soon as you press the button, there's a new transaction that's being mined. You can actually return something over here. For example, the new variable returns. But let me tell you that this is actually a bad idea. When you open this up, you can see here that it actually returns it as a decoded output of the U256 is 234. It is a bad idea because these return variables are actually only meant for inter-contract communication. So when contract A calls contract B and there's a return variable, then this can work. If you work on a real blockchain outside of this JavaScript virtual machine environment, then you actually use events for that. This is something we are going to do later. Just remember, writing functions usually don't have return variables, and if they have it, and it's only meant for other smart contracts, you cannot get the output over here. You can try this. We will see later when we download MetaMask and use Gurley or Robston or other test networks or Ganache. Even in Ganache, you cannot see any output anymore. It's gonna be blank. Yeah, enough for the writing functions. This is all I wanted to talk about. Let's quickly talk about the constructor in Solidity, and then let's put it all together. Okay, the last thing that we need to talk about before we can wrap it up is the constructor. So let's create a new file called example constructor Solidity. Let's copy over the stuff that we need as a scaffolding and contract example constructor curly brackets. And let's create an variable of the type address, public my address. So as we know from before, if we are going to deploy this, then it will be the 0 address. It will be initialized with its default value. Now, of course, we could go ahead and write a function, set my address to an address, my address, public, my address is my address, or we could even go ahead and set my address to message sender. So we can set this to the message sender. When we deploy this, then we can set this either to something that we want, or we set this to the message sender, and then it's going to be the message sender. But if we want to assign our address, the ones who deployed the smart contract, to my address, then we could do this. But if you want to assign it directly at the deployment time to another address, then we would have to actually call 2 transactions. So we cannot make this a variable that is assigned during deployment. We would have to deploy the smart contract. This is exactly where the constructors are coming in. So what is a constructor? A constructor is a function, a special function that is called constructor. It doesn't have the function keyword, and it accepts the kind of arguments, some address. It has no visibility specifier, and it just has curly brackets. And the special thing about a constructor is it is directly called during deployment of a smart contract, and it is called only once and cannot be called afterwards again. It cannot be overloaded, which is something we might gonna dig into later. And it is automatically called. You cannot not call it. So if we are going to set our my address to some address, then we get, when we try to deploy this now, we get over here, we suddenly get an argument that we can provide. So let's say we want to copy this address over here and paste it here. You can copy any kind of address you want to, but then our my address is suddenly the address that we pasted over here into the argument field during deployment. Yeah. And that's basically everything I wanted to discuss with the constructor. You will see it later on when we do tokens, or when you have a look at any smart contract samples online. There's tons of constructors. They are used very heavily to assign values to storage variables or do stuff during deployment of a smart contract, like assign owners and other things. So let's wrap it up, and I will see you in the next lecture. Before we continue, let's wrap up the simple variables that we went through and a couple of infos just to make sure you understand everything and we have covered everything that is necessary to know to finish the project. All right, what did we do? We actually went through a couple of value types, that is Booleans, integers, unsigned integers. We talk now a little bit about fixed point numbers, even though they are not important for the project, but I think it's important to understand how is the support for fixed point numbers in Solidity. We talked about addresses and we talked about strings. And yeah, we didn't talk about enums, array, structs, or mappings yet. This is something we do for the next project. Okay, so all variables, no matter the type, they are initialized by default. There is no null, there is no undefined, there is nothing like a segfault or anything. You can safely assume that if you define a variable and you don't initialize it, then it's initialized with its default value. For integers, that's 0. For bool, that's false. For a string, that's an empty string. Public variables generate a getter in Solidity, and you cannot create a function with the same name as the variable yourself. This is just something good to know. I'm sure you have thought of it probably. And if you ever think of something like this, just give it a try. Remix is there to play around. Reference types needs a location for the memories. It can be memory storage or call data. And in this case, you saw it with the strings. We had to give the string memory and then my string. Okay, with Booleans, we started off with Booleans. They can be true or false. They are defined with bool and then your variable. You can negate them, and they have and, or, and all of the other things you probably, hopefully know already from another programming language. I hope Solidity is not your first language that you learn, because it's pretty hard with all the surrounding blockchain stuff. But I heard there's also people who started with Solidity. All right, integers, unsigned integers, they are in 8-bit increments going from uint or int8 to uint 256 or int 256. uint8s range from 0 to 255, so from 0 to 2 to the power of 8 minus 1. Integer 8 ranges from minus 128 to plus 127. So they are shifted exactly to the negative area. You can write exponential values with the 2 stars. And the unsigned integer 256 is ranging from 0 to 252 to the power of 256 minus 156. So that is a fairly large number. uint is an alias for uint 256 and for unchecked. And please remember that is only for unchecked values. And that is also for Solidity 0.8, or well, it becomes important from Solidity 0.8 that there's an automatic wraparound. And before 0.8 is also, there is no checked values. So this was a new feature from Solidity 0.8. Okay, then let me quickly talk about fixed point numbers, because there is this huge confusion about fixed point numbers. Fixed point numbers are not implemented in Solidity, still not. And there is nothing, as far as I know, on the radar that they are becoming implemented, because it's really not necessary. What we do instead is that you take a very large integer number and then give it somewhere like a decimal point. Let's say you want to have 2 decimals in your system. So you say, we are going to have a decimal point at the second 0. So instead of writing 100,00, you just write 10,000, and then you say over here's the decimal point. So most of your arithmetic operations actually check out. So for example, 100 minus 53,01 is 46,99, and that actually works out. So this is also why in a lot of tokens, in a lot of token contracts, you see that there is 18 decimal points that is defined in the IEEE standard for floating point operations. I'm not sure if this is actually a coincidence or maybe not, I don't know. But most tokens, especially the ERC20 tokens, they work with 18 decimal points. So you have a really large range for super tiny fractions of tokens. And you will also see this later. All right, we talked about addresses. Every interaction on Ethereum is address-based. They hold 20 bytes of values or 40 hex characters. And they are used, you will see this later, to interact with other smart contracts. They are used to transfer money. They are used to send funds. They are used to delegate calls and so on for libraries. So all of this is address-based. There's two kinds of addresses. We have only discussed a simple address, but there's also a payable address where you can send money to, which is something we're doing in the next project. And they have a member called balance, and that's something we discussed. So we said address.balance, right? And they gave you back the balance in way. It's important to know that everything is based in way. If you want to convert it to ETH, then that is 10 to the power of 18. Way would be 1 ETH. Strings and bytes, both are special arrays. String is kind of equal to bytes, but it doesn't have a length or an index access. So if you want to have like the nth byte of the string, you have to convert it to a bytes array. Bytes are for arbitrary length data, but be careful if you convert strings to bytes. String is represented in UTF-8 data, and all of them are expensive. So it's always better to avoid strings and store strings maybe off-chain, and then just only the necessary information on-chain. But for this project, obviously, we use on-chain string data. As a key takeaway, Solidity has several typical high-level language variable types. So everything is statically typed. The thing is with Solidity, especially with the cost, not all rules of modern development apply to blockchain development. You have to be very careful with that. If you come from a Java world, from an enterprise world, usually you want to have well-defined objects, and you leave enough space for your all eventualities. You basically. Alrighty, now it's time to put together what we've learned into one project or one contract that is called the blockchain messenger. Just to repeat, what it does is it can store a string on the blockchain. It is readable for everyone, but it's writable only for the person who deployed the smart contract in the first place. Now you have everything in place. You know what are strings. You know what are the message sender, you know the addresses. One more thing, we also want to know how many times the message was updated. Now you can pause the video if you want to try it yourself, or you can follow along for a sample solution. First thing, what I'm going to do is I create not a new workspace, I create a new file called the blockchain messenger.sol. Now this can obviously all vary by whatever you're planning to do, or they were kind of like that is not set in stone. So it depends on what you want to do, what kind of naming schema you want to have. Contract the blockchain messenger. And in here we have a couple of things. That is one time a uint that we're gonna make public. We call it change counter. And then we have an address public owner. And then we have a constructor that is going to set the owner to the message sender. Yeah, I know if you maybe have tried or not, you can also directly do message sender, but I'm old school. I like to do it in the constructor. And then we also have a string public the message. And then we have one function called update the message string memory new message, and I still like to put an underscore in front. That's public, and we can update the message with the new message, but we only do this if the message sender is the owner. Then update the message and also increment the change counter. All right, let's give this a try. Blockchain messenger. So who is the owner? We are the owner. How many times was the message changed? What is the message? Nothing. Hello world. New message. How many times was the message changed? Once. The message is now hello world. Let's switch over to a different account. Let's try to update the message to hello earth. Still goes through. We haven't learned anything about error handling, require, or assert. So that's something that we do in a later project. Change counter, still one. Didn't update anything because our current message sender is not the owner. The message is still hello world. All right, that's it. That's our blockchain messenger. Now, don't stop now. Let's get on to the next lecture. Let me quickly summarize it, and then to the next project. Wow, this was not bad for a first real project. The question is, what's the difference between your level of knowledge and someone who's been doing Solidity development for a few years? Of course, there's still a gap, but we're quickly closing in. We can already write some pretty complex code, make use of some very specific Solidity functionality like addresses and message sender, and compilation and deployment procedures. But we did not interact with the real blockchain yet. We did not send any Ether around. So far, we were running code in our little sandbox, and that's it. It's time to escape our sandbox and get into the real world. That's why in the next section, we are introducing wallets, test networks, and value transfers. Come on, stay on for a little longer, watch another video or two. It's getting very exciting. Have you ever wondered how these fancy DeFi projects work? These projects where you apparently can send money around, like adding code to a bank account? It's time to introduce just that. It's time that we see how a real blockchain feels like when being utilized by us as blockchain developers to send Ether from accounts to contracts and from contracts to accounts or other contracts. In this project, we are creating a smart contract that can manage its own funds. It's going to send Ether to other addresses. You will learn about sending funds from wallet A versus sending funds through a smart contract. We are also installing MetaMask and getting some test Ether through a faucet. Again, I will introduce all the theories you need to complete the project at the end. Then it's up to you if you want to challenge yourself to finish it or follow me for a sample solution. Either way, it's going to get really exciting now, and we're diving deep into some of the best features an EVM-based blockchain has to offer. So stay on, I will see you in the next lecture. Before we can do anything on a blockchain, we need some sort of access and we need a wallet. And with MetaMask, we somehow get both in a convenient way that it's directly installed in the browser. So I've opened up here the website for MetaMask. It's MetaMask.io. Be careful, there are a couple of scammers out there. So make sure that you are on the right MetaMask website. I'll just make sure it's metamask.io. And then we can add it to our browser. I have the Chrome browser here. There is a plugin for Brave, or I think Brave even has it installed already. There's a plugin for Firefox. I think for Safari, you can have MetaMask on your mobile phone for iOS and Android, as far as I know. And it features an in-app wallet. So I think it's a pretty convenient app. And I'm using it basically every day. You can even attach your hardware wallet to it, which is extra convenient. Okay, so what do you do with MetaMask? You download it for Chrome over here. It redirects you to the Chrome Web Store, and then you basically just add to Chrome, add the extension. Takes a little bit, and it should pop up in a second. And then it directly redirects you to the setup procedure. So when you first start MetaMask, you run through the setup and you get a seed phrase. Let me show you what I mean. Get started. No, I already have a seed recovery phrase if you already have one. Or if you don't have one, then let's get set up. And this is what you want to do the first time. So you get a seed phrase. You can help improve MetaMask or not. Either way, it doesn't really matter. And I don't have any recommendation here. And then you set up a new password, and that should be a strong password. It is not a password for a server. It is a password to encrypt your local store that is stored inside your browser. So that whatever you do in MetaMask now is not going to be sent to any centralized server. So there is no database to be cracked. It is, if somebody gets access to your computer, that he's not able to decrypt or to get access to MetaMask and to your keys and your funds and so on. So make it strong enough that if you lose your laptop or you forget it somewhere, you have somebody using it, that he cannot get access to it so easily. So I'm just choosing a random password now, agree to the terms, and now comes the important part. They even made a video about it. That is the secret recovery phrase. So this phrase is unique for every MetaMask user, hopefully. It is a 12 words mnemonic, so that you can easily write it down or save it somewhere. And you can easily reuse it if you reinstall MetaMask on a new computer. So what you should do here is you copy this and then print it out and put it in a safe or store it somewhere really, really safe. And I'm going to talk about this also in some of the slides that I'm going to show you in one of the next lectures, why this is so important. But if you lose access to MetaMask, that's the only thing that can bring access back. So there is no recovery, there's nothing that the MetaMask team could do because there's nothing stored on their servers. Everything is locally in your wallet. So that's the only thing you really have to be careful about. Copy this, save it somewhere safe. So I'm just going to paste it for now into my editor and then print it out later. And now obviously I'm not going to use this seed phrase for anything other than the course. But you need to reconfirm the seed phrase on the next page. So it's exchange glance wage example, just is serial, balance rigid curtain 8 sky, balance rigid curtain 8 sky. Once I confirm this, then MetaMask knows, okay, I really have copied my seed phrase somewhere safe. I've written it down and it's not going to remind me anymore. If you don't do this, then MetaMask will occasionally pop up and tell you like, hey, you should save your seed phrase somewhere safe. It's really important. And it is important. So if I can recommend you one thing, keep the seed phrase safe. What happens next is that you get access to MetaMask. And MetaMask has a couple of features that are not so obvious for a first-time user. So let me just quickly highlight them. Okay, so over here on the top, you have a network selector. And that network selector is here to select the different Ethereum networks. When I click on it, then initially you have nothing, but you can show and hide the test networks. And that is very important because we are going to work with test networks here. We are not going to spend any real Ether. We are not going to spend any real Ether. We are going to spend only testnet Ether, which are for free. So when I click now, I have the different test networks, and I can also add my own networks, which is also something we're doing later on. If you work with test networks, they are like a dev database. They are a completely separate environment. They have nothing to do with the real Ethereum mainnet, other than they work exactly the same. So you can run smart contracts, you can interact with each other. All the rules that are applied to the mainnet are also applied to the test networks, just that you get Ether for free. Okay, on the next thing, you have the kind of like a settings, accounts menu, like a MetaMask main menu. And over here, you can not only lock it, which I also recommend when you go away from your computer, but it also auto locks. You can add new accounts. You can import accounts from private keys. You can connect your hardware wallet, or you can go into the settings. There is one setting I very much recommend you to know. That is here in the Advanced tab, the Reset Account setting. So if you work with different test networks, especially as a developer, it has something to do with the nonce. The nonce is for each and every transaction, that's a number that's getting incremented. And sometimes MetaMask gets confused when you work on different test networks or on your own development networks. In case a transaction gets stuck, just remember reset account. So that very often helps. Other than that, I can recommend to go through the settings yourself, have a look, see if you find anything that you want to personalize or whatever. We probably won't need it, and if we need it, I'm going to mention it separately. So now we are getting to the actual main window over here. You have a couple of buttons here and a couple of things that are important to understand. The one is your account. You can rename that over here in the account details. You can rename that account. More important is the actual address. When you click on it, you can copy it. So that is a feature that you will need very often. This is why I'm highlighting it. Then on the mainnet, you get a buy button where you can actually buy Ether, real Ether, on the test networks like the Robston test network, which might get sunsetted soon when ETH 2.0 comes out. When the POS merge comes out, and it will be a different test network. It really doesn't matter for us as long as you're on one of the test networks. The buy button will still be there, but you will be redirected to a faucet. And the faucet is a place where you can get Ether for free for testing. Now there is no mainnet faucet, at least I don't know anything, because there's the ETH on mainnet cost real money. The faucets are usually there for testnet, and if you see some mainnet faucet, be careful, it's usually a scam. Okay, but I will show you in the next lecture a different faucet which worked for me very well. So sometimes the MetaMask faucet doesn't work, and there's a couple of problems with them. Obviously, the incentive to run a faucet is very low because it just costs money, it doesn't bring anything. Okay, then there's a send button, and that is the next thing which is important, which we are going also to do in the next lecture. We can send Ether, money, we can send transactions from one account to the other. And that's everything I wanted to talk about right now. If you came so far, you have set up MetaMask correctly. There is one more thing. If you close this, how can you get back to MetaMask? And that is over here. There must be somewhere the MetaMask extension over here in the extensions. So you can just pin this to your browser, I don't know, extensions area. I don't know how this is called. Extensions tray maybe. And then you have MetaMask over here. It actually pops up like this. It seldom pops up as a full page window. It's a little pop-up over here on the right top. When you click it, then you have all the same features that you saw in the full screen window also over here. Yeah, that's it. I will see you in the next lecture where we are getting some test Ether and we are going to send our first transaction and we are following it on Etherscan. Now that you have MetaMask installed, it's time that we are going to get some ETH and send them around from one account to the other and see if we can track funds. Now, if you have closed the browser in the meantime, make sure that MetaMask is opened and unlocked. So you see kind of like this screen. It doesn't really matter what kind of network you have currently selected. Just make sure it's unlocked now. Now, on our accompanying page to the course, I have a page for getting testnet Ether. And the reason for that is that some of the faucets are not working all of the time. Actually, getting faucets that are working is kind of a little bit of a hassle, but I found a few of them and I try and update the list as we go along. Please feel free to message me if you have a new faucet so I can add it to the list and so on and so forth. So don't give up if it doesn't work on the first try. It's a little bit tricky, this part. Also, if you cannot get any free testnet Ether right now, don't give up. Don't stop the course. You can continue. There's tons of stuff that we're going to do where you don't really need any Ether. You can do this later on, okay? So don't get discouraged by not getting this step done. However, there are a couple of new faucets that I want to highlight. And my current go-to faucet that I kind of really like is the Paradigm faucet. So if you open faucet.paradigm.xyz, then it's actually a faucet. It's a multi-faucet. So it gives you ETH and tokens and whatnot on all of the different networks at the same time. So you don't need to have one dedicated faucet for Robston, one for Coven, one for Rinkeby. These are the test networks. So the only thing that you need to do is you need to sign in with your Twitter account. That's not a paywall, but it's a scam or a spam wall. So you wouldn't believe it. There's actually people who are trying to drain those faucets for, I don't know, for good laugh. I don't know why they're doing that. But in order not to get the faucets drained, they have some sort of a security measurement. So you need to sign in usually with your Google account. You need to post something on your Twitter or whatnot. In this case, with the Paradigm faucet, I'm just going to show you this one. I'm going to sign in with my Twitter. Sign in over here. And the next thing I need to enter is my address. And this address is from my MetaMask account. So as I told you before, you open MetaMask, you click copy, and then you paste it over here. And then what you also want to select here is like drip some ETH on additional networks. And I think those are the networks like the Optimistic Coven, the Polygon Mumbai, the test network. Some additional networks like level 2 solutions. We might gonna work on them later on. So it's good to have some test ETH there as well. And then hit claim. Wait a little bit. And it should have claimed the tokens. Now this one takes a little bit. And the reason for it is that these transactions need to be mined first. So what you want to do now is you click on the little, how's it called? Sandwich menu. Not even a sandwich menu. It's like a free dot menu. And you view account on Etherscan. What will happen is it will open up a new tab. And that tab is showing you on Etherscan, which is a block explorer, which is constantly observing the network because all the information on the blockchain is public. So there is nothing to be hidden. And there's services like block explorers that can observe the blockchain as blocks come in to see if there's any information related to certain accounts, transactions, or tokens or whatnot. And in this case, it's open up our address and telling us if there were any kind of transactions coming in. So let's see if there's anything coming in. Not yet. Let's see if MetaMask has any Ether yet reported to be arrived. So this one might take a little bit. Let's switch over to a different test network. Coven maybe. Let's see if the Coven ETH arrived there already. Yes, they did. Let's open up a view account on Etherscan. And you will see it's opening kind of the same Etherscan with a major difference. The one is called coven.etherscan.io. The other one is called robston.etherscan.io. And you see we have 0 ETH, or maybe we already have some. No, we still have 0 ETH on Robston, but we have 1 ETH on Coven. So what this tells you is that the networks are totally separate, although they work exactly the same way. And sometimes the test networks are being shut down. Sometimes the test networks are being under maintenance. Sometimes they are completely reset and wiped. Sometimes there's new test networks popping up. So test networks, there is no guarantees that anything on the test network will stay there forever. Not like on mainnet Ethereum, where we have a certain high degree of guarantee that information, once it's there, it's going to be preserved for a very long time. Okay, let's one more time reload our Robston. Still not there, but in Coven, we can already do something. So in Coven, we have 1 ETH now. If it doesn't really work with this faucet, then I will just try different ones maybe on Coven, on Gurley, and see if you can get test ETH for one of the networks. Now, let's do the next thing, which is to send some money around and see if we can have a look into the transaction details. For that, we are actually creating a new account in MetaMask, because MetaMask is not just a wallet for one account, it is a wallet for many accounts. So when you hit the little top round button on the top right side, then hit create account and just give it a name like account 2. Then it will take your seed phrase, it will run the seed phrase through a function and create a new account based on the seed phrase. So when you lose your laptop and you still have your seed phrase, you can recreate all of the accounts that you had in MetaMask based on that one seed phrase. So don't lose it and don't give it away. And now we are going to send half an ETH from account 1 to account 2. So I'm going to hit account 1 again. I'm going to say send, transfer between my accounts. I'm going to send it to account 2, and I'm going to send 0.1 ETH to my account 2. Actually, we said half an ETH, so we send 0.5 ETH to my account 2. We still have Coven selected here, so make sure you have the right network selected and hit next. What happens is that it tells us there's an estimated gas fee, and that is the fee that we need to pay on the network to transfer this 0.5 ETH from one account to the other account. Now the question is, who is getting this gas? I'm going to tell you this in a second. Hit confirm. It's pending. Transaction is pending for a little bit. You can also click on it and then say view on Block Explorer. And usually on Coven, it has a very, very low block mining time. So it gets very fast mined. And now it's already a success. So now you have a transaction detail on Etherscan, which has nothing to do with MetaMask, but it's the same information because the ground truth is on the blockchain. Somebody mined the block and it got distributed across the network. And when you hit see more details, then let's go through this quickly together, just that you understand what is going on here. So the first thing which is important is the transaction hash. That one over here is unique for every transaction. And that is a long hash that you can identify the transaction with. There is the status. The status in this case is success. It's either true or false. In this case, it's true. It's mined successfully and it's baked in the blockchain. This is the block number. So in this block, that's currently, like every time a new block is mined, it's get added to the chain. And we have currently on Coven, was it 32,573,094 blocks. And the block confirmations are how many blocks are already added to this block number after we send our transaction and mined it into a block. Well, that's the timestamp. Okay, that's pretty self-explanatory. That is the from address. We send from this address to this address this amount of ETH. And there was a transaction fee. Now the question is, who is paying the transaction fee? Is it going to be deducted from here or is it going to be deducted from here? And it is always going to be deducted from the account that sent the transaction. This is very important to understand. So if you have, let's say, if you want to interact with a smart contract, you also need to send a transaction, and there's also a transaction fee. So what you always need is the native token of the blockchain you are working with. On ETH, on Ethereum, that's ETH or Ether. Okay, and that is also sometimes called the gas token. You will see this sometimes. You need gas token. And that is meant that it's the native currency of the blockchain, because on Polygon, that's Matic. Okay, same thing, same function, different denomination, different value, but it's exactly the same thing, just that here is not saying Ether, it says Matic here. Okay. Good, what's the next thing? That's the gas price. The gas price is in GUI, which you see over here, and we paid 2.35 GUI for this transaction per gas. And the gas usage was 21,000. So that is if you send a transaction without any data, input data is empty, nothing there, then a pure transaction, a pure value transfer will be 21,000. That's the minimum. I will show it to you later in the Ethereum yellow paper. Yeah, and that's pretty much everything that I wanted to talk about. We are going to talk about later about the EIP 1559 type transactions versus the old ones. The nonce is a number that gets incremented every time a transaction is sent. So in this case, we sent the first transaction on this blockchain. That means the nonce is 0. If it's the second transaction, the nonce is going to be 1, and so on. So there's one thing that is important to understand. If you send a transaction with a really low transaction fee, really low gas price actually, and it doesn't get mined, and then you send another one with a really high transaction fee or gas price, then this one will also not get mined because it needs to wait until this one is mined. Okay, so you have a lot of, maybe if you open Etherscan and you look at the transaction details, you see a lot of pending transactions there. And then it will tell you there is a transaction with a lower nonce somewhere recorded, and this transaction with a lower nonce has a really low gas fee, and it actually never gets mined. I have a separate video on updating transactions or canceling pending transactions on my blog, which sometimes maybe you will need this. Okay, that's it. That's all I wanted to talk about. And in the next video, we are going to have a look at behind the scenes, what happens with MetaMask, with Ethereum transactions and hashing again, just to make sure that you fully understand what's going on here before moving on to the smart contracts. Before we continue, let's have a quick look at how MetaMask works behind the scenes, because maybe that's not exactly clear how that magic trickery here actually works, that MetaMask gets access to the blockchain. Does it have its own node, or how does it work? And so what I kind of want to answer in these few slides is, what's that magic box? How does that even work? So there is no magic trickery. There is a service provider called Infura, or at least it was. I'm not sure if they're still with Infura, but I think they're still with Infura. And Infura is running its own blockchain nodes internally in the data centers, and they have convenient access to those blockchain nodes. And the blockchain nodes itself, they are storing, or they are syncing the data with the blockchain and always keeping it up to date. And then you have an RPC method or a REST interface or a WebSockets interface to actually connect to those blockchain nodes, but it's going via Infura. And there's a couple of others that are now popping up every now and then. Alchemy is one, and there are more of them. So running a blockchain node, keeping it in sync is really a pain sometimes, especially if you want to have a high degree of uptime, load balanced for many users. So that one is totally abstracted away. All that MetaMask does, it's conveniently connecting to Infura data centers. I think they're running on AWS, but don't nail me down on that. And then connecting to blockchain nodes there. And Infura is doing the heavy lifting. The next thing we did is we had a look at the faucet. Now it looked a little bit different than this faucet, but from our browser, through some magic trick, we had influenced the blockchain by clicking a button, logging into Twitter in the videos, but maybe you use this faucet. They all look a little bit different. But the point is, somehow, somewhere, this 1 ETH on Kovan or this Robston ETH, or I don't know what kind of faucet you used, at the end went into a MetaMask wallet. How does that work? Is this some kind of magic? No, it's also no magic. There's a browser, there's a normal backend in the background, and then this backend is connecting to blockchain nodes. It can be Infura, it doesn't have to be Infura. It might even run their own blockchain nodes. Who knows? The point is those blockchain nodes are syncing in with the exact same blockchain, and they are having the exact same underlying ground truth of data. So when you send the transaction over here, then it's also getting over here. And at the end, you have basically a public database that is openly available to everyone, and just the different implementations or just the different participants, be it the backend or be it just a browser or be it MetaMask, are getting access to the same kind of data. Then we had a look at Etherscan. We were looking at our transactions both on Robston and Kovan, and we saw on Kovan there's the ETH coming in, but on Robston not. How does that work? Well, exactly the same. Blockchain node behind somewhere writing in the database in Etherscan. So Etherscan is not directly, when you are on the website of Etherscan, you're actually looking into the Etherscan centralized database, but the database gets data from the blockchain and they are running their own blockchain node. So it's the same thing. Blockchain node gets access to the underlying data. And there's tons of other nodes out there. This can be, you might have seen it, go Ethereum, or maybe Parity was it before. Now it's in Ethereum, I think. And there's new ones popping up. So nodes are pieces of software that are implementing the Ethereum protocol. And this Ethereum protocol allows other nodes to sync on the data, on the underlying blockchain data, which is block by block added in small increments to the overall data that is available, but they are chained together with a hash of the previous block into the new block. So you cannot change information anymore. And that's exactly what I want to deep dive into the next lecture, because this is one of the major features of blockchain over a normal database. So what are the key takeaways here? You need a blockchain node to interact with the blockchain, or you use something like Infura, but they are running the blockchain node for you then. So the blockchain node is like the access to the blockchain data. The blockchain is the single source of truth. There is nothing like a sharding at the moment. It might come later with Ethereum 2.0, or maybe we are already there. But right now, there's just a single source of truth, which is the blockchain. And if you are connected to the main network, then you are connected to the Ethereum main blockchain. That's it. There's nothing else. That's it. There we are. And if you want to bring data over to Polygon, that's a different blockchain. But it's going to be then the Polygon blockchain is the single source of truth for the wallet that you're connected with. There are infrastructure providers like Infura or Alchemy or others, and they abstracted running a blockchain away from you, which is very often very convenient. If you're running any kind of mainnet or any kind of networks in production, I can very much recommend you looking into infrastructure providers, unless you want to become one. And it might be worth to invest extra time into trying to get Geth to run stable. Other than that, it's a real hassle, and it's good that they are there. All right, that's it that I wanted to talk about, and I will see you in the next lecture. All right, now it's time to talk about the Ethereum transactions in more detail before moving on to our next smart contract example, because once you understood how transactions internally work, then you already have covered a lot of bases for anything that you do on the Ethereum network with any kind of EVM. Okay, what did we do? We started a MetaMask transaction. So we used MetaMask to actually run a transaction, and the Ethereum transaction internally uses a couple of properties from an object that is being sent through either Web3 or Ethers.js, but usually they are the same properties. So if you have a look at the Web3 documentation, then you will see something like web3.eth.sendTransaction. This is something you will come inevitably across as a web developer. This kind of function is so important that I think it should be on the first page of the Web3 documentation. Now this one gets a transaction object, and this transaction object is, in this case, it's a JavaScript function that you call with a JavaScript object, and this JavaScript object has a from property, which is the address of the sending account. It has a to property, which is the destination address. And you already see here, this is optional. I will tell you in a second why. It has a value. So we send 0.5 ETH, which is 0.5 to the power of, well, times 10 to the power of 18. So it is not 0.5 that we send in there. This is denominated in way. That one is way. Important to understand that. It's always going with the lowest possible denomination, and the lowest one is way. Then we have, well, this one is the old transactions. It's gas and gas price. Now we have gas, we have the base fee, which gets burned. So this doesn't go to miners, and then we have a priority. This one goes to miners. And this one is actually the auction for how fast the transaction is getting baked in a block. Then we have a data field, which is also optional. And then we have a nonce, which is the integer, the amount of transactions that were already sent on the network, which is usually there. And if it's not there, then it's being filled in by the Ethereum, by the send transaction function itself in the background. This is just optional over here for Web3.js. Now, what happens over here if you don't send a to field? I will also show you this in the later lectures about the smart contracts. Then the data field must be populated, because then it is a contract deployment. Okay, data field populated, no to field, contract gets deployed. Okay, one more time, the most important things. From is an account, to is optional, value is an integer in way, and the rest we will talk about later as well. Then we had a look at the Ethereum transaction on Etherscan. So you saw the transaction hash, you saw the status, the block number. It's considerably lower over here because it's an old screenshot. From address, to address, the value, we send 0.5 ETH, not 0.15, and so on. Transaction fee, and so on. So those things should be fairly understandable numbers for an Ethereum developer. So please make sure that you understand what is going on here. This is why I'm highlighting it so often, because when you are digging into failed transactions, and they will happen, especially with smart contracts, then there are a couple of numbers over here that tell you a few things about how the transaction failed and what might have happened. We have the from, we have the to, we have the value, and those are already the most important for just sending transfers. But How does the blockchain know that the transaction is not malicious? What happens there in the background? Or in other words, how does the blockchain know it's allowed to transfer like this amount of ETH, 0.ETH, from my account 1 to my account 2? How does that work? Well, there is the answer. That is, it's creating a signature. And that happens with another function on Web3 that is Web3.eth.sign transaction. And this uses an account in the background or a wallet. And this is where MetaMask comes in. So if you have a look at this raw transaction object over here, then we actually just said, hey, send from this address to this address this amount of way, basically, and the gas price and so on. That's the data we provided. But that is the actual data that is sent to the blockchain. So where is V, R, and S coming from? What is that? And that's the thing that we are going to talk about right now. So when you have a look at this transaction object, then you take it and you need a private key. And the private key is stored in MetaMask without really being visible for you, but it uses then a so-called ECDSA, elliptic curve digital signature algorithm, to create the public key. And from that public key, it creates the Ethereum account. So the Ethereum, that one, the private key, public key thing is actually very, very similar to how SSH connections work. So there's nothing super special there. The only addition here is that the Ethereum account is the Kazak hash of the last 20 bytes of the public key. So it's hashing the public key again, and it's taking the last 20 bytes or last 40 hex characters. So you have an Ethereum account now, you have a public key, you have a private key, and you have a transaction. So somehow you need to combine these two into something that creates a signed transaction. So you have these R, S, me values. That's the thing that you're after, or that's the thing that happens in the background. So once you have this, there is another function on the blockchain that is called EC recover. So elliptic curve recover. And what does it? It takes the transaction details that were provided. It takes the RSV values, and it can recreate the Ethereum account. So that one is never shown to anyone. That one is known, and that's basically the from field. And the EC recover should be the same as the from field from the transaction object. And there you have it. That's how the whole magic works. So the really important part to understand is that you cannot give away your private keys. They have to be kept safe. So no matter who is asking for your private keys, don't give them out. The public key is something you seldom see. You maybe see the public keys when you're working with Go Ethereum. That's the eNode ID, but normally you don't see the public key. What you actually see on Ethereum is the Ethereum account that's publicly known. That's your account, so that everybody knows that. Now there's one more thing, and that's with, especially with MetaMask, what I said before, the seed phrase. The seed phrase is run through a special kind of algorithm and uses an index to create these private keys. So you can have a virtually unlimited number of private keys, and then a virtually unlimited number of public keys, and virtually unlimited number of Ethereum accounts from one seed phrase. So that one is the thing that works in MetaMask behind the scenes. Your 12-word mnemonic, 12-word seed that you hopefully wrote down and kept somewhere safe. And then from this one, the private keys are generated. And when you say in MetaMask, hey, give me a new account, then it will use the seed phrase, increment the account index, create a new private key, create a public key in the background, hash it, take the last 20 bytes, and then have the Ethereum account. This is what happens in the background in the wallet functionality of MetaMask. So keep the private keys safe, but please keep the seed phrase even safer. So never give it out. There is no MetaMask support that will ever ask for your seed phrase. So if there's maybe one takeaway from this course, keep the seed phrase safe. It's meant for recovery. It's meant for your eyes only and nobody else. Now, before we are continuing, I want to give you a quick intro into cryptographic hashing. And it's not that, that I don't believe that you don't know cryptographic hashing. If you know everything about hashing, then feel free to skip this lecture. If you think there might be something that you can still learn, then stay on. So this is just a quick intro. So what is hashing? What happens during hashing? You have some sort of hash function. And in this hash function, you usually send in something and get out something. So let's say in a hash function, it might be an SHA-1, SHA-256, KZAC hash, any other hash function that you come across. MD5 is one, you might have heard of it. You send in something and get out a digest. It's called a digest. So let's say you send in hello Rome and you get out this digest 398 BDAF and so on. And then you change one character, you add an exclamation mark, hello Rome, exclamation mark, and suddenly you get a totally different digest, D2, B3, C5, D9, and so on. So what is happening here? The different parts of a cryptographic hash function are the input, that is something we send into that hash function. Then you have that cryptographic hash function that does something with the input, and it produces a so-called digest. There are 5 properties that every hash function has. So these are the 5 main properties. The one is it's deterministic. So if you send in hello Rome and then send in hello Rome again with the same input, it produces the same hash. It produces the same output no matter how much time passed, no matter on which machine or where you are, it's producing the same output. So it's deterministic. Number 2, it is very quick to compute the hash value of any given message. So it cannot take forever. It's sometimes beneficial to slow that down in case to avoid any brute force attacks, but it's still fast enough that you don't have any measurable lag. So if you interact with a system, then you don't need to wait 5 minutes or 10 hours or 3 days, that you can continue with your work. It's quick to compute the hash value, so the digest for any given message. The thing is, you shouldn't be able to go back. So once you have the digest, it should be infeasible to generate the input from the hashed value, except by trying all the possible messages. So a brute force attack, it should be the only viable way of getting back to the message. And this one should take very long or pretty much forever. And when you change a small thing, like I showed you with the hello Rome and hello Rome exclamation mark, it's just a very tiny change, then the digest, the hash value, should be completely uncorrelated and very different to each other. So you have totally different hash outputs, digests, to very small changes to the input. And the last one, there shouldn't be any collisions. So it should be infeasible to find 2 different messages with the same hash value. So one problem with MD5 is that people found a couple of collisions and found that it's in general not a really good hash algorithm. And SHA-1, I think, has the same problem now. It's better than MD5, but it's still not very good. So SHA-256 is right now the go-to hashing method, and the KZAC hash is also considered safe as far as I know, but I am by all means no cryptographic expert, so do your own due diligence, please. Now, what is important to understand is how hashing of hashes work, because this is what the blockchain is actually building upon. This is what is the power of blockchain. So let me show you what I mean. let's say you hash ABC, and let's say you hash CDE. And for whatever reason, we are doing this with color coding here because it's easier to understand. So if you mix those two together, you're getting a greenish color, right? Blue and yellow is green. And that's what we learned in school, color theory. You mix them together, fine, green. Now you're going to hash 1, 2, 3, and you're mixing this, you're hashing together the green and the red. So basically our hash function for the colors is a pure mixing. Imagine it's like a pot of normal color of paint, and you mix this together. If you mixed it once, you have a hard time to separate them again. So let's say this is our hash function. So if you mix green and orange or yellow together, let's say you get this brownish color. Okay, now you change something. You change the hash from CDE to CDF, and the hash from CDF is not the yellow color anymore, it's the purple. So if you mix blue and purple together, you get a dark purple. But then suddenly the dark purple is not the same as the brownish, as the bluish. And if you mix the dark purple together with the orange, you get an even darker purple. So this is not the brown that we got. So everything down the chain changed by changing one of the input values. And this is what the blockchain is about. With blockchain hashing, it works very, very similar like the thing that I just showed you. You have a block that might be a blue color. You have transactions that might be now in yellow. If you mix them together, you get a green. Okay, now you have a green block. You have transactions again. You mix them together, you get a purple. You have a purple, you have a gray block with transactions. You mix them together, you get a lighter purple. Then you could go ahead and say like, there was a transaction here. Let's change this. Let's make this a different color. Okay, because I'm in control of everything. Okay, if you mix these together, let's make this a different color. And then obviously you have to make this a different color. So everything that came afterwards is then a different color. But because we are in control here, it's on our database maybe, we can do that. It's maybe inconvenient because we have to rewrite a lot of data down the road, but we can do that. Now the trick with blockchains is to take these hashes and to have a copy of these hashes on every blockchain node that is running. So if you want to change one thing over here, you somehow need to convince all of the other blockchain nodes that they should do the same thing, but you cannot because that is not what the Ethereum protocol allows. That would mean to actually do something like a hard fork where you have to have the actual people that run the miners agree to do this change. And this is where the power of decentralization really comes in. And this is why the blockchains are considered so secure. Okay, our key takeaways. Hashing is the mathematical foundation of blockchains. There's no other way to say this. This is the base of why the blocks are chained together, because in every block you get a hash of the previous block. Changing information in your previous block changes all blocks after the block where you change the information. So you cannot just go in and change a block's information without changing all of the other blocks too, because then the hash of that block would be different. You remember, small change in an input, large change in the digest, so that the hash would be totally different. And then that hash is stored in the next block. So if you hash that hash, it's a different hash that you hash, and so on and so forth. So it wouldn't be feasible to do that. And blocks are stored decentralized by being stored on every participating blockchain node in the network, and they are re-evaluating the hashes because it's very quick to do. You can hash a previous block and compare it to the hashed output, but you cannot go back. But it's a very good way to have a checksum. That's it. That's what I wanted to talk about hashing. I hope maybe a few things are more clear. And now let's go on to the next lecture where we are talking about the transaction in more detail. One thing I really quickly want to talk about is how to update or delete transactions, because it seems to be quite confusing for a lot of people how that actually works. In general, a transaction is a gas price auction. The higher the gas price, the more likely it gets mined. The higher the priority fee, the more likely it gets mined. If you send the same transaction nonce with a higher gas fee, then you can update it with a higher gas fee, or you can cancel it if you send no data and the to is the same as the from. So just make sure you send the same transaction nonce, because if you send a different transaction nonce, you add a new transaction to the transaction queue and it doesn't get mined unless the one with the lower nonce gets mined or canceled. Okay, so how does this work in MetaMask? Because that's the easy way, and then I show you the hard way. In MetaMask, if you send a transaction, you will get this little transaction queue over here, and you have conveniently two buttons that says speed up or will send the same transaction with the same nonce if you speed up with more gas, or if you cancel it, it will change the to field to yourself, to the same account, and then with a higher gas, and it will get canceled. So if you click this, then it will pop up this cancel transaction thing, and you just select, I want to have the high fee or the medium fee, and you click save, and it will send a new transaction with the same nonce, and the blockchain will pick it up because it will then cancel out the one with the lower nonce. But let's say you have just MetaMask installed and you have only access to a private key, which you can import into MetaMask, but you don't have this convenient buttons here. So how can you cancel a transaction then? And let me show you a real world example, because that is something that seems to be, I don't know, have gone wrong somewhere. So I just opened up Etherscan and I had a look at the transaction pool at the pending transactions, and I picked out one that is pending for 24 days. That's really long. Pending for 24 days. Why is it pending so long? I mean, what's wrong here? The person already sent 1,005 GUI, which is an insane amount of transaction fee, because there is a pending transaction with a lower account nonce. This transaction can only be executed after confirming of the earlier transaction hash. So then I click the earlier transaction hash. Now guess what is there? A transaction with 5 GUI, and it's been pending for 24 days and 6 hours. So somebody probably got nervous, and somebody probably sent another transaction, learned somewhere. If you send the transaction to yourself, then you will cancel it. Wrong. If you send the transaction to yourself with the same nonce, then you cancel it. So how do you do this with MetaMask? Let me quickly walk you through that. First of all, from the pending transaction, you have to click on See More to actually get to the nonce. Click the nonce over here. That's the important number that you want to have. Obviously, you also need to have access to the private key that is the from address. So if you don't have that, there's nothing you can do. Then you go to your MetaMask, you open the settings, you go to the advanced tab, you scroll down, and there you see customize transaction nonce. Turn this on to change the nonce transaction number on confirmation screens. This is an advanced feature, used cautiously. Okay, we are blockchain developers. We can use this cautiously. Still, please use it cautiously, because things can go wrong. So I take no liability here. Okay, what happens next is you go to the account, you click the send button. Then you send it to yourself if you want to cancel it. Then you enter 0 ETH. 0 ETH. Okay, I'm here in Kovan. If you do this on mainnet, there will be ETH. If you do it on Polygon, there will be Matic. Okay, 0, whatever, to yourself. Hit next. And there you go to the confirmation screen. And when you scroll down, you have the custom nonce. So what you want to enter there is the nonce from the transaction over here. And then you click confirm, and hopefully this transaction gets mined earlier than the previous one. So if you have a really low gas amount, okay, you can speed it up, or you can cancel it altogether. Please make sure, just as a reminder, when you have other transactions pending with a higher nonce, that you cancel them first. So those are all going to get mined once this one is mined. So make sure that you cancel the others first, and so on and so forth. But this is the way how you cancel transactions on Ethereum. It had helped me a lot of times already. And that's it. I will see you in the next lecture. Okay, now that you have some ETH in one of the test networks, and I'm just using Coven over here, then we can go on and deploy a smart contract on a real blockchain. And we're going to do this with Remix and with the Injected Web3 provider. Now let me show you how this works. Let's start with a sample smart contract. I have a new Remix over here. So if you have something in there, fine. If you have nothing in there, also fine. I'm just going to write a sample contract. And it doesn't really matter how this contract looks like. I'm just going to use the same messenger that we did before. And then we are getting one string, public, my string, hello world, and we are going to add a function, update string, new string, public, my string is new string. Okay, let's use this smart contract over here, and we are going to deploy it to Coven or to one of the test networks and see how this works from Remix. Autocompile. I have a new browser over here. This is why I have to reset the settings. Go to the Deploy and Run Transactions tab, and now we are choosing the Injected Web3 provider. What will happen, or what should happen, is that MetaMask pops up and asks us which of the accounts do we want to connect with this website. And if we hit, like if you say the first account and hit next and connect, then the account will pop up over here. The way this works is that MetaMask will inject itself as a Web3 provider into the website, and the website can then, from the window object, can attach itself to the Web3 provider and then get some information from MetaMask with the classical Web3 Web3.js, Web3 JavaScript library functions like web3.eth.getAccounts, which we're going to talk about later. So don't worry about it. What you need to understand is now with Injected Web3, we are going through MetaMask to the blockchain. So Remix, MetaMask, Infura, blockchain. And we see this over here. We are connected to the Coven network, has a network ID of 42. Mainnet has a network ID of 1. Accounts, we only see one suddenly because that's the account that we have connected with Remix. And if we hit deploy, then instead of having a check mark over here directly, we actually need to deploy the smart contracts by confirming a transaction with MetaMask. And if we hit here confirm, then it takes a little bit. It's not instantaneous. We can also view it on Etherscan. It will open up a new window with the Etherscan Coven Block Explorer. So that one might take a while, maybe a few seconds, maybe a minute. And then we have our transaction over here. And if we open it up, we can see all the transaction details that we already saw before. We can also interact with our smart contract here on the left side as usual. So if I hit my string, interestingly, this one is more or less instantaneous. Why is that? Because a call doesn't need to be mined. A call is just a reading operation. It doesn't need mining. It doesn't need to be baked in a block. The information is already there. It's also virtually free, and I don't have to click anything in MetaMask. But if I want to update the string to hello girly maybe, then again I need to send the transaction. The transaction has data. The data looks like this. If it shows us the data, maybe just the hex data. So the data is encoded. It is encoded in a special way. And if we confirm this, then a new transaction is sent on the blockchain. So it's a different transaction, but from the same account. This one is a contract creation. If I hit refresh, then we were sending a new transaction hash to this contract over here, and with this data field, special encoded data field. You see the exact same nonce and everything else. We didn't send any value. Now, while we are talking about the data field later and how the contract addresses are generated later, what I want to talk about in this particular section is how to send Ether from and to a smart contract, because that's one of the backbones of how DeFi and so on works. So in the next lecture, I want to see if we can send transactions with Ether to the smart contract and send it back again. Now let's look at something else which is equally powerful as the rest that you learned already. That is how you can actually transfer Ether to a smart contract and back again. Now over here, we have still our sample contract, and I want to extend it a little bit by letting somebody overwrite that string if we are paying 1 Ether, or maybe 0.1 Ether. Now there's two things that you should know for that. The one is a payable modifier, and the other one is a property of the public message object called value. Let's start with the first one, that is the payable modifier. Let me show you what I mean. I'm here in the deploy and run transactions tab, and I selected the JavaScript VM again because it's much easier to work with. We have our accounts with 100 ETH each, and I'm going to deploy the smart contract. Now over here, when I hit the update string method and I just write something inside, I can hit update string, and then the string will be updated, as we know from before. Now, when we open that transaction details, then you see that our value is 0 way. Now I can also send some Ether or some way or some value to the smart contract with the same transaction. And I can do this by modifying the value field here. And in in MetaMask, you can do this also by adding ETH to a transaction. Let's change this by adding 1 Ether from the dropdown here and send this to the smart contract. How do you send this to the smart contract? You don't really have to do anything. You just have to enter a value here and then send off a transaction. Now, if you're doing that, it will fail. And the reason for that is that we have to mark functions that are meant to receive ETH with a payable modifier. And the payable modifier comes here, public payable, it's defining this function as a function that can receive ETH. And if we are deploying this again, then our button here becomes red, meaning as a UX, simply a UX thing, that this function is meant to receive ETH. Now it doesn't need to receive ETH. You can still write here ASDF and send something without any value. But now you can also send one ETH together with that, and it will still work. Now the value is 10 to the power of 18 way, or 1 ETH, and it's still overriding it. And it's not erroring out. Now we're not doing anything with those ETH. Instead, this 1 ETH is now stuck in the smart contract, and as long as we're not sending it away, it will stay there forever. Now we have locked 1 ETH in our smart contract. How can we get it out again, and what can we do with it? Now the one thing is the message value. If you want to know how much ETH or what kind of value was sent to the smart contract, then you can access the message object, the global message object, and the value property. Let me show you what I mean. Let's say we want to have at least 0.1 ETH Or let's say we have at least one ETH to change this string. So if message value is 1 Ether. Ether is a global unit. It's a globally available unit like Gwei. There's a couple of them, and I will show it to you later in a presentation and also on our website. But for now, you can just safely assume that Ether, that is already defined somewhere as 10 to the power of 18. If that's 1 Ether, then just update the string. So if we are deploying that, deploy the smart contract, write ASDF without anything, it's working, but our string is not updated. And the reason is because we didn't send 1 ETH. If we send now 1 ETH, then our string gets updated to ASDF or any other test string. ASDF might not be the best test value, but I hope it shows you enough about how this thing works. Now, the problem is if we are sending, let's say, 1 Gwei, the transaction still works. We send a value there, but now our smart contract didn't error out or did anything. So we basically just sent 1 Gwei there, but didn't get it back, even though nothing changed here. So let me just hello you, put in 1 Gwei, send this. Doesn't update, but the transaction works. So now we already sent 2 Gwei there, but how can we get it out again? Now this is where we can actually send money or send Ether from the smart contract that is stored inside the smart contract back to an address. And that is not any address, it must also be a payable address. And if we just make something like this, there's 2 options here. Number 1 is we let it error out, but we didn't learn anything about errors yet. So let's just send it back. Else, and you already know this, the message sender, that is the address that sent the transaction in the first place. .transfer message value, and it doesn't like it because it's only available for types address payable, but message sender is just an address. So we have to wrap this in a payable casting modifier. So now we have a payable address over here, and every address, every variable of the type address has a transfer function. And this transfer function will transfer from the smart contract the value to the address. Now the smart contract can take care of his own money. So you can send money to the smart contract. It can be stored there. There is nothing that the logic itself needs to do. It's just natively on the EVM level, and it can send it back. So let's give this a try. So let's say we are deploying the smart contract, but instead of just sending 1 ETH, we are actually sending 5 ETH. And that should have a major impact. Hello global. So the transaction goes through. We send 5 ETH there, but we don't have 5 ETH less. Instead, what happened is we sent the 5 ETH there, and it was immediately in the same transaction sent back without us doing anything. Yeah, just to recap that, we are going to learn more about different structures, how you can let it error out properly, how you can require certain values and so on. But in general, these are the 2 most important global variables that you will probably encounter during your Ethereum blockchain developer career. That is message sender, the address that sent the transaction, and message value, the amount of ETH that was sent within the transaction to the smart contract. Now the payable modifier is here to make a function allowed to receive ETH. Now what happens if you're actually sending ETH to the smart contract without calling any function? Basically just making a transfer. That's where the fallback functions come in, and that's what we're doing in the next video. Now, there are two more functions that I want to talk about before wrapping it up, and that are the fallback function and the receive function, because they are equally important for finishing our project. Now, let me show you an example by just creating a new smart contract. Let's call this sample fallback sol, and then just add in the pragma and SPDX license identifier, and call this contract sample fallback. Okay, as we heard before, we can send Ether with message value. So why don't we just create an unsigned integer public last value send and no other function. You already know that if you have a function with a payable modifier, then you can send ETH there. But what if there is no function at all? What happens if you're going to send ETH there? So let's deploy this. And let's try to send one way to the smart contract by doing a low-level interaction. And by doing a low-level interaction, that will basically just send one single transfer, one single transaction. And the data field is going to be this one, but we're going to leave it empty. There is not going to be any data. So we are basically just sending a transaction from our account with one way to the smart contract address with no data. So if we transact, in order to receive Ether transfer to the contract, in order to receive Ether transfer, the contract should have either receive or payable fallback function. What that means is by default, the smart contract cannot receive anything. It just errors out. There's only one chance the smart contract can receive something, and that is by letting another smart contract self-destruct with this smart contract's address as a beneficiary. But we are not there yet. So let's just say in 99.9% of the cases, you cannot just send Ether to a smart contract. You need to have one of the two specific functions. And there is a receive function and a fallback function. Now let's go to the receive function first. The receive function is a function that can receive Ether, and it needs to be defined as receive external payable. And the problem with the receive function is it can only rely on 2,300 gas, which is really low. It's called the so-called gas stipend, because if somebody is sending a transaction without any data or anything to the smart contract, especially if another contract is interacting with this contract and just sending, an ETH or some value, then it will not have enough gas to actually do something meaningful. So normally you cannot even write a function or call any other function or write any storage variable. We are still going to do that because we are providing here enough gas. So we are sending enough gas to the smart contract with our transaction, but you cannot rely on it. So you should never rely on more than 2,300 gas. So in this case, we are just going to say last value sent is message value. But in order to also understand where this came from, we are going to introduce another variable, and we call this string public last function called. And we set the last function called to receive. Okay, let's just remove all of that. Hit the deploy. Nope. Hit the deploy button. Also, if the constructor is not payable, then you cannot send the value together with the deployment. So be careful with that. You just saw it erroring out in the background. The constructor is not payable. There is no constructor, so it's not payable. It's not payable by default. So you should have 0 value when you want to deploy a smart contract without a constructor. Okay, going back there, we can now send away to our smart contract because we have a receive function. So let's just send it without any data. Hit transact. Oh, our function goes through. What is the last function called? It's receive. The last value, 1. We send one way. Perfect. What if we send actually some call data there? So let's just again add one way, and let's just 0x ABCD. What will happen? Oh, a fallback function is not defined. So what did we learn? We learned if there is no data, if there is just a value transfer without any kind of data that is sent to the smart contract, then it will automatically hit the receive function. Otherwise, if there's a call data, it will need a fallback function. So the way this works is by defining a fallback external. So the payable here is optional. Why is it optional? Now, if you want to have a function that gets called in case no other function matches the data encoded signature, function signature, and I will tell you in a second how that works, then the fallback function will be called. If you want that fallback function to also be able to receive any value, then you add the payable modifier. So in this case, let's run with this one. Last value sent is message sender, and last function called is fallback. Also over here, be careful because it cannot get more than value. Obviously, it cannot get more than 2,300 gas usually, or you shouldn't rely on more than 2,300 gas. So writing to any storage variables is a bad idea. What you can do is send an event or something. Now let's redeploy this. Again, 0. Deploy this, and then send one way to our smart contract without anything. Let's receive, and now let's add some data and add two-way over here. Transact, now it works. And the last function called is fallback, and the last value sent is 2. We send two-way. Now the question is, what if we have no receive function, but we have a fallback function and we don't send any data? Now the way this works, let's just quickly deploy this. Add one way, no data, transact. Now it calls automatically the fallback function. So if you have a fallback function that is payable but no receive function, then no matter if there is a call data or there's a data sent, it will call the fallback function. If you have both, then there is no data, it will call the receive function. If there is data, it will call the fallback function. If you have no fallback function but a receive function, then it will be only possible to send ETH to the smart contract without any call data. Now, this is where the signature, the function signatures comes in. And I will also tell you more about this in the next lecture, but let's just roll with this. Now let's add another variable called uint public my uint, and then add a function set my uint my new uint, and we are going to set the my uint to my new uint. Okay, let's just remove all of this, deploy the smart contract, and let's call this with 1. And let's open this. Have a look at the input data. I'm going to copy this over here, and I'm going to just paste it that you see how this looks like. You see the input data over here? That is specially coded to make the EVM understand what you actually want to do. Now the first 4 bytes, that one is the 0x to show that it's a hex value. The first 4 bytes, 1, 2, 3, 4. So the first 8 hex characters are the function signature. And this is how internally the EVM understands what kind of function it should call. That is the identifier. And the way you get to that is by making the Kesa cache of the function signature. The function signature over here is simply set my uint, the name, plus the type that it actually expects, uint 256. You know, that's an alias for uint 256. And if you take the Kesa cache of that, free utils SHA free. Scroll down. Where is it? Then you get this large string. And if you have a look at the first 4 bytes, then that is the function identifier. So the rest, it will be thrown away. This is how internally the EVM knows what kind of function it should call. Now, if you take the raw data over here, let's just comment this out. If you take the raw data field that we set before and just insert it into call data and hit transact, then the function will work perfectly, because it will call the same function. It will call the, where is it? The setMyUint function. And Remix even knows that, because it can decode or it can map this 4-byte or 8 hex characters function identifier on this function signature to the actual function. Now you can also modify this this data, because it's just an unsigned integer 256 with zeros padded to the actual length of the variable. So if you just hit here 2 and you ask what is my uint now, it's going to be 2. So this is how this works. In the fallback function comes in if it doesn't know where to go. So let's say we have this one as a function identifier. There is no such function, so it's going to call the callback function. This is where the fallback function will come in. So I hope this was helpful, and let's wrap it up, and then let's get our project going, because that's going to be very exciting now. All right, then let's wrap up what we learned in this section, and a little bit also from the previous section, because sometimes it's just good to get the theoretical background as well. And I'll try to make this short and sweet so you can continue with the actual project. Let's talk about functions, visibility, what we haven't really talked about, constructor and the fallback function, as well as address and payable stuff. So the first one that I just want to recap is their setter and getter functions. Writing transactions means it needs an actual transaction that is mined, and a reading transaction is actually called a call, and that is only against your local blockchain node. Remember that everyone in the network has a copy of the blockchain, so you don't need to send a transaction to somebody else. You can just read it from your local cache, basically. And if you don't need to change anything, you don't need to inform anybody about that you were reading something. And reading is virtually free. It still needs gas, but you don't really pay it. You just pay it for yourself, so you don't need to pay any ETH. And yeah, that's it. So writing and reading transactions. Then there are view and pure functions. In earlier versions of Solidity, it was called a constant function. That is now view and pure for a while. So I don't think that anybody still remembers constant functions. That was, I think, from Solidity 4 or something. The view function reads from state and from other view functions. A pure function cannot read or modify the state at all, and it can only read like the variables that you gave it as a parameter or other pure functions. So it doesn't even touch the state. It has a couple of internal reasons from the EVM, which I'm not touching on yet, which we are going to dig into a little bit later. Now, the function visibility is something that we have not discussed yet. I just want to quickly mention it. There's public functions, which we saw already. We use them, public functions. You can call them from outside. There's also private functions, which can only be called from the contract itself. So you can have a couple of functions. If you want to structure your code differently, you can have functions that cannot be called from outside, that can only be called from inside. And you will love these functions once you hit an exception called stack too deep. Now, if you hit stack too deep, remember there's also private functions where you can get logic from a function which became fairly big. You can structure differently into other functions. It's not important right now, and I'm going to show you once we hit a stack too deep problem how we can overcome this. There's external functions, which can only be called from other contracts or called externally with an actual transaction. They cannot be called from within the smart contract. And there's internal functions that can only be called from the contract, or which we will see later, also from derived contracts. So when we talk about inheritance, then I will show you what internal functions are. They can't be invoked by a transaction from an account. There's a constructor, starts a function with the name constructor. It's only called during deployment, and it can't be called afterwards. And it is now it's public. It was public or internal before. Now it's simply public. It doesn't need a visibility specifier at all. Then we talked about the fallback function. The fallback function is a function with the name fallback external and maybe payable to receive ETH or to receive call data that cannot be matched to any other function signature. And a function with the name receive external payable is there to receive a value without call data. And if you have both, then fallback will be called with call data and receive will be called without call data. This one can only be external, and the fallback function, the payable modifier, is optional. So if you don't have a payable modifier, then you're actually just catching calls to the smart contract that were meant against a different function signature that cannot be found. Contracts receiving values without a fallback function and without a proper function call to a function that is payable will throw an exception. The thing is, you cannot completely avoid receiving Ether. So there is a minor reward, which we haven't talked about, but definitely self-destruct. You can forcefully credit Ether to a smart contract by self-destructing a smart contract, which had a balance or a value stored on the address. And then you can use the beneficiary as this address over here, this beneficiary. You can set the smart contract that is actually not allowed to receive any Ether, but it will still receive Ether. That's a design from the EVM, which cannot be circumvented. So be careful if you have some kind of internal bookkeeping that relies on the balance of the address of the smart contract and how many ETH were sent there through legitimate functions. If that doesn't add up, that can happen, that you can forcefully send Ether to there. Why I am talking so much about it, because there was actually a bug that cost someone quite a lot of money because the internal functions then blocked any kind of withdrawal because the internal bookkeeping did not add up anymore. Also, when you send or when you use the fallback function or the receive function, then you can only rely on 2300 gas. That happens if you send to the contract with the transfer function something. It doesn't matter if it's 1 ETH or less or more. Then this will only send 2300 gas along. This is called the gas stipend. That's the 2300 gas. One thing that we haven't really talked about yet is the exceptions with require and assert. So that are exceptions. They became a fairly large topic because now you can have some sort of rudimentary try catch, which you couldn't do before. And you can even have named exceptions now, which you also couldn't do before. So I want to dedicate a lecture to that. But essentially this one, this require statement over here will error out, will make the complete transaction, reverse the complete transaction if this statement doesn't evaluate or evaluates to false. So if the message data, a property that we haven't really talked about yet, but this is the call data that was sent along, like value, like message sender, that's the data that was sent along, is not 0, then you can like forcefully throw an exception there so that the transaction will revert. Then we quickly talked about message value and address. The global message object contains not only a sender, but also a value property, and that is in way. And the question is how much way was sent during this call. And that means, again, like before we had it with message sender, if an address A sends to a contract 1 ETH, and that contract 1 sets to a contract 2, I don't know, 0.5 ETH. So if this one sends 0.5 ETH here, then over here, the message value will be 0.5 ETH. And if this one sends over here 1 ETH, sorry, my handwriting, then over here the message value will be 1 ETH. So it depends on where you are calling message value, from which point of view. So this point of view is that this contract initiated this kind of call, and over here it will be then 0.5 ETH, and this contract sees this address here as the initiator, and this one will be 1 ETH. Very important to understand is every kind of address type variable, so any kind of variable that is of the type address, will have a balance. So you can always call in any smart contract for any address, you can read the balance. And why is that? Because all of the information on the blockchain is publicly available. An address type can be payable, so you actually would have to define this as a payable modifier on the actual variable type. Payable addresses can receive a value, so that would be if this would be an address payable variable named x, then you can do x.transfer, and that one is in way. It's not an ETH. And the contract itself can, of course, also have a balance. And the question is, how do you get the contract address? That is by calling address this. That would be the address of the contract where it actually sits. And then you can call the balance and get the balance in way. All right, that's it, what I wanted to talk about. What are the key takeaways here? Constructor is called only once and once only, that is during deployment. The fallback function is here to receive Ether as a simple transaction, but beware of the gas limit. The getter functions are usually view functions, so you can safely usually assume that it's a view function. View and pure is only against your local blockchain node, doesn't need mining, doesn't really cost anything, and there is a payable address, and addresses have a balance. All right. I will see you in the next lecture. Now let's put everything that we learned into practice by writing a wallet. Smart contract. And what it essentially does is when we have our account, then we want to be able to send 1 ETH to the smart contract, and we want to be able to see the balance. And we want to be able to withdraw, so that one would be deposit. And that one to withdraw from the smart contract, and then also withdraw to a specific address other than our account over here. And all of that is going to be in ETH, so we are going to do this in ETH and not in any kind of tokens. So tokens come later. Yeah, what you need to do is some sort of deposit functionality, some sort of function to see how much balance is actually stored in the smart contract, a withdraw, let's say withdraw all function, and a withdraw to address function. If you want to try this yourself, then I would say you pause the video now and give it a try. Otherwise, I will start now with the sample solution. One last thing, we are going to test everything in Remix, and then we are going to deploy it to Kovan and see if that works there as well. And maybe I'm also leaving 1 ETH inside for the first lucky person who can withdraw that then from the Kovan smart contract, just to leave a little bit of a bounty. And if you're not the lucky one, then you can at least see who was the lucky one by looking at the Block Explorer. Great, let's get started. I'm going into the contracts folder. I'm creating a new smart contract called Send Money Example Solidity. And then we are going to take our SPDX license identifier and our pragma line, and I'm calling that send withdraw money. Now the first one is deposit, right? So we are going to write a function deposit. Why is this not intended the right way? And we don't even need any kind of argument here because our argument will be in the public message object by looking at the value. And let's just also store this somewhere in a balance received variable, just for the fun of it, public. So we make actually use of that. Balance received is incremented by the message value. And we don't need to take care of any kind of overflow or underflow here because we're using a new Solidity version. Then we also want to get the balance, get contract balance, public, that's a view function, and that one returns us an unsigned integer. And you can choose now normally between the balance received or the balance of the address of the smart contract. If you think back what I told you before, you can forcefully send money to a smart contract without the smart contract actually wanting it. So in case that happens, our balance received will be off. So we are going to use directly the address of the smart contract and then the balance of it. And we are going to return this. And then we also need a withdraw all function withdraw all. And instead of directly sending it to the message sender, let's split that up just to see how that actually works. We have address payable 2 is payable message sender, and then we send to transfer get contract balance. So we get the whole contract balance and we send it to the person who calls this smart contract. Yeah, whoever calls this function withdraw all can get all of the ETH. There is no sort of precautions for owner like we had in the previous project. Let's just roll with it so we understand how the money is managed between the smart contract and the addresses. And then we also have a function withdraw to address, and that gets an address payable to, it's a public function. It's not a readable function. It's not a view function because it actually modifies something if you transfer ETH, and then to dot transfer get contract balance. Now this is our send money example. Let's give this a try over here before we are actually deploying it. So we can deposit, let's see, the balance currently is 0. The contract balance is 0. If we are sending 1 ETH over there, then the balance received is 1 ETH. The contract balance is 1 ETH. And now let's withdraw this to a different account over here. Copy the account over here. Let's have a look at the balance over here. Now we have 101 Ether. We had only 100 before. And let's send another Ether to the deposit and just go to the second account and hit withdraw all. And let's have a look. It's almost 101. What we didn't, where we don't have 101 Ether, but a little bit less, is the gas amount that we needed to pay for this transaction. Now, the last step is to use the injected Web3 provider with our Koban network. And we are going to deploy the smart contract over here in Koban. And if you have a different ETH on a different test network, then feel free to use that one. Just get a better feeling of how long that takes to actually deploy the smart contract. So I just hit the deploy button and it should be there now. It's indexing. And where's my transaction? Come on, Etherscan. Show me the transaction. Remix says it's already there. Yeah, maybe it just takes a little bit. Anyway, our smart contract is over here at this address. So if you go to Etherscan and you type in this contract address, then you see that I created this contract. And if you go to the contracts tab, you just see bytecode. And in the next video, I will show you how you can actually publish the bytecode and why it's so important to do an ABI array, but we are not quite there yet. Right now, we just want to deposit. What do we deposit? Let's deposit 1,000 Gwei to the smart contract. And you can see over here that we are now also sending, we sent the estimated gas fee, but we are also sending an amount on top of the gas fee. So if we confirm this one, then you should see a new transaction popping up, hopefully soon. Come on, Etherscan, you can do better. Here's my contract creation. Where is my transaction? There it is. I called deposit. And Etherscan knows deposit, the name or the function signature, because it knows the method ID. It can already remap it because so many other smart contracts are using deposit. If I would name this deposit ETH, it wouldn't know where this belongs to, and it would just show the raw input data. All right, that's it. And I will wrap it up in the next lecture, and then we are going to talk about some more advanced stuff that is going to happen in the next section. Before we continue, let me quickly summarize what we did in this section. First, we installed MetaMask, a browser wallet. When you connect MetaMask to a website, then it will inject itself to the website as a Web3 provider. Through that, and further down the road through JavaScript libraries like Web3.js or Ethers.js, a website can communicate with the selected network. We're going through different networks in depth later. For now, it's enough to know that these work a little bit like different databases. And test networks are like a dev database. We got some free Ether for one of the test networks, and you should be able to dig into real-world transactions by now. Now it's time to expand our knowledge a bit and build a full wallet solution around our knowledge. Don't forget, you can add the source code on your GitHub. If you post it on social media, why not tag me so I can give it a thumbs up? That's all for now. I'll see you in the next section. Did you get pocket money as a kid? Maybe your parents tried to teach you an important lesson on how to spend money wisely. Or maybe you have a business credit card and you can have a certain amount of expenses per day or per month. In this project, we are going to have a look at a smart contract wallet. A smart contract that can manage its own funds and limit how much can be spent. In this section, you will learn about some more advanced data structures like mappings and structs. We will also talk about exceptions and exception handling in Solidity. At the end of this section, you will be able to read about 95% of all contracts out there, and you will be able to write some very advanced code. Of course, we'll put everything to good use and write the wallet at the end of the section. So without anything further, let's jump right into it and learn about mappings first. Now let's get started with something that many of you will find extremely useful, and it's one of the biggest things that you're still gonna learn in Solidity besides the stuff that we already learned, and that is mappings and structs. Now I want to start with mappings, and the reason is because many people will start now to create arrays, and arrays are not exactly the best thing to store a lot of data in Solidity. And there's actually a better way, and that is mappings, and they very much work like hash maps. Now, before talking too much, let me give you an example of how that actually looks like. I'm going to create a new smart contract over here. Just select the folder, either click the little icon or new file, and then just call this sample mapping sol. Now, of course, we can bring over our SPDX license identifier and also the pragma line. It doesn't really matter. It can be 814, 815, doesn't matter. Contract example mapping. Okay. Now, how's a mapping working? Mapping is mapping a key type to a value type. Let me give you an example with a Boolean. So we can map maybe an unsigned integer to a Boolean, make this public and just call this my mapping. And then maybe just set something, like we set a value to true. The rest of the values are false. Let me show you how that works. We just write a getter function, setter function, maybe set value, some index, and then we set my mapping for this index to true. All right, everything is compiled. If it isn't, then obviously check the checkbox auto compile here. Let me make this a little bit bigger. Why is this so small again? Okay, and let's go over to the deploy and run transactions tab and deploy the smart contract. What we have here in our contract instance is two functions, one set value and one my mapping. Now, my mapping has already an input field here. So it expects a parameter, and the parameter it expects is the key, an unsigned integer, and it gives you back a Boolean value. Now for the Boolean, for the key 0, it's going to be false. For the key 1, it's going to be false. This works very much like an array, just with all possible unsigned integer values already initialized with the default value of the Boolean. Now, if you're going to set one of the values, let's say we set the key 2 to true, then number 1 will still be false, but 2 will be now true. So this is how you can work with mappings and store basically a lot of values inside a variable in Solidity. Let's create another one. Let's create an address to Boolean mapping. Address type to bool type public my address mapping. And this can also be, for example, maybe a whitelist. So where you whitelist certain addresses that they're allowed to do something, maybe depositing or withdrawing, or maybe the bool type is not maybe you don't map address to bool, maybe you map address to a certain withdrawal amount that people were withdrawing already. So let's just write a setter function for this as well. Function set my address to true and let's set our address to true. That is stored in message sender. I think you remember that. My address mapping, message sender is true. So now when we are calling this function, right now for our address, if you copy my address over here into my address mapping, it says false. But if I hit set my address to true, then automatically it will take the message sender, which is my address, and then we'll set the Boolean to true. So now I click that one, and now I click the other one. Now it's true. It's still false for the other addresses. So if I go on to the other address, don't really have to go back. If I copy that address over here, it's false. So no matter, I'm still with my first address here. No matter how many times I call set my address, it will always be false for the other one, unless the other address is going to call set my address to true, and then it's going to be true for that address as well. Now, obviously, there is the functions missing to actually go back to false and so on. So what is important to understand is that when you want to access a mapping, then you have kind of the same syntax like you would access arrays, just that all possible combinations of the key type are already initialized with the default value of the value type. Also, the public keyword here will create a getter function again in Solidity. That's like the normal thing that we saw before with normal variables. So with one difference, it will automatically create a parameter for the key type over here. So you're actually fetching one unsigned integer index or key, and you get back a Boolean for that key. So it's basically the same. If I want to write, if I want to create a getter function for the my mapping, what internally happens, and I'm going to write this, but it gives an error because the function cannot be the same name as a variable. But what internally happens is it creates a function with the name my mapping, and this one will have an unsigned integer key or something, and it will be public. A view function returns a Boolean, and this returns my mapping key. This happens internally with the public visibility specifier over here for the variable. Okay, let's remove this again. Now, one last concept that I want to show you is mappings of mappings. Now, you are not limited to value types, to normal simple data types over here. You can actually create another mapping that maps to something else. So for example, if I create a mapping from uint to another mapping, uint to bool, then I have something like a uint bool mapping. Let's make this public. And if I want to write this value over here, then I would write a function set uint bool mapping, and then I have uint key one or index one, uint key 2, and a bool for the value. Public, and then we can write to uint bool mapping, and then write key 1, key 2 is the value. So this would be how you would access those variables inside a mapping of a mapping. And you can do that, like you can nest a lot of mappings together. What I've seen in practice is usually 2 mappings for something like balances in token contracts or allowances. Yeah, it's pretty much that's as complex as it gets in the real world out there. Maybe votings for governance contracts and so on. This is where stuff like this is usually used. But still, before you actually now go out and write mappings of mappings, stay tuned for one of the next lectures where we talk about structs, because that can come in a lot more handy before you create a lot of mappings. That's actually where it gets really powerful. So before we go to structs, I want to go through one more example of mappings, and that comes in the next lecture. Now that you know the basics of mappings, I want to get started with an example of mappings where it will all make sense to you. And that is how you can make sure that withdrawing money from a smart contract is actually money that somebody else put in there. And many people can actually put money in the smart contract. So let's get started with an example before I'm talking too much. And let's just say this is example mapping to Solidity. Now we can copy over our SPDX license identifier and everything, and just call this example mapping withdrawals. Now let me write a simple smart contract and then secure it. The simple smart contract should look very familiar from the contracts that we had before. We have a contract where you can deposit money and then withdraw the money again. So let's just write a function send money, and that is a public payable. Doesn't do anything yet. Then a function get balance, public new returns an unsigned integer, and that returns this smart contract's address balance. And then we have a function withdraw all money, and then we just withdraw this to an address. And to.transfer or get balance. Great. If we run this smart contract, let's deploy this, and we put in, let's say, 1 ETH into the smart contract. Then the get balance is 1 ETH, and then we can withdraw the balance, well, from somebody else to somebody else. So now I did deposit with this account, and then I'm switching over to the other one, copy the address, but I don't switch back. And that's the important part. So I can just, as the second one, withdraw all the money to myself. Balance is gone, but now I have almost 1 ETH more minus the gas cost. And that is the exact problem where we would need some sort of extra data structure to make sure that this doesn't happen, and so on and so forth. But the question is, can we make this kind of like inherently secure by tracking who deposited what and just let people withdraw as much as they deposited before? And there's actually a way, and there's an elegant way instead of dozens of different variables. And the elegant way is to use a mapping that tracks the balances received. So let's improve this smart contract. Let's say we have a mapping that maps addresses to unsigned integers, and that is maybe called balance received. And then we need to track this somehow. Well, in send money, we are going to increase the balance received from message sender gets incremented by the Msg.value. So the plus equals means balance received message sender is balance received message sender plus message value. So whatever is in there already stored gets incremented by message value. If you've never seen that before, that is something that you will see quite a bit and is basics. Now in withdraw all money, instead of letting the user withdraw the amount of money that is in total in the smart contract, we will just let him withdraw the amount of money that was sent by this user to send money. So what he can withdraw
is what is basically in here. So, and it's not quite there yet. Let me just write the more or less pseudocode in there. So what he can withdraw is what is stored in balance received message sender. But obviously we also need to reduce this. And we could do this over here. We could easily say like transfer to that address the balance received, and then balance received dot message dot sender equals 0. That would be a valid thing, but here we would open it up to a sort of re-entrancy attack, and it's not really possible with the transfer function because it only gives you a minimum amount of gas. But in general, this is called the checks, effects, interactions pattern. So what you should do, what you should not do is what is here. And what you should do is first check if the user has enough balance. But we don't really do that yet because we will see in the next few lectures about exceptions and require statements and so on, how this works. And we can improve it there. But then we are going to apply the effect and then have the interaction to an external address. So instead of first sending out and then applying the 0, we first have to apply the 0 and then send it out, because this address over here could call back into that smart contract. And if it is possible to do that, then it could actually withdraw again before it gets set to 0. And that is the problem with the re-entrancy attacks that happened on the DAO, for example, which was one of the first voting and crowdfunding smart contracts that got hacked, that led to the split between Ethereum and Ethereum Classic. Now, a small thing can have a huge impact. So how are we going to do that? First of all, we are going to cache our value, balance to send out is balance received message sender. Then we set balance received message sender to 0. And then we are going to send out the balance to send out. And this way, even if this smart contract or whatever is running here would be, for whatever reason, be able to call back this function again, at that point, the balance received would already be 0. Now, the good thing is it's inherently secure. So you cannot withdraw more money from this smart contract than you actually initially put in. So let's give this a try. Let me just close this over here. We are going to deploy this smart contract with the first address in our address list. And I'm going to send 1 ETH to the smart contract. And now in the smart contract is 1 ETH. And I'm going to the second address and I'm going to deploy, I'm going to get 1 ETH into the smart contract. Now we have 2 ETH in the smart contract. The thing is, our address over here, this one, if I paste the address into the parameter for balance received, then it only sent 1 ETH. So even if I say I want to withdraw all the money to myself, all I can do is withdraw the money that I sent to the smart contract back to somebody else. So I kind of like put it in escrow. I have no access to the other funds that the other person sent. So even if both or all parties are having access to the same smart contract and can run the same functions, inherently by the data structure used by the smart contract, only one can interact with the data it has actually access to. Even though you can track and see everything, you cannot modify it. And that is very important to understand this difference, especially if you want to build something like a wallet, an escrow smart contract, a voting smart contract, or any kind of smart contract where more than one party can interact with each other, like a token. A token is nothing else than increasing balance on the one side and decreasing it on the other side. That is how an ERC20 token works, and you will see this later on. Now, enough of that, and we are going on with structs, which are bringing a little bit more complexity into the game, but making it much nicer to work with smart contracts with a lot of data.
Now that you know a little bit more about mappings, I want to touch on a different kind of data structure, and that is structs. And there might be a confusion how to use them and where to use them. And I especially want to compare them in this lecture against contract instances or objects of contracts instead of just using structs, and touch a little bit more about when to use what and the gas usage and so on. So I want to get started with a sample smart contract that uses a subcontract as an object to store some values. And let me give you an example. Let's get started with, I don't know, an example struct solidity file. And then let's bring over the SPDX license identifier and the pragma line as usual, and call this. So I'm going to use two contracts here now, and I know I'm going to go ahead a little bit because we haven't really talked about contract interactions and so on in depth, but just follow along. I think it will be pretty clear what is going on here. So I will have a contract that acts like a wallet, and every time you receive something, I'm going to, well, in this case, I'm just going to store like a subcontract that holds the values for the actual payment received, how you would do it normally in an object-oriented programming language with classes and like with classes to have a logical group of variables. So I have a contract wallet, for example, and that has a function, I don't know, pay contract, that is public payable, just an example. And over here, I want to store the from whom is it, like who sent this and how much. So I could do here address sender and Uint.value sent, and then I could do over here sender is message sender and value sent is message value. Now, before even going into how we can map this and so on, is there a way to logically group this together into something like a payment received? And yes, there is. There's two ways to do that. One is with structs, and the other one is with subcontracts, or, well, contracts that hold this logical group of variables. Let me give you an example with the contracts first, and then simplify it with the structs. So we have a second contract that we call maybe payment received. And over here, we actually say address, I don't know, public from, and a Uint public amount. And then we maybe have a constructor that stores these variables, address from Uint amount, and then the from is the from, and the amount is the amount. And then we somehow need to reference that over here. So we could do over here payment received, public payment, and over here we just say payment is new payment received, and then the message sender and the message value. So if you're going to compile this, it compiles just fine. And if you're going to deploy it, be careful over here that you deploy the wallet this time. If you deploy the wallet, nope, there's something in there which shouldn't be in there. So if we deploy the wallet and we say pay the contract with one expensive way, then it will create a new smart contract payment received for us, and it will store the values of the message sender and the message value into this smart contract. So we are going to call this function, and this one creates a new payment received smart contract, and it will input in the constructor the from and the value. So if we are getting the payment over here, the getter function, the question is what is going to be returned. And over here, it is going to be returned the address. And with this address, we can then instruct Remix or whatever kind of software we are using to actually fetch at this address from the payment received contract the actual variables. Let me show you how that works. So now we click on payment and we see a new smart contract was created at this address. So we can copy this address, paste it over here, and say our payment received smart contract, it's a different one now, is living on this address. So if we say add address, then we get a new interface that interacts with this smart contract at this address. And then we can say the amount. Yes, we send one way, and we send it from this message sender over here. So it's going to be the same addresses over here. So AB 8 and so on. So the question is, what are we gonna, can we simplify that? Or is there a benefit in doing it this way versus a simplified way? Now, before I'm answering this question, let me show you with a different smart contract how this can be simplified with structs. So I'm going to create directly underneath here a new contract, and I call this simply wallet2. And I'm having the same function pay contract, public payable. But in this case, I do not want to create a subcontract. I will create a struct over here. And the struct starts with the keyword struct, and it's a logical grouping of variables. And the logical grouping is inside curly brackets, but the struct also gets a name. So why don't we just call this payment received struct? So we don't have a naming confusion over here. And then we have an address from, and you finish it with semicolons. So it's not a comma, it's a semicolon, and a uint amount. And this one becomes a new data type. So now we can give a variable the data type payment received struct. So payment received struct, public payment. So the variable payment is now of the type payment received struct. And the question is, how can you access these variables inside the struct now? Now there's two ways. The easier one is payment received struct. Oh. You see, I don't have a new keyword here. So I'm just writing payment received struct, and then very much like with the constructor in the smart contract, message sender, message value. So it's in order of the variables that are defined in the struct. Or, well, let's give this a try before we're continuing. Over here, wallet2, deploy. And what happens if we are calling this public variable now? Let's send one way over here, pay contract. And then over here, we're getting the variables directly returned from our getter function. So we don't get an address because we didn't create a new smart contract. It is going to be directly the variables that are defined in the struct. Very convenient. Now, how do you access these values? I could also do payment.from is message sender, and payment.amount is message value. It is exactly the same thing as above, just, well, more clearly defined. It's up to your flavor what you're going to use in your smart contracts. I think sometimes this is more readable, but that's my personal opinion and it shouldn't influence what you're doing. So the question is, when you use what here? So what is better, a Solidity struct or a child smart contract? And I have to say, most of the time, it is better to save gas with structs. And gas costs are pretty high. And if we are comparing the gas costs over here, let me make this a little bit bigger. Where do we have that? Wallet.pay contract needs around 221,000 gas. So if you multiply that with, let's say, 100 GUI, and say the network is congested and you have to pay 100 GUI times 221,000 gas, it can become fairly expensive if ETH hits a certain price. Now, on the other hand, with our Wallet2Pay contract, it only needs 75,000 gas. That's quite a gas usage reduction here. The other reason why you should use structs is because to save complexity. Now with a child smart contract, if you want to update a variable over here, you kind of need to write setter functions, and then you need to take care of access lists, access rights, who is allowed to override what, and it can become fairly complex rather quickly. And then it's also a dry, do not repeat yourself, and KISS, keep it simple, stupid principle. Contracts are code, and every time you deploy code, it's possible to introduce bugs and so on. So the simpler you can keep it, the better it is, the lower the attack vector probably is going to be with structs. Now, there's also good reasons to use child smart contracts, and that is since whatever information you want to put in the smart contract is then living there, you can have arbitrary complexity in there. So you can have you can fill in a smart contract with certain variables, and then do whatever you want with that smart contract. You can split up the code into subcontracts, but be aware that of the additional gas costs, so that you're not running out of the block gas limit. Now, obviously, all of this makes little sense to just store one variable. And in the next lecture, I want to have a look at how we can combine structs with mappings. All right, so far we've relied on simple data types like addresses, uints, or booleans. In the previous lecture, we also grouped them together into structs, and I showed you the difference between using smart contracts or child smart contracts as data stores versus structs as data stores. But what if that's not enough and you need to track them in maybe an array-like data structure? Maybe you want to track the timestamp when a deposit happened. You want to track every single deposit from every user. You want to track how many deposits happened and many more details. Just as a rule of thumb, before we even continue with that, it is always better to just store the most necessary functions and informations on the blockchain and do everything else off-chain. But because we want to explain structs and everything, now I will track everything I can, and like every single payment, single thing in greatest detail possible with our smart contract now. But rule of thumb, just move the stuff that really needs the blockchain onto the blockchain. So for sake of this example, let's write our small wallet and then improve the small wallet. And it's not going to be the same wallet that you're going to write at the end of this project, but it's going to be just enough to explain how mappings and structs work together. So let's call this, I don't know, example mapping struct solidity. And bring over the SPDX license identifier and the pragma line. And let's call this mapping struct example. Now that I think of it, maybe not the best to have example mapping struct solidity and then call the contract mapping struct example, but just bear with me on this one. And what we want to do is we want to have basically three functions. One is a function deposit money, one is a function withdraw money, and the other function is getting the balance of a particular user. Now, what we did before was a mapping that maps address to a uint, and we called that balance. And then we have a function called deposit money that is public payable, and we are going to balance message sender
is plus message value. And when we want to have a function withdraw money, maybe an address payable to and a uint amount public, then we are going to reduce the balance of the message sender by the amount, and then we are going to send the amount to the user. Now that one doesn't track a lot. I mean, we can send money here and we can send money back. Make this a little bit bigger. But it doesn't really track any kind of deposits unless you are going to look into a block explorer and just see when somebody deposited and when somebody withdraw money. And that's something we are going to look into the next project, how we can track that with block explorers and how we can do code verification. But in this lecture, I want to show you actually how to use structs and how to use them in combination with a mapping. So why don't we create a struct that actually records a transaction, be it a withdrawal or a deposit. So let's call this a struct transaction. And over here, we are recording an amount and we are recording a timestamp. And the other thing that we are going to do is we are not keeping the balance in a simple unsigned integer. We are keeping the balance in another struct that has the current balance, the number of deposits, the actual deposits, the number of withdrawals, and the actual withdrawals. So let me show you how that can work. Struct, simply call this balance, for example, and maybe the total balance. And then we have a uint number of deposits. And then we have a mapping inside that tracks for each deposit an actual transaction. And then we have an unsigned integer number withdrawals. And then we have a mapping that tracks for each withdrawal a transaction withdrawals. And over here, our mapping balance isn't going to map to an unsigned integer. It's going to map to balance. And let's call this balances. Now, what we can do here now is instead of just simply tracking that a balance was received, we are going to increase the total balance when a deposit happens, and we are going to record a new deposit in our deposits mapping in our balances mapping. The way this works is by accessing with the dot specific variables from our struct. So in our balances mapping, we want to increase the total balance by the message value, but we also want to record a new transaction. And it happens to be like this transaction, and we want to keep this in memory here. It's going to be a deposit, is a transaction that is containing the amount, the message value, and the current timestamp, which is the block timestamp. And then we are putting this on the current position of the number of deposits, and then we are increasing the number of deposits. So if it's the first one, number of deposits is 0 because it's initialized with its default value. We can simply use this in an array syntax writing to access our mapping keys. So what we want to do is from the balances of the current address that deposits, we want to get the deposits mapping, and over here we are going to access the balances message sender.num deposits, and we are going to assign this the deposit, and then we are increasing the number of deposits. Message sender num deposits plus plus. Okay, just to be clear, what happened here is we want to write into this mapping with this key type, or with this key, with the value of this variable for this key. So over here, we are expecting an unsigned integer, and that one, and the first time we call it is 0. So what actually happens here is that this one will be 0. So we're accessing the first element of the element with the key 0 of the deposits mapping over here. And this one expects a transaction. So we are going to save this transaction over here in the deposit 0. That's our first transaction. And then we're increasing the number of deposits. So the next time we call deposit money, that one will be 1. So the next time we deposit something, we are going to access the deposits variable 1, and so on. So now we are going to do the same thing with withdrawals as well. Let's just head over down to the withdrawals. We are decreasing the balances of total balance by the amount. And then we are also recording a new withdrawal. So a transaction memory withdrawal is a transaction, and that is the amount and the block timestamp. And we are going to add this to the balances of the message sender dot withdrawals. And over here, we want to access the key of the num withdrawals. So in our balances, message sender num withdrawals is the withdrawal. And then we're increasing the number of withdrawals. Yeah, it's quite extensive here. Let's give this a try. So we are going to deposit one way over here. Oh, we should have made this public. Then we can actually see what's going on. Let's try this again. So deposit, and let's see what happens here if we're gonna copy this address. Okay, we have a total balance of 1 way, and we have the number of deposits is 1. So we had 1 deposit so far, but we have no way to actually access the deposits. Question is, what happens if we make this one public over here? Does this work? No, it doesn't. So we have to write specific getter functions for the deposits. So let's say we want to access the deposits for a specific address, then we have to write our own getter function. It's not getting returned automatically. So if you're gonna get deposit number, and then it's like uint num deposit address from uint deposit public view returns a transaction. Memory. Okay, and here we're gonna return balances from deposits num deposit. Let's see if that works. So I'm just gonna clear this out, gonna deploy this again. And let's deploy, let's get 1 way into the smart contract. And let's see if we can copy this address over here, balances. So we have 1 total balance, 1 number deposit. And now we want to get from this address the deposit with the index 0. And we get back the amount and the timestamp, and that is the amount is 1 and the timestamp is this Unix timestamp. Now, there are a couple of things that are important to understand with mappings. And I think the most important thing to understand is a mapping doesn't have a length, unlike arrays. So with an array, you have a length. And because an array, it's known to the smart contract or known to Solidity how many elements are stored in there. The good thing and the bad thing with mappings is they don't have a length. So every value that is possible is already initialized with its default value. And why is that? That is because internally it is stored with the actual hash of the value that you provide as a key. And it will just look in its own storage and see if there is anything written there. And if not, then it will just return you the default value. So this is also where we actually have to keep a number deposits and number withdrawals helper variable to understand how many deposits were actually there. If you do this with an array, then you can do the length, but an array has other drawbacks. And yeah, they're just not as convenient as mappings. Yeah, and that's it. What I wanted to show you with structs and mappings. They are quite powerful, and you basically will use them almost everywhere. And I've seldom seen smart contracts that do not use structs and mappings. And with that, I want to go to a different concept now that are exceptions. Now it's time to learn about exception handling in Solidity. I want to get started with require and then head over to assert and then show you a few things with revert, named exceptions or custom exceptions, and try catch. If you come from a Java background, you are probably going to be a little bit disappointed. Exceptions in Solidity don't work quite the way you're used to them. Even if you don't come from Java, like Node.js or even PHP, it's not the same. Let me show you what I mean. Let's get started with a simple example with a simple smart contract. I'll just call this example exception requires Solidity, and over here we are going to bring over, yeah, you guessed it, right, our XPDX and license identifier in the pragma line. And this time, okay, let's call this contract example exception require. And what I'm going to do now is I create a deposit function, and I create a withdrawal function with a simple mapping. And for the withdrawal, I'm going to check if the amount we are going to withdraw must be smaller or equal than the balance we actually have. And instead of using Solidity 8.15, I'm going to use some smaller version like 7.0. And the reason for that is I want to do that with the integer rollover example. So it actually makes sense to have this require statement. Anyway, you should always check if the withdrawal amount is smaller than the actual amount available, and so on and so forth. So input validation is a thing that you should always do, no matter what kind of Solidity version you have. But that's a different story. So let's create this mapping, address, unsigned integer, public balance received. Then we have a function receive money, public payable, and that is going to increase the balance for the message sender. And then we are going to have a function with the draw money. And over here we have an address payable to and an unsigned integer amount. And we are going to check if the amount is smaller or equal than the balance received. Then we are going to decrease the balance received by the amount, and then we are going to transfer the amount to whoever is the lucky address to. What did I make here?
Oh, of course, message value. Okay, so now it compiles. If we are going to deploy this, and I'm going to send, I don't know, 100 way to this smart contract, receive money. So how much do we have in there? We have 100 way in there, and I want to withdraw it back to me. And I'm going to withdraw 1,000. If we hit transact, well, we still have the balance here because nothing happened, because the amount that we tried to send is larger than the balance received balance that we have. But the transaction went through, and that's just not a good thing. You want the perfect, or you want a good user feedback from your smart contracts. You want to tell the users if something went wrong, and this is where require comes in. Require is for input validation, and it can also output or send it throws an exception, it rolls back the transaction, the complete transaction, and it gives you optionally an error message. So instead of the if, we can write a require here, remove the curly brackets, because that's not a control structure. And we can have an optional error message, so not supporting. Yep. So what happens here is that this part of the require, if that evaluates to false, then it will roll back the complete transaction. So no matter if this is the last statement over here or the first one, everything that happened within the transaction will be rolled back. It is as if this transaction never happened. And this error message will be outputted. What internally happens is it is actually, when it's compiled, it is changing the require to revert error, and then whatever is the error message. But I'm going to show you this in one of the next lectures again when we talk about custom errors. Okay, let's run this. Let's see what happens. I'm just going to deploy the same smart contract over here again. So we have two instances. We are going to send again 100 way to our smart contract. And then we are going to try and see if we can withdraw more than the 100 way back. So I'm just going to withdraw 101. So what happens here is now the transaction is actually not successful. Status is false in this case. That's important to understand. And we are getting a revert back. And the error message, the reason provided, is not enough funds aborting. So you can give the user feedback when something happens that shouldn't happen. And require is for input validation. So it will use up gas until it hits the require statement, and then it will return the rest of the gas. So even if you say you give the smart contract 8 million gas, if until here it only uses 50,000, then it will give back 7,950,000 gas to the user. It's important to understand that because in the next lecture, we are going to talk about Assert, and Assert is for a different purpose. So stay tuned. Now that we've talked about require, I want to talk about asserts. And assert, the function assert, is used to check invariants. And invariants are states that our contract or variable should actually never reach, like never ever. And for example, if we decrease a value, then it should never get bigger. It should only get smaller. And that's an obvious example. And I want to use that in our smart contract now because it is a nice showcase. So what I'm going to change in our smart contract is instead of an unsigned integer 256, which is a fairly large numbers range, I will use an unsigned integer 8. And that is not so uncommon that you're going to limit the unsigned integer range because it is for gas optimizations. So if you do gas optimizations, you're trying to like make variable types small enough that they can fit in the same storage slot. It's a different technique. It's something that I do not want to go in depth right now. Just bear with me. Now we have introduced a potential bug over here. We are going to fix the error messages in a second. But the bug is our unsigned integer 8 ranges from 0 to 255. So we're going to convert this over to unsigned integer 8 because that's an unsigned integer 256 by default. And this one is an unsigned integer. Well, let's just make this an unsigned integer 8. Now, the problem is that this value over here can roll over in Solidity 070. And one thing that we should never reach is that the balance received, even though we add something, should be smaller, like is again smaller than, well, what we added. So essentially, the unsigned integer 8 of message value should always be the same as message value. But let me show you what I mean by that. So if we are going to deploy this smart contract, and we are going to send 257 way to this smart contract, so receive money, then let's check the balance. Let's see how much is actually in the balance received. Oh, it is only 1. And why is that? The reason is that it will roll over to 0. So it can store 0 to 255. If you try to put in 257, then the value 256 becomes 0. And the value 257 becomes 1. And then it's only stored 1. So if you try to withdraw again, you cannot withdraw, well, more than your balance. Or you introduce some weird bugs in your smart contract. So one thing to test that and to make sure that this can never happen, or this should never happen, is to use assert statements. And assert very much functions the same as require. So you input, you have an assert function, and you compare something. And if it evaluates to false, it will stop the execution of the smart contract, and it will roll back everything. So in this case, we can assert that our message value is the same as the unsigned integer 8 of our message value. And let's see what happens now. So I'm going to deploy the smart contract, and I'm going to try to deposit 256 way. And it's going to stop the execution. And the difference to the require is that this is going internally to a panic opcode. And what panic means is that it's going to use up all the available gas. So we provided 300,000 gas. It's going to use up 300,000 gas. It cannot throw an exception, a normal one. It is just stopping the execution, eating up everything it had, saying like this is a panic. We stop here. Yeah, essentially it is a state that your smart contract anyway should never reach, because in this case a balance can only get bigger and smaller, and it will just make sure that, well, we shouldn't execute this particular transaction again, because it's something that shouldn't happen in your smart contract. Okay, there are two more things that I want to talk about with exceptions before we are moving on. There's a concept for basic try catches inside smart contracts in Solidity 0.6, and it doesn't work exactly like in other languages. It works slightly differently, and it's only for smart contracts. So let me show you how that works. Let me create a new file, example try catch sol, and just bring over something over here. We can make this work for Solidity 0.8 and then whatever is the newest Solidity version, and call a new contract that will throw something, and there's a function, like a function that doesn't do anything else than throw an error message. So if we are going to, actually that can be restricted to pure. Okay, if we are going to execute this one, and we are going to call a function that will inevitably throw with an error message. Now we can catch this, but we cannot catch it from outside. We have to catch it from within another smart contract. So the way this works is, let's create a contract called error handling. And just let me show you how that works. We have a function. There's a catch the error. It doesn't really matter how it's called. And if we want to call the other function with, like let's say we have the will throw, will is a new will throw smart contract. And then if we are going to call will.a function, then that one will definitely not work, because if we're going to deploy this and call catch the error, it will crash, because when it calls the a function, it will just require false, and the whole chain will just crash. The chain of commands will just crash. The transaction will not go through. Everything will be reverted. The way you are catching these things is with a try catch. So the way this works is you try will a function, or whatever that function is, and then if that works, then you can add code here if it works, and you can catch here the error with the string memory, the reason. And here you could do something with the reason. And we haven't really covered events yet. I just want to throw in like emit an event here that shows you that there's actually something happening. So just follow along. Let's define an event called error logging with a string reason, and then we are going to emit the error logging with the reason here. So if we are going to deploy this smart contract and we are going to catch this, then the transaction goes through. So it will try, but it will land in the catch block, and it will actually emit an event. So if you open up the transaction details, you see in the logs part that there is an error message, that error logging event with the reason error message. Now this is for the require that will catch an error. There is also another one for assert, and that is a panic. An assert doesn't have any kind of message. So an assert only has an error code, and we could do here a uint error code. And then we could maybe event error log code in code, so we can emit the actual error code. Just to show you how that looks like. Log code. So instead of the require assert false, that will definitely throw something. Let's deploy this and let's have a look how that looks like. Catch the error. It fails and it emits an error log code with the code 1. Yeah, seldom I don't know where this actual code comes from. But you can catch panic errors. And then for any other kind of error, which is then something that we are going to do in the next example, is the rest of them. So if it's not going to be an error, and if it's not going to be a panic, so if it's not going to be a require that fails, and if it's not going to be a panic that fails, if it's a custom error, then you can only catch it with custom, like with the rest of the bytes, memory, and then some low-level data. And I don't know, this will, maybe we cannot emit anything here. Well, I can maybe event bytes, low level data. Log bytes, low level data. And don't worry about it. If you don't know what events are, we are going to discuss them in depth later. Right now, it is just here that we can see some output here in the logs. Now, the question is, how can you throw low-level data? The thing what you need to know is an require will revert with an exception called error. And this is why you can catch the error here. And assert will fire an exception called panic. Now you can also have custom exceptions, and those custom exceptions are defined at the beginning of a smart contract. So I could say here, error not allowed, error with a string for a reason. And instead of requiring here, or asserting here, I can say revert not allowed error, you are not allowed. And this one is not an error, it is not a panic, and it's unfortunately also not really catchable. So it's very crude almost in how the exceptions are working. I can deploy this now, and I can catch the error. And you will see that we are logging bytes, and then we have to take care of parsing this low-level data ourselves. So the way this works is that one is the signature of the error, exception of the error. And that one over here is the encoded string, I would assume. And if you are converting it, then you get you are not allowed, which is the kind of like the bytes encoded string from over here. Maybe I cut 1 byte off, but it essentially gives you are not allowed. Yeah, that's all I wanted to cover with the custom error messages and try catch. I barely use them inside smart contracts because usually if you are calling an external smart contract and it fails, then you just want to have the transaction fail. That's the whole point. It's an atomic operation. You don't want to interrupt that. But if you really need that, then this is how it actually works. So let's wrap it up before we are implementing our wallet. We already talked about addresses a little bit, but since we are writing a wallet here in this project, I want to cover one more quite complex topic before wrapping it up, and it's about sending money around. And there's more than one way to do that. So far, we've talked about addresses having the property balance, and you can use a function called transfer to transfer money from a smart contract to an address. But there is more functions that we can use, and there's more ways to interact with another smart contract and sending money versus a so-called externally owned account, which is created by a private key and sending money there. Now let's get started with a simple example where I want to discuss briefly the difference between send and transfer. And let's create a new contract over here, and let's call this example send transfer Solidity, and just bring over our SPDX license identifier and the pragma line. And let's create 3 smart contracts so I can demo you the difference between send and transfer to these smart contracts or between smart contracts. Okay, let's create one contract called sender,
And that contract is going to be a fallback function, just that we can receive some funds here. A function withdraw transfer, and that is going to use the transfer function to withdraw all the funds or funds to an address 2.transfer, I don't know, 10-way. And we are going to create another function called withdraw send, and that is going to use the send function 2.send10. So basically, those two functions are doing the same thing. So transfer will transfer 10-way in this case, or any amount of way to this address, and the send function will transfer or send 10-way from the smart contract to this to address with the send function. So the question is, when should you use which one and why? So let me create two more smart contracts to show you the difference. So I'm going to create a contract called, I don't know, receiver no action, and that one will just receive any kind of funds that is sent there, but not do anything. And if you want to get the balance of this contract, then we can do this with a special function that says return address this.balance. So we know how much money is in this smart contract. And then we are going to create another smart contract. And this time we call this receiver action. And this one will write to a storage variable. So we're going to have a uint public balance received. And we have a receive function. And this will update our balance received with the message value. And there's an important difference, because this one is not doing anything other than getting the money and basically not stopping the execution, just not doing anything. And this one will write to a storage variable. And if you want to write to a storage variable, this costs gas, and it costs quite a lot of gas if you write the first time, especially the first time. So we also want to have read the balance from the second one. Just paste this here. So what will happen if I use the transfer function? So let me start with the transfer function. Ignore the warning here for now. So I'm going to deploy the sender. I'm going to send 1,000 way to the sender just to have that funded. And you use the low-level interactions here. So you just transact, and it will hit the receive function. And then I'm going to deploy the receiver action, and I'm going to deploy the receiver no action. So I have both of them. So if I'm going to copy the receiver no action address, and I'm going to paste it into the transfer function, that works. Now in our receiver no action, we have 10-way. If I'm going to put it in the send function, oh, that works too. Now we have 20-way. So we used one time the transfer function, one time the send function. Question is, what happens if we are going with the receiver action? Let's use the transfer function first. So we hit the transfer function. Oh, it doesn't work. Why doesn't it work? Because when we called the receiver action, it tried to write to the storage variable, and it ran out of gas. And then the whole thing failed. It came, the calling contract saw that the call failed, and it just failed. It threw an error, and yeah, the transaction was rolled back. What about send? So let me do the same with send. Oh, the transaction goes through. Is it really gone through? Let's check the balance. It's still 0. That's strange. So here's the difference. The difference is that the transfer function will throw an exception or throw an error, basically just throw or revert, when the transfer fails. The send function will return a Boolean. So in case you're using any kind of low-level interaction with smart contracts
And the send function is a low-level interaction. It doesn't care about what's happening on the other side. All it cares about is it's going to send this away. And if the execution is successful, it will return you a Boolean. So a Boolean is sent. And then you have to take care of require this, like making sure that the checks are in place, that this send is actually successful. Sending the funds was unsuccessful. So let's see this again. Also, the warning got away. So it actually warns us that, hey, this one can fail. You have to be careful about that. You have to check the return value yourself. So if we are going to deploy the sender again now, and we are going to put 100 way in there, low-level transaction, and we are going to send to the receiver action the funds, it will fail, and it will tell us sending the funds was unsuccessful. And the reason for that is because the isSend is false. This the require is false, and it will just fail here. So always be careful with that. But there's more. So what if we actually want this to succeed? Because what if we know that there on the other end is a smart contract that actually does something with our funds? How are we going to go about that? And we go about that with external function calls if we know the smart contract, and low-level calls if we do not know the smart contract. Let me show you the function calls with known smart contracts first, because it's easier to demo. Okay, let me show you this with a new smart contract. Let me just reload the page here. And let me show you with a new smart contract how that looks like, because it's quite convenient to know these features. 1 second. So here we go. Example contract call. Solidity. So let's bring over the SPDX license identifier line and the pragma line. Okay, let's create two contracts. Contract 1. And this one on deposit is going to write to mapping. So mapping address uint public address balances, classic mapping for a wallet, and then a function deposit, not even a low-level function, a function deposit. So I will show you how to call this payable. And this one is going to, in our mapping for the message sender, is going to increase the value by message value. And then we have a contract 2 that should call the contract 1. And over here, well, we first want to put something in there. And then we also want to deposit on contract 1, some function. Let me just give it an address for contract 1. So this one will take the contract 1 is contract 1 at the contract 1 address. So fine, we have that one. And then we can do one.deposit. What can be? The question is, how can we make it so that the value we are putting in there is actually going over here? How does it work? And that is very easy with the special syntax. And the special syntax is over here. Before you actually do the call, you write in curly brackets a value, for example, 10 way, and a gas amount that is optional. And let's say we provide 100,000 gas instead of the 2,300 gas that is provided by send and transfer. So send and transfer are both providing 2,300 gas, not more. And you cannot do a lot with 2,300 gas. You can emit an event, which you will later eventually see, but you cannot write to any storage variables, let alone to any other contract calls or complexity or anything much other than receiving the funds. So what we're doing now is we are using a native transfer of funds from our contract 2 to our contract 1. Now let's give this a try. We are deploying our contract 1. We are deploying our contract 2. Let's send 100 way to our contract 2 with the low-level function here. You could also write a deposit function here that is public payable. And then we are going to deploy to our contract 1 some funds. And now let's check how much is in our contract 1 for the contract 2's address. Just be careful over here. The message sender over here will be the contract 2, not your address, because the contract 2 sent the funds and called the contract 1. Let's check. It's 10. That is perfect. But the question is, what if we do not know if the contract 1 is a smart contract? Or what if we don't know the exact ABI array? What if we just know one function? How are we going to do about that? So what if we don't have this line here? How can we encode a call so it actually also calls the right function? And the way you do that is with a function called encode with signature. You will later see in the debugging section that when you do a transaction, the data field, the call data field, is encoded in a special way. And the first 4 bytes or 8 hex characters, they define what kind of function is going to be called. And the way this works is the function name plus the parameters are Kesa cached. So what encode with signature is doing, it is taking that particular function signature and creating it for you and putting it into a bytes. So if you have a bytes memory payload, and then we can say ABI encode with signature, and then we want to call the deposit function. The deposit function doesn't have any arguments. If it had arguments, you would add it over here, but it doesn't have any arguments. And the way the actual function call works then, on the contract 1, there is another function on the address type contract 1. There's another function that is called call. And then you can give it here the payload. The question is, where is the value and the gas coming in? The value and the gas are coming in right before the normal round brackets open. So this is how you can call any kind of smart contract, any kind of function of a smart contract with specific call data. And that is very, very convenient to know sometimes. With every low-level function, like with send, you have to check the return value and if it's successful. It will not fail. So the way this works is you have actually 2 return values over here. One that tells you if the transaction was successful, the other one if there's an actual return over here. We don't have a return, so we don't have this right now, but we have a Boolean success, and this will tell you if the low-level call was successful. And then we can just require the success. So now all of our warnings gone away. Everything is gone, so we can simply deploy the second smart contract, fund it a little bit. Contract 2, transact, and then we can deploy, we can transfer another 10-way to our smart contract. Now we have a different address balance. So this also has 10-way. Okay, but the question is, what if we do not know anything about the smart contract? Now we made like low-level calls, but what if we don't know anything about that? In a way, this works is, so if you want to call the fallback function, the receive fallback function, the way this works is by not providing any payload. So if we have a fallback function over here, and this fallback function is doing more than just receiving the funds, if the fallback function is doing the same as the deposit function, or if the fallback function is actually calling the deposit function, so it writes to this mapping, then you have to provide more gas. So instead of just transferring it to this address of the contract 1, you can do a low-level call. And let me just comment this out and provide an empty payload over here. And then it will just hit the fallback function. So let's give this a try. Let me deploy the contract 1. Let's deploy the contract 2. Let's fund the contract 2 and call the deposit on contract 1 with the contract 1's address, and then check the balance for the contract 2. It is 10 way, and the reason is this one over here called the address of contract 1, provided 10 way into the, well, during that call, and it hit the fallback function. The fallback function called the deposit function. The deposit function said, well, who initiated this particular call to this smart contract? It was this contract over here. So that one will be here, and the message value will be 10 way. And that's how it works. And this is how you generically send funds like this 10 way to addresses, and even providing more gas. But be careful here. This one opens up the potential for a re-entrancy attack, or in general for re-entrancy. Because if you provide enough gas over here, then there is no reason why this smart contract couldn't go back and recall this one, and then maybe change the state somehow. This is where this checks effects interactions pattern comes in, where it says, first check if this address or whatever you want to do has enough funds, or like the state is correct for this operation. Then reduce the funds or change the state of this smart contract the way you want it. And then as a last thing, make the interaction. So the last thing in your function call should be the interaction, which is then an external function call. Always be careful about that. Never assume that an external function call will not be to a malicious actor. That is very, very important to understand. And I can also recommend you read into re-entrancy attacks, because that is a big topic. Now, before we start implementing our smart contract, let me wrap up this section, because it was quite a bit of stuff to do here, and maybe not everything is completely clear anymore. I don't know how much time did you take to take the lectures and so on. So let's go through all this stuff quickly and just see if you understood everything. So the first thing that we did was mappings, and mappings are a little bit like hash maps, and you go from a key type to a value type and then give it a name. You can also make this public, so you can add the public keyword over here. But the point is, you can go from address to an unsigned integer, from an address to an address, from a Boolean to an address. But you can also go from an address to another mapping, or you can go from some key type to a struct, as you can see. But the key type, that can be any kind of elementary type. This means it can be any of the built-in value types plus bytes plus strings, which is really cool. And the value type over here, so you can map to pretty much any type, including other mappings, as you saw before. What is important here, all values are initialized with their default value. Mappings doesn't have length at all. And you can make a mapping public, so it becomes a getter function. You can have iterable mappings that can be done with special libraries, which we might gonna cover later, but basically just have to Google mappings and library, and you will find libraries that actually implement mappings that you can iterate through the mapping. But by default, you cannot. Then we covered structs. It's a way to create your own custom type. So if you define a struct, for example, funder or transaction, we had transaction with amount and timestamp, then you can say, I have a new variable with the type funder, and then with the period over here, you're going to access the members.
Well, the members of the struct can be pretty much of any type except of the type of the struct itself. And if you think about you want to do a child smart contract, then usually it's better to define structs than child contracts or objects, mainly because of the gas consumption in the first place, which is pretty obvious, but also because you need, for setters, you need usually kind of a fairly complex access rights or some sort of permissioning system, and you just add complexity to it. So it's not always ideal to use objects, but there are certain cases where objects are actually better when you know that you want this extra complexity. Otherwise, I suggest that you stick to structs. You can also then directly get through the public getter function, get the values. You don't have to go via an address and so on. So you can also combine those, which is exactly what you usually want for advanced data structures. And that is used a lot in Solidity. And you can also find this pretty much in any kind of smart contract and mapping with a struct. So this is essential that you understand how these work. This is why we spend so much time on it. There's also arrays, which we didn't really cover. There's fixed and dynamic size arrays. You can define them. They have members. You can push elements to an array. They have a length and so on. But be careful with them. Usually it's better to use mappings. But arrays work like in any other language, and we might gonna run a couple of examples on arrays later on. For this particular project, you don't need them. Then there's also enums, and they just fit in here with the rest of the data types that we're covering. It's a user-defined type in Solidity, and internally it's just integers. But the way you define them is you say it's an enum, and then you give the enum away a name, and then you define all the possible options for the enum. And then you say, okay, I have a variable of the type of the name of the enum, so it's going to be an enum type self-defined variable type, and then you access this where you give this the way you access the actual values is by saying, okay, action choices dot go left or action choices dot go right and so on. And this is how you can assign enum types the actual value. So let's make a takeaway over here. Mappings are like hash maps. They are usually preferred over arrays, mainly for guess reasons. Structs is a way to define your own data types, and mappings and structs are a powerful combination, especially for things like wallets. Now, what else did we talk about? We talked about errors and exceptions, and the throw isn't a keyword anymore. I will still talk about it because some smart contracts are out there, require assert and revert. Now, transactions are usually atomic, and errors are state reverting. That means the transaction is completely abandoned. No matter where the error happens, the whole transaction is going to be rolled back. There is require assert and revert. That was previously in versions, I think Solidity 0.4, called throw, or maybe even 0.3. But you will not. Usually you won't see this anymore. So if you see throw, it is now the actual require, I think. So this one was throwing an exception. They cascade, meaning if you are calling another smart contract with a contract call, then if that contract, so if over here, this one is calling another smart contract over here, and that one fails, then this one will fail too, and the whole transaction will fail, except for low-level function calls, and that is send call, delegate call, which we didn't discuss yet. It's for libraries, and static call, which is for non-state modifying functions. Those are low-level calls. They will return you a status, and you have to check yourself that status Boolean if that is true or false. If it's false, there was an exception that happened in the called smart contract. Well, catching outside of Solidity is not possible, but now within Solidity. So actually that is now possible. During creation of that particular slide, it was not yet possible. And I'm going to talk about this in the next slide. Revert and require can return an error string. Actually, revert can revert a custom error message or a custom error, a custom exception. Okay, when to use actually assert and when to use require. That's a big topic that a lot of people don't really understand. So assert versus require. A revert operation that is internally a 0xFD returns the remaining gas. And an assert is like a panic that consumes all the gas. So assert is used to validate invariants, states that your smart contract should never be in. And require is used to validate user input. So whenever you validate user input and the user inputs something wrong, you kind of want to be nice and return him the gas. Plus, you want to be nice and actually give him an error message. Well, with assert, you just say like, wait, this should never happen. That's a technical error. Don't do that again. So if an assert is triggered when you try to access an array out of bounds, when there's a division by 0 or modulo by 0, when you do byte shifting by a negative amount, when you convert a value that's too big or negative to an enum, when you have a 0 initialized variable of an internal function type, which we didn't cover yet, or when you just do an assert, which evaluates to false, which I showed you before. When you do, when a require is triggered automatically, well, obviously, if you have a require that evaluates to false, but also if you do a function call which doesn't finish properly, then which, you have one contract that calls another contract and so on. So that will trigger a require, so the remaining gas is returned. If you call an external function to a contract that doesn't contain any code, so if you try to call a contract on an address where there is no contract, if your contract, or if you try to send ether to a contract that doesn't have a payable modifier in the function, or if you receive either the getter function, or if the transfer function fails. This is where require is triggered. Now, throw is outdated, it's removed in Solidity 0.4.10, and it's just not there anymore, so you don't have to pay attention to that. Revert reverts the transaction, and, well, you can usually do like a revert like this, where you just revert and you say if, then revert. Otherwise, you do a require. That's the if part, and then that's the message part. And then there's also try catch, and that catches errors from within intercontract calls. It catches an error if it's a revert. It catches a panic if it's an assert, like a division by 0 or any other non-recoverable error. And it catches also custom errors, but only with the rest. You have to do the decoding yourself if you want to. And you can define custom errors with error and then my custom error. So you have the error keyword, and then you define it with my custom error, and then you can give it some parameters. What are the key takeaways here? I usually require for input validation, use an assert for checking internal states, and for both, if it evaluates to false, then evaluate to true. No, this is evaluate to false. If it evaluates to false, then the transaction is aborted and there's a revert error that happens. Okay, contract calls is something that we did briefly. We did named function calls over here, where we had one smart contract, one contract calling another contract. And then over here, we called the actual function deposit. And the important part over here is that it has a value and a gas, so it can actually do something. So we transported 10 way, that's denominated in way, with 100,000 gas. So this smart contract, contract 1, can actually write to a storage variable which usually costs a lot. But what if you don't have this luxury of directly calling the smart contract? Well, you can also do this anonymously. You can either do an ABI encode with signature over here and then provide the payload. Or if you have directly a fallback function and you just want to provide the fallback function with more gas, then you can call the address of that smart contract .call, and then in curly brackets, the value and the gas, and then an empty payload. And then because it's a call, it's a low-level function, you have to kind of make sure that this one succeeds. Then before we are continuing, I want to spend a moment on accounts, just understand how accounts and ethers are actually transferred. Now, I already briefly talked about it. Accounts that are created with a private key are called externally owned accounts. I briefly mentioned this. It's called EOA. And a contract, which also gets an address, is called a contract account. And let's say this is the Ethereum blockchain. So who is actually allowed to initialize a transaction? So obviously the externally owned account, the EOA, is allowed to call a contract. We did this all the time. The question is, can the contract call another contract without being initialized? And the answer is no. So a contract by itself cannot do anything. But an externally owned account can call a contract, which then during running that transaction calls another account, calls another contract. Obviously, we can also have several users call the same contract, which then in turn transfer money or do anything with other externally owned accounts, like send money there, or call other contracts, which then send money there. So all of that combinations are possible. Remember, all information is public. It's a global database, and addresses have two important members, balance and transfer, which we used a lot. That's something you already know. We can also do the low-level calls. Send returns a Boolean, doesn't cascade exceptions. Call, gas value, lets you forward a specific amount of gas, also returns a Boolean. Be aware of the re-entrancy dangers, and also that send and transfer do not really have the re-entrancy dangers because they only send 2,300 gas along, and that's pretty much nothing. You can only receive the values. So that's my last slide here. Key takeaway: all information is public. It's not that ethers are stored in your wallet, but they are stored on the blockchain. Addresses have a balance and can transfer ether. And the global objects that you saw, they tell you, like the message value and the message sender, they tell you what happens inside a transaction. And we will also see later that there's another one that's called block. I think we briefly mentioned already block.timestamp, which is the timestamp at which the block was mined. And that's it for now. Was a long section, but you made it through. And now the final project, and then we're done. Now let's get started with our smart contract wallet. It's the final task of this section, and this is the implementation. But before watching the video with my sample solution, you might want to give it a try yourself. So those are the requirements. The wallet has one owner. The wallet should be able to receive funds no matter what. It is possible for the owner to spend funds on any kind of address, no matter if it's a so-called externally owned account, EOA with a private key, or a contract address. It should be possible to allow certain people to spend up to a certain amount of funds, so an allowance functionality, and it should be possible to set the owner to a different address by, well, let's say, a minimum of 3 out of 5 guardians in case the funds are lost. So if the owner loses his private key, there should be some sort of a recovery functionality. Now, if you want to do this challenge, then get started now. Press the pause button. Otherwise, I will get started with the actual implementation. Now we are going to create a new file and call this our smart contract wallet.sol. And obviously we have an SPDX license identifier and a pragma line. Let's take a newest version of Solidity 0816. There was only a minor change in the language, so it won't affect us. Okay, so we have a contract called Smart Wallet. Actually, let's call this the same as our file name so we don't have a confusion. Smart Contract Wallet. The first thing that we have is an owner, so an address, payable owner, and a constructor. Constructor that sets the owner to payable message sender. So we have an owner. Then the next one was that the wallet should be able to receive funds no matter what. So because we don't have to track any balances or anything, we can just set a receive function, which is external payable. So now our contract can receive funds no matter what. Then we also need to be able to transfer funds out of the smart contract. So we have a function called transfer and then an address payable to a uint amount. So this would be the naive first approach, which I'm going to do now, and then I'll tell you how to do it better. Okay, it's a public function and it can transfer. Well, first of all, the requirement would be that the message sender is the owner. You are not the owner. Aborting. And then to.transfer amount. Now the problem with that is, what is the problem here? Oh, I mean amount. Yes, I meant amount. Now the problem with that is it doesn't fit our requirement that we can also interact with other smart contracts. We can interact with other smart contracts if the receive function of the receiving smart contract is only doing the fallback function without any kind of storage variable interaction. But it will most certainly not work if you want to interact with a smart contract with an actual call data. So what I want to do instead is I want to add a Bytes memory payload. And then I want to do here, instead of a transfer, I want to do a call. And I want to give it a value. So we are going to send to this address the value of the amount in curly brackets, please. And then we're also sending the payload. Now this one, what's the problem with this one? Yeah, payload. I meant underscore payload. This one should always be checked if the call was successful with the Boolean here. But it also returns us a Bytes memory return data. And then we can simply check here, require success, aborting call was not successful. And then we can return the return data in case somebody called this function programmatically from another smart contract. So what do you don't like? Let's returns. Great. The next requirement is that we should be able to allow certain people to spend up to a certain amount of funds. Now we can do this with an allowance functionality. For example, mapping address uint public allowance. And then over here, instead of saying requirement the message sender, we can do if message sender is not the owner, then we would require that the allowance is larger or equal than the amount that we want to send from this person. So we would say require allowance message sender greater or equal the amount you are trying to send more than you are allowed to boarding. Now there's another problem with that. Of course, this one goes away. There's another problem with that. That is now anybody can go in and send a 0 amount with the address from the smart contract to the to address. So I can impersonate the smart contract if I don't want to send any value. And that's something we definitely do not want to have. So we have a mapping address bool public is allowed to send. So the next one is require is allowed to send. We are not allowed to send anything from this smart contract. Aborting. And this goes first. We also forgot one thing, that is to reduce the allowance. Allowance message sender minus equals message value. So that one will anyway error out. What is the no. The amount, not the message value. Okay, and then we need a setter function. Set allowance address for new int amount public. This one can only the owner do. Not the owner. Boarding allowance message sender is amount, and if amount greater 0, then is allowed to send is true. Else is allowed to send message sender is false. Let's just say you cannot send anything if you are not allowed to spend any funds. Oh, and of course not the message sender, of course 4. Well, lucky that we have these warnings in Solidity. Okay, then the next requirement is that it should be possible to set the owner to a different address by a minimum of 3 out of 5 guardians in case the funds are lost. Now let's say the person lost his private key and he has 1,000 ETH in this wallet. So we somehow need to recover the funds. Well, that is relatively easy. So let's say we have a mapping that is an address bool mapping public guardians. And then function add guardian. We can copy the require statement here. Guardians, guardian is true. Actually, let's call this set guardian. Or is guardian. And then we want to have a function that is like propose a new owner. And it automatically sets the owner to the new owner when we have 3 guardians agree to this new owner. Great. So we have maybe an address payable next owner. And then you int guardians reset count and a uint public constant confirmations from guardians for reset. And let's say we need 3 confirmations. So now we need some sort of function that implements this. Let's call this function propose new owner and then an address payable new owner.
that is public. The first one is obviously have to be a guardian here. Otherwise, you cannot call this function. Require guardians message sender. So if you're not a guardian, you are not a guardian of this wallet, go away. Okay, we call it aborting. We are friendly people. Well then, if the new owner is not the next owner, then we are going to set this next owner to the new owner, and we are resetting the guardian reset count. So that is our initial thing. Then we are increasing the guardian reset count by 1. So the guardians can propose a new owner. There's still a problem with that. And then if the guardian reset count if guardian reset count greater or equals confirmations for the resets, then we can reset the owner to the next owner, and the next owner is the payable address 0. But there's still a problem with that, because as one guardian, I can recall this function, and that's obviously a bad thing because you want to have different guardians agreeing to the next owner. And then we need some sort of a way to find out that the guardian didn't vote yet on this address. So we need a mapping of an address, which is the address of the next owner. And then we need a mapping here of an address to a Boolean. And that is next owner guardian did not or voted bool. So maybe that's a long variable name. So we require that the next owner guardian voted bool for the message for the new owner for this guardian is false, makes you already voted aborting. Okay, well then, this is our wallet. It's quite sophisticated functionality here. Let's give it a quick try. I will not try the guardians now. If you try them, leave me a comment somewhere. You can obviously post this on your GitHub and improve on it if you want to. Right now we have some redundancy in here, which we're going to cover in the next section. But for now, it should be enough to understand, okay, this is our, where's our owner? Let's make this public. Okay. Public payable. Okay, deploy the wallet. Our owner is our address over here. Let's send 1 ETH to our smart contract. Perfect. Then we have another contract. I don't know, consumer. Function get balance. Public view returns you in return address this dot balance, and I just want to test if the call data is working. Function deposit public payable doesn't do anything. So if we are going to deploy our consumer, and then we are trying to interact with the deposit function over here, let's just copy the input data. So we have 1 ETH in our smart contract wallet, and we want to transfer it over to this consumer smart contract, and we want to interact with this deposit function. Then we have to add this payload, and let's just say we send 100 way there. Let's copy the address, and let's fingers crossed that it works. Balance 100. Perfect. Then let's add some allowance for our second account. Set allowance for our second account for 200 way. How much allowance does this address have now? Oops, something went wrong here. What went wrong here? What is guy has no allowance? Oh, I have a typo here. Oh, unit tests would definitely fix this. I think we should do unit tests in the next section. What do you think? So I will not start from scratch. Yeah, why not? Let's start from scratch. Smart contract wallet, deploy. And then we are going to add 1 ETH to this smart contract, transact. And then we are setting the allowance. Oh, this copy and paste is very annoying. Of course, this is the wrong. Yeah, let's transact, and then allowance is 100. And now we transfer to our, where's the consumer? That's weird. I think there's an issue with Remix here. It should say, the interface here doesn't make any sense. Let's deploy a new consumer. Okay, we copy the consumer address. We transfer 100 way to the deposit functionality. I have it somewhere here in my clipboard. Now let's hit transfer. Did we select the right account? Yeah, the second account. Let's hit transfer. Okay, let's hit transact again. This one fails because you're trying to send more than you're allowed to because we already spent all our allowance. Perfect. Now it's up to you to try the Guardian functionality with the accounts here. And with this, I want to conclude our smart wallet functionality, and I will see you in the next lecture. This was quite an intense section, full of stuff a regular Web2 developer is seldom exposed to. If you open up any smart contract in the wild, you should be able to understand around 90 to 95% of it. A big portion of what we covered are the essentials, like the complex data structures and exceptions, as well as the contract-to-contract interactions. Don't forget, the blockchain lives from composability. A contract is only a small function, but it can be combined to serve a more powerful purpose. This is what happens with DeFi. You can give contracts the allowance to do something in your name. With this, and the fact that transactions are atomic, you can do powerful combinations like flash loans, where you borrow several $1 million, execute an action and pay back everything, including interest, in the same transaction, all while hopefully pocketing some nice profit along the way. But that's a different story. We're still missing a few critical elements to cover the full Solidity functionality before moving on to local development environments. In the next section, we're developing an ERC20 token from scratch, and you'll learn about events, modifiers, and a few more special functions of Solidity. Before going to the next section, don't forget to add your smart wallet to your GitHub. post it on social media like LinkedIn, and feel free to tag me there so I can give it a thumbs up. Have you ever wondered how these tokens work? In this project, we are creating a simple coin smart contract and building in a token sale. In essence, everyone who gives us 0.1 ETH can get one of our coins. It's important to understand this project is creating a token from scratch and follows partly the ERC20 interface. So it has all the functions an ERC20 token would have: transfer, balance off, allowance, and so on. We're also looking into block explorers, source code verification, and why it's so important to have a common, standardized interface to interact with smart contracts. At the end of the section, I firmly believe the whole composability features of DeFi will become a lot clearer to you. So even if you're not 100% following the programming side, still stay on. The most powerful side of blockchain development is yet to come.
Now in this section, I want to go beyond Solidity a bit. In this section, we are introducing events, and it makes no sense to learn them without seeing the benefits directly in Web3.js. So in this lecture, I want to give you a little introduction to Web3.js. Particularly, I want to cover the following two things here. First of all, understanding the components involved in deploying a smart contract with Web3.js, but then also how to interact with smart contracts using Web3.js. And we are going to use Remix for this and build upon a little bit the already existing scripts here in the scripts folder. Now you can see I already have another JavaScript file here, but I want you to create a new file and then just call it maybe accounts.js. And I want to get started with a really, really simple example, and that is how to get the accounts in Web3.js that are over here in our Deploy and Run Transactions tab under Accounts. Now, the first thing is it's a JavaScript file. And the JavaScript file needs a function to execute, and the easiest one to start with is an anonymous function that is called. And over here, you write your actual content. That is pretty much the same as a function main, and then you just call main. The reason why I like to do an anonymous function is because it's basically a one-liner. So it's a brackets open, brackets closed. We have no arguments, and then we start the function body, and then we call the actual function. Now, this one we have to be careful. We have to also make this an async function. So because we are going to use async await the promise pattern. Now over here we have access to a Web3 object and console log. If we type in console log ABC, then we can run this script, right click, run, and then we should actually see over here ABC in our console over here down there. Make this a little bit bigger so you can see better. Now we also have access to a Web3 object. And if we do let accounts is web3.eth.get accounts, and then a console log accounts, then we will probably see a promise here. I hope at least. Okay, it's nothing. And if we do await, then we see our accounts that we have over here. Actually, how many are those? It's 15 accounts, not 20. My bad. I always told you it's 20 accounts. No, it's only 15 accounts that are given to us as a sample. Now, where does this come from? This comes from interacting with a Web3 provider and with a Web3 node or with a blockchain node. And the blockchain node here in Remix is simulated. If you switch over your environment to, Injected Web3 MetaMask, and then unlock your MetaMask. Takes a little bit. And then you run this script
then you get the account that is selected in MetaMask. So this Web3 object is connected to the Web3 provider that is selected here in the environment. And that Web3 provider here is the injected Web3 provider from MetaMask. In this case, MetaMask is injecting itself into the website. And then you can interact with, the wallet functionality over here in MetaMask. And if you're not directly interacting with MetaMask, then you're interacting with one of the chains here that you have selected. How this works internally, there are RPC methods for that. So if I open up the ethereum.org website, if it's loading, then you can see eth.getBalance, for example. And what it does internally is it sends an RPC request, a JSON RPC request to the blockchain node you are connected to with the method eth_getBalance, and then the parameters with the parameters, right? It's the address that you want to get the balance from and the block where this balance was recorded, in this case, the latest block. So if you're doing here, let balance is await web3.eth.getBalance with the accounts 0, and then console log balance, but I'm gonna switch it back to the Remix VM. And then we are going to run this. Then we have a number here, and the number, we can also convert this number to an actual ETH with also Web3. Log web3.utils.from way balance, and we want to have ETH. That is a convenience function to convert, to basically divide this by 10 to the power of 18. And not delete, run. No, I need an await here. What's going on? Sometimes that's a little bit finicky. Oh yeah, and this console also doesn't care about any errors, so it's actually called Ether and not ETH. And when you run this, then you get 100 ETH, which is exactly the amount that we have over here. Now, Web3.js, if I open the documentation, web3.js.readthedocs.io, then you can see it has a couple of modules over here. One is web3.eth. Then you have contract interactions, web3.eth.accounts. If you want to have an accounts module that you can actually create accounts and sign stuff, or web3.eth.personal, and so on. And you also have the utils over here, which are convenience functions, and some of them, many of them, you will get to know through JavaScript work. It's just you cannot get around them. And there's also web3.eth.subscribe, and this is the thing that I want to talk about in the next lecture, which allows you to subscribe to blockchain events. So what it does is it is going to deploy, or it is going to configure an event listener in the blockchain node that is going to send the JavaScript Web3.js library updates via WebSockets if an event occurred in one of the blocks that are currently processed by the blockchain node. And you can subscribe to a number of different things, but I want to especially talk about the contract events over here that allow you to just listen to certain events. Yeah, with this, I think it's enough introduction of Web3 for now. You are maybe wondering, what's the ABI Array and why do we need this for interacting with smart contracts? And to explain that a little bit better, I want to dig into debugging with Remix. Now, I have here a very, very simple smart contract, and I'm 100% sure you can already read what it does. It has one unsigned integer variable called myUint. It's public, so there will be a function called myUint which can read the contents of this variable. And then we have a separate function, setMyUint, with one parameter, which is an uint 256 with the name new uint. It's public, and it's going to override this unsigned integer storage variable. Now, if we are looking at the ABI, at these compilation details from the Solidity compiler at the ABI, then you see all the inputs and outputs that the contract has. In this case, it has one function name, type function here, called myUint, and it outputs one parameter with the type unsigned integer 256. It has another function which is called setMyUint, has 0 outputs, and it has one input of the type unsigned integer 256. This one function has the state mutability non-payable, and this one has the state mutability view. But why do we need this? What's the purpose of it if we already see these function names? So why do we need this extra array? And that's what I want to answer in this lecture. So first of all, I want you to go to the plugin manager, to the debugger. I also provided a link in Ethereum-blockchain-developer.com in the labs that you can directly click and you get this smart contract. You don't need to copy and paste anything, and the debugger is activated. I hope the link still works. If not, you have to create a new smart contract and so on. But the point is, there should be a debugger on the left side. So what we're going to do now is we are going to deploy that smart contract, and then we are going to hit, like, myUint is 123 because we have it here, and then we just make a 444, anything really that you want. And then we are going to hit the debug button over here. What will happen is that the debugger will start, and it will go, normally, at least in this version of Remix, to the position where it actually was overriding the storage variable, basically the end of the execution. Now, if you have this horizontal scroll bar, then you scroll it all the way back to the beginning, and then you can step into, and you will see parts of the code here are highlighted. I don't know if you see that. It's basically like a dark blue on a dark gray, but you see that it's highlighted. So when we dig into the code, and let's just go quickly over here, then you will see at some point it will stop highlighting certain parts. So why is that? Now, I want you to direct your attention to this list of opcodes over here. When we are going to a specific step, then a specific opcode is highlighted. And in this case, it highlights push 4 bytes, and the bytes E49to FD84 onto the stack, and then try to compare it with what's already on there. And if it compares, then jump to a specific position in the code. Now, the bytes here, they are fixed. And what is not fixed is the bytes of the call data. These bytes here, they come from the compilated bytecode from the smart contract that we compiled. And it gets compared to the first 4 bytes of our input data. Where is our input data? Over here. So the input data starts with E49 and so on. So it's basically, we can already guess this is going to be the same 4 bytes or 8 hex characters. Now, we suddenly have no more plain text identifiers, function names, or whatever. We are actually working with function signatures. And the function signature here is the first 4 bytes of the KESA hash of, well, the function name, plus in brackets all the
function parameter types. So if I'm going to make the Kaiser cache now with web3.utils.sha free of the string set my uint, which is the function name, plus the type, which is unsigned integer 256. Uint is just an alias for unsigned integer 256. Then we should get a very long hash. So it's the full hash of this function signature. And if you take the first 4 bytes, 8 hex characters, then you will get exactly this E492FD84, which is the same as over here. And that is in the call data before we actually send the padded input parameter in hex value over here. So this one gets compared in code. And our code itself, as you know from hashing, you can go in one direction, but you cannot go back. If you want to know the plain text function name plus the plain text function parameters, then you need this ABI array. And this is exactly what Web3 needs to interact with smart contracts, and other convenience libraries need that too. Now, I want to create a script that actually updates our integer here with the scripting functionality from Remix. So over here, I'm going to create a new script, and I call this update uint.js. It really doesn't matter how you call it. And then I'm going to have an anonymous main function that is async that gets called when the script is executed. And over here, we are going to add our address of our smart contract, and we are going to add the ABI array. And then what we are going to do is we have a contract instance, and that is done with new web3.eth.contract in capital with the ABI array and the address of the contract. And then we can interact with our smart contract. We can, for example, console log, we can say contract instance dot methods, and this will be hydrated or populated with the methods that are given in the ABI array. Currently it's empty, but we are going to copy and paste the ABI array from our smart contract there in a second. So our function is called myUint. MyUint has no parameters, and then we are going to make a call on this. Let's give it a try. Let's have a look. So first of all, we have to select the smart contract, and then over here in the Solidity compiler, you can copy the ABI array, just paste it over here. So you have the full array over here as ABI array, and then in the run and deploy and run transactions plugin, we are copying our contract address because our scripting functionality here in Remix can get access to our Remix VM. So if we are going to the file explorer and we right-click the script and hit run, then we get our 444, which is the content of our myUint. Now, obviously, we can also override this. So we have, for example, that accounts is await web3.eth.get accounts. So we get the full accounts array, and then we are going to override it with contract instance.methods.set myUint. And then we are going to override it with maybe 345, something that you can pick and choose. And then we are going to, instead of a call, which is a reading operation, we are going to send, and we have to specify the account which we want to send it from. And that is going to be the first account in our accounts array. And then we just go and read again what was outputted here. We can also output the transaction result just to see what is in there. Okay, let's run this again. And you see now it was 444, and then we update it to 345, and the transaction result is the transaction hash plus the status, which is true, it was mined, it gives you the gas and so on. Basically the same as you can see over here, because those transaction data is not outputted anymore if you run the scripting functionality. It's very limited, the scripting functionality in Remix, but it's convenient to deploy and interact with smart contracts in a simple way. Now, if we are going back to our deploy and run transactions tab, now it's 345, so everything is in order. Yeah, that is how you can use Web3.js and scripting from like Web3.js from the scripting, with the scripting functionality. And the reason why you need the ABI array is because Web3 cannot guess what are the function names. So if you have also events, which you're going to see in the next lecture, and other things, they are going to be hydrated here, and you can later in with local development environments then actually see this is very beneficial, and Web3.js can correctly encode the contents and decode the contents from function calls. All right, enough from my side. Let's go on to the next lecture where we are going to talk about events. Now I want to talk about events and why we have them and what is it about with these events. So I've prepared a simple smart contract over here, called it event example, and it's a very simple token smart contract. If you deploy the contract, you get 100 tokens, like the person who deploys the contract, and then there's a function called send token, and you can basically send your tokens to somebody else. And if that works, then there is a Boolean returned with a true. So the question is, where can we use this Boolean, and how can we make use of this smart contract? Now let me deploy this smart contract over here in the Remix VM. Going to hit deploy, and I'm going to send one token. Yeah, just let me send it to myself. It doesn't really matter. So I'm going to hit transact with one token, and I'm going to open our transaction details. And what you see over here is there's a decoded input and a decoded output. And the output is a Boolean true. Now the problem with this is this only works in Remix, and we've seen that before, so there shouldn't be any news here. So if I go over to my MetaMask, and I have MetaMask unlocked, and I'm here still on the Coven test network that we used before in the course. So if I deploy the smart contract over here, takes a little bit, confirm. Wait a second until this is deployed. And now I'm going to send one token to basically myself. Going to send another transaction. Confirm. And if I open up the transaction details this time, you see there's a decoded input and no decoded output, because this return variable is actually only for inter-smart contract interaction. So if a smart contract calls this smart contract, or if I call this function from within the smart contract, within the same transaction, I get the return variable, but you cannot get it from the outside. So this is not what it's meant for. What is meant for communicating to the outside are events. So let me define an event and emit an event, and then tell you how this actually works. So an event is defined inside the contract, not outside, inside the curly brackets of the contract. It's called event, and it's called this simply tokens send. And then you can have event parameters, and let's simply define 3 of them before we actually dig into that. So we have maybe an address from, an address to, and maybe an unsigned integer amount. So this event is something we can now use inside functions when we want to emit this with specific values. So over here we could, for example, emit with the keyword emit an event, and in this case it's going to be the tokens send event, and we are going to emit this from message sender to with the amount.
Now you could also emit this over here at the top before the require. And if the require evaluates to false, the transaction will be rolled back. This event will never be sent. So it doesn't matter where you emit this event. If the transaction happens and is successful, the event is emitted. If not, the event is not emitted, no matter where it stands. And if we deploy our smart contract again, let's do this. Close the first one. Let's wait until it's mined. Takes a moment. So we have now our second smart contract instance over here. Let's again send ourselves one token. Confirm. And if we open up the transaction details now, you already see there is a logs over here, logs 1. So let's drill into that. We still have no decoded output, but we have logs, and the logs are an array of the emitted events in the order where they were emitted. Now, this is all nice and good. So you have events that are communicating something to the outside world, but why do we actually need them, or what is the benefit of using them? This is what I want to explore in the next lecture, where we are going to use Web3.js to listen to certain events that are emitted from our smart contract while we are actually interacting with it from within Remix. So let's head on to the next lecture. In the previous lecture, we were doing events as return variables, but that's not the only thing. The actual thing where events come into play is with decentralized applications. And in this lecture, I want to show you a minimal example of an event listener with Web3.js. And I have two different browsers here. I have one Chrome browser with a MetaMask. And I'm here on the Coven test network, and I have a separate browser. In this case, it's a Vivaldi with a different MetaMask also on the Coven test network. And the important part is that you're on the Coven test network. You can do this also in the same browser. It doesn't matter. What I want to show you here is that you can really, from a totally different browser, listen to events. And the way I'm going to do this is with Web3.js, and I have a minimal MetaMask Web3.js example here in this JS fiddle. This JS fiddle is also on our labs website, ethereum-blockchain-developer.com, in the appropriate projects folder. You can follow along, you can click on it, or you can write it from scratch if you want. I will not write this from scratch, but I will explain to you line by line what's going to happen here so you totally understand what's going on. Now, when you open this up for the first time, then you see an Enable MetaMask button. And when you press it, then MetaMask should pop up and ask you for permission to connect. If you get an error like this, that Web3 is not defined, then my JS fiddle remove the Web3 resource. So on the left side, you have resources, and you just search for Web3.js, and it will pop up as a Web3.js, and you just add it over here. I don't know why this is always removed. So now when you hit Enable MetaMask, MetaMask should pop up and ask you for permission to connect to the site. So select the account that you want to connect, hit next, and then connect. Now MetaMask allows for querying the account. And how this works in code is with the following thing. There's an HTML button called Enable MetaMask, and it has the class Enable MetaMask. And over here in the JavaScript part, I'm listening with this Enable MetaMask button to an event that is called click. And then I'm starting this enable tab function. Now in this enable tab function, there is a couple of things happening here, and that's the magic behind this Enable MetaMask button. First of all, we are checking if there is a window Ethereum which is not undefined. So if this is undefined, then MetaMask is not installed, because MetaMask will inject itself
into the website, into the window object as Ethereum, as an Ethereum object. So the first check is MetaMask installed? If it's not installed, then it will just output an error, need to install MetaMask. And it does this into this status text. This status text is simply a span element inside an H2 tag that allows for writing something over here on the right side. All right. If MetaMask is installed, and I assume it is installed here with your browser because we did this in the previous lecture, then it will try to send a request, ETH_request accounts. That's the method it's trying to request. And with the await keyword, it's actually waiting for the promise to resolve. Now, there's two things that can happen here. Number one is the user clicks cancel, doesn't allow connecting. What will happen is it will go into this catch block, and the error code will be 4001. I have this from the MetaMask documentation, so I didn't invent this myself. It's in the documentation of MetaMask. And then I will output error need permission to access MetaMask. Now, if the user connects his account, then we can use window.ethereum as Web3 provider for Web3.js. And I'm using this here as a convenience library. You could also send raw requests here to MetaMask, but I'm used to Web3.js, and I think it's, besides Ethers.js, pretty much the standard that you should know. And it's a great way to get started with Web3.js. So Web3.js, here a capital W, expects a Web3 provider. And then I'm basically initializing Web3 over here. And also I'm setting the accounts array to the accounts array that is coming back from Ethereum.request ETH request accounts. Now what happens next is I'm going to set the account to my first element of the accounts array, which is the one that is here in MetaMask. Let me open this up. So here it is in MetaMask, the checksummed account, and here it's the non-checksummed account. How do you see the difference between a checksummed account and a non-checksummed account? The checksummed account has uppercase and lowercase characters, while the non-checksummed account is all lowercase. We are going to talk about checksummed account in a different lecture and how this is calculated. For now, it is enough that it works. So when you see account, double point is your account that you have in MetaMask, then you can continue. How do we continue? First of all, the input field and the button for listen to events was disabled. So I'm removing this disabled attribute, and that's it. From here, we can continue. We have MetaMask connected to our website, and we can continue. So what do we want to do? We want to listen to events. So if you scroll to the bottom of the page, then you see another function, listen to events. And what this does is it creates a new contract instance. And from the previous lecture, you would know that the contract instance to interact with a smart contract needs two things: the ABI and the contract address. The ABI, I have it already here because we are going to use the contract that I have here in Remix and that you can also have still from the previous lecture. So the ABI I already know. What I don't know from your account is the account address. That's something that you would need to input into this input field after you deployed the contract to the respective network, either on Robston, Rinkeby, Kovan, or the new ones after ETH 2.0 is released. Okay, so now we are going to deploy our smart contract in our network. So I'm going over here to the deploy and run transactions tab. I'm selecting MetaMask, still connected, and I'm hitting deploy. So let's wait a moment until we have the contract address over here. Our contract is deployed. I can now copy the contract's address. I can go back to my, where's my JS fiddle? And I enter the contract address and hit listen to events. So I'm not outputting any kind of data here. You could add some console logs as a debug or something where you can see that actually something happens. But what will happen is the contract instance is created, and then we are taking the contract instance.events, the event name, and then when there is data coming in, then it will call this function over here. And what this function does is it's going to write the events as a JSON stringified string into the status field. That's what it does. So it prepends it actually. So it takes the already existing content and prepends the string. Now let's create such an event. And I'm going to send myself one token because the to address really doesn't matter. So I'm creating a new transaction. And we are confirming our transaction, and we are waiting for something to happen. Let me just resize the browser here, because you saw it in the background. It automatically caught this event from the other browser with the other MetaMask with a totally different account. And the same would happen if you on your machine would have a decentralized application open, like a Web3.js application open that would listen to events from smart contracts. Now you're maybe wondering, what are the limitations of these events, and what else can we do with it? There are a couple of things that you have to keep in mind. First of all, right now you can query events back to the block 0. So you can ask a blockchain node, give me all the past events from a smart contract, and we are going to do this. Now the way you do this is with the contract instance, get past events, and then the event name, and then a config array, which is maybe from block 0. And this one gives you a promise, and then it resolves to event data. So let's try this one. What I get back is the events that happened since the beginning of the blockchain in this smart contract. Now, obviously, it doesn't need to go to the block 0. It actually only needs to go back when the smart contract was deployed. And you can query all events, especially archive nodes, quite easily, going back to really the beginning of the blockchain. This might gonna change, and there might be a chain pruning sometime in the future. I don't know when. But if you are a smart contract developer, you might want to store events also outside of the blockchain in a database or something. Just to be sure, it's also usually faster to query a database for events than the blockchain itself. The other thing that you should keep in mind is filtering and the amount of data you can store in events. Now, under the hood, the blockchain or the EVM has 4 functions to output an event. Under the hood, if you look at the Ethereum yellow paper, which I've opened here, the blockchain defines 4 functions to output an event. And what they do is they define topics and event data. Now, topics are a way to quickly filter the underlying Bloom filter for data, which is very, very handy. And I'm going to show you now how this works. And then I'm going to show you how you can append pretty much all data you want to an event, because it is priced based on the amount of bytes you want to send or you want to emit. So it's not really limited, but at some point you probably won't be able to add more data to an event, because you will run into all sorts of errors, or maybe out of gas. Okay, the event topics. So events, when you have a look at them, and I'm going to show you this now in our Chrome browser over here with the transaction that happened. You see the last transaction where we actually send a token, it has logs 1. So if I open this up, then you will see in the logs a from, a topic, an event, and the arguments. So this one has one topic and, well, number of data. The way the data works is it is combined and then encoded and padded to the ABI data types. And then in Web3.js, through the ABI array, it knows this event has one address, another address, and an unsigned integer. So it takes the amount of data or the length of the data field and cuts it down to the amount to the size of an address, another address, and an unsigned integer, and then it converts the encoded data back to an address, and unsigned integer, and gives you back these convenient arguments. Then you also see this event topic, and this event topic over here is very much like a function signature, the signature or the Kazakh hashed event signature. So if I do web3.utils.sha3, which is the Kazakh hash of tokens sent, and then address uint 256. Don't forget uint is an alias for uint 256. And then I create this hash, then it should be the same as the event topic. And this one is then used to filter inside the blockchain node for specific event names. Now you can have up to 4 topics. And that is the name of the event itself is already one. And then you can define 3 more arguments as event topics to let the blockchain node quickly filter for those topics. And before I show you that, I want to show you what happens if you don't filter or if you don't use indexed keywords. That is, over here in the get past events, for example, you could say filter, and then you could give it an object that filters for specific things. For example, we could use the, what do we have here? The to address. To must be the same as maybe our account that we have here. So to, we filter for that one. And then we hit enable MetaMask, and then we just use the get past events. It finds our event. Now, what you want actually is to filter out stuff. So if I change this address, let's say I make this a 7 here, and I run this again, enable MetaMask, it will still find the event because the to field is not an indexed field. So if you want to filter for specific stuff, for specific values, then you have to make this an indexed field. Okay, if we redeploy our smart contract, confirm, and then we again send an event to our smart, or we send a token to emit an event, then we can filter. Let me show you how this works. This time we copy the right contract address. Be careful that you have a different one here. Oh, come on. You can see the event was outputted, and we can now go in, enable MetaMask. This is our contract address. Listen to events. Nothing is found. We change it back to the right account. Now there is a caveat to that. Also nothing is found. Why is there nothing found? Because our ABI array also changed. If you change the tokens sent arguments from non-indexed to indexed, you have to update the ABI array as well. So you can override this one over here simply, and it now says indexed true And when we now hit run, enable MetaMask, paste this, then we can find our account. And let's make the last check just to be sure that we cannot find our account. Yeah, it's filtered out. And this way you could, for example, if you have a dApp that only shows specific events that are meant for the user who logged in with MetaMask with his account on his side, you can conveniently just filter out before it actually hits the JavaScript part directly in the blockchain node. So this one will actually never fire because the blockchain node will never send any event if it doesn't fit the filtered value. Yeah, just keep in mind, these are values where you can only do an equal. You cannot do like a bigger than or smaller than values. So for example, if you have token amounts and you just want to show events that have more than 5 tokens, you wouldn't be able to do this with filters. You can only do this directly in JavaScript. You have to filter, like no filter, and then just get all the events and then process them in JavaScript. But that's basically all there is to say. I think it's time to summarize this. It was a large lecture. It was a large section about events, and I will see you in the next lecture. Now it's time that we summarize the events and return values a little bit, because the last 2 lectures were pretty long and not everything is quite equally as important. So let me just highlight a few things that were outstanding. Number 1, the EVM has a logging functionality, and it's not the same as storing storage variables. It's used for return values from transactions. It's used to externally trigger some functionality. It's also used as cheap data storage. And there's 2 things that you have to keep in mind. Number 1 is writing transactions cannot return any values. So that one over here is quite important. Because it's a misconception that a lot of people have when they start in Remix. The thing is, a writing function returns a transaction hash, and transactions, they can take very long, or they may fail, or something can happen. So you cannot really rely on return data from transactions. Instead, what you would want to have is an architecture where your application listens to certain events and updates an off-chain state accordingly. So this is where events are used, for example, as a trigger. So when we are looking at maybe a multi-signature wallet over here, where 2 of 2 people need to confirm a transaction. So let's say this person sends free ethers into a smart contract. This person sends free ethers into a smart contract. Now this person wants to withdraw free ethers to that person over here. What will happen is maybe this person has some sort of application installed, or maybe is having a website open, or a smartphone app that is connected to the blockchain, and it will pop up a notification like, hey, can you approve this request? And he's going to click a button, send a transaction that approves a request in the smart contract. We had this before, very, very similar with the wallet smart contract, where you have people who can override an owner if this functionality is built in. So that would be the simplest version of a multi-signature smart contract, where 2 people have to provide a signature in order that something is going to happen. Events can also be used as a data storage. And the problem that you face very quickly on the blockchain is data storing is extremely expensive on Ethereum. And the more ETH will be worth, the more expensive it will be. So the solution to that problem is maybe store data off chain and just store a proof of the data on chain, like a hash of the data, like a notary. Or maybe store data in another blockchain, such as IPFS. And store the data in event logs if it's not necessary on chain, because events cannot be accessed from a smart contract. They can be emitted, but the data cannot be accessed. Very important. So
how does it work with events as a data storage? And I just want to give you a quick comparison. I don't know if this is extremely up to date. And they changed some gas costs for the S-Store EVM opcode. But at some point, this was up to date. And I don't think that a lot of the numbers changed to just give you a good idea of what it costs. So you need around 640,000 gas per kilobyte data storage, or 655 million. So you cannot even go there. You cannot store a million. You cannot store a megabyte of data within one transaction, but you could basically store a kilobyte of data in one transaction if it's 640,000 gas. So let's say you want to store 1 kilobyte of data on a smart contract, but you don't need the data inside the smart contract. You just want to have it inside, I don't know, inside the blockchain somewhere. And you can use maybe events for that. So how would that work with events? Events work slightly differently. So when you want to log something, the amount of data is 8 per byte. So in this case, dynamic data, besides the overhead and everything. But if you have a lot of data, you basically can run with the dynamic part, because the static part will always be there, but it will not be as influential to your overall transaction cost. But let's say you want to store 1024 times the 8 amount of gas, because you want to have 1 kilobyte. That is 8,192 gas per kilobyte, compared to the 640,000 gas per kilobyte in a storage variable. That is around 78 times less gas at the time of writing this overview. I don't know if they changed something, but it's definitely going to be a lot less gas to emit an event than store it in a storage variable. So that is something that you kind of should keep in mind when you are working with smart contracts and make your users' life easier. There's actually a really cool game which uses events as the text storage, but only saves the path to the events or to the adventure nodes on the blockchain. It's open source. It's a crowdsourced text-based game, but I think it's a really good example of how you can leverage events as data storage. Yeah, events in decentralized applications, they subscribe and listen to these events. The events you will later see, they're inheritable members of a contract, and indexed parameters can be searched for or filtered for, actually. Now, the key takeaways for you should be events are used for return values, as you saw it, data store or trigger. They cannot be retrieved from within smart contracts. Very, very important to understand that. You can mark up to 3 arguments as indexed, and they can be searched for. And events are really cheap. They're really good, and you should use them. All right, that's enough from my side. I will see you in the next lecture. Now I want to talk about another specialty of Solidity, and that is modifiers. And I want to kind of explain it to you with together with inheritance. Now consider the following smart contract example. I want to walk you through the things. I'm not going to write it from scratch, but I'm going to modify it with you together. So what this smart contract example does is pretty much the same as our previous token example. We have one person who is going to deploy this smart contract, who gets 100 of our tokens, and we have the send token functionality. So you need to have some tokens in your account, but we also have something else, that is you can buy tokens. So this purchase token functionality lets you purchase tokens. But we also have, for the owner specifically, a function to create new tokens or burn tokens for the owner himself. And the way this works is with this require statement. So the message sender must be the owner, or else you're not allowed, and it's gonna just stop the execution. Now, if you're gonna give this a try, head over to the deploy and run transactions tab. I'm gonna do this in Remix, and I'm gonna deploy the example.
and I'm going to check my token balance. Great. It's 100 tokens as we specified in the constructor. And now I am going to create a new token. And now my token balance is 101. But how about the other person over here? How much token does he have? He has 0. And what happens if he clicks create new token? Well, obviously the require statement will evaluate to false and it will fail. But he can purchase tokens, right? So if we are going to say our token price is 1 Ether and I'm going to send 1 Ether to the purchase token thing, then we have 1 token. Now that works fine. And well, the functionality is there, but we have code duplicated, which we don't need to duplicate. And that is these 2 require statements. And the way these modifiers work is they can modify a function to basically inject code into it. Let me show you how this works by defining a modifier. So the modifier starts with the keyword modifier, and then we could say only owner, and then we can also have arguments there. And then we say the owner needs to be the one who is calling this function. And we also specify with an underscore and a semicolon where the rest of the function content goes. And the way you're using these modifiers now is by going into the actual function where you want to use them and define them next to the visibility specifier. So you say create new token, only owner, and then you can remove this require statement as well as over here, only owner. And what will happen here is that when this function is executed, actually when the contract is compiled, it will take this require statement, it will put it, actually it will not put it over here, it will take the contents of the function and put it over here and then put everything back into the function itself. So when you call this function, it's basically saying require message sender is owner blah blah, and then the function content, same as here. So when we are going to deploy this now, let me just remove everything. We are going to deploy this now. And now this one is our owner because we used that one, the second account, to deploy the contract. So I'm switching over to the first one and I hit burn token, get the same effect as before. Now we have another problem over here, and that is we have a lot of functionality in a smart contract, which could actually be reused if we just put it in another smart contract. For example, this owner's functionality. So if we would put this only owner functionality in another smart contract and then just use it within this smart contract, well, that would be a lot more clever. So let's just define another contract over here. That is contract owner. Here we have an address owner and the constructor that sets the owner is the message sender. And then we have the modifier, only owner, and then just copy basically the whole thing. Actually, let me cut and paste this over here. Now you see, well, it's complaining that the modifier only owner is not found. But let me update a few more things in this smart contract before continuing. So now we are getting a lot closer to the example, to the smart contract example that we had before with our minimal token. We just added like 2 more functions, and we have the visibility, we have the modifier only owner in addition to the visibility specifier. But how can we use this? With inheritance. And the way this works is you say this smart contract has a base smart contract, and that is owner. So now it's going to take all the functionality from that smart contract and inherit it into the inheritance modifier example smart contract over here. Now be careful if you are going to deploy this. Now you have 2 smart contracts in your contracts dropdown. So you have to select the right one, hit deploy, and of course you can just try burn tokens and it will have the same effect as before, just that this owner smart contract, you can use it in any other smart contract as you like. But right now we have another problem. That problem is we have this in the same file. And that's kind of inconvenient. So every time you want to use this owner smart contract, you would have to import this file over here. So the way we are going to do this now is we are creating a new file, and we call this maybe ownable Solidity. And then we are going to take our whole content, paste this over here, and then we can remove this contract. So we just have the SPDX license identifier and the owner, but we need to import ownable Solidity here. So from our file ownable, we are going to import the contents over here, and then we can again deploy the contract. Be careful that you select the right one over here, the drop down. Burn works with the owner, but without, like with the wrong owner, it doesn't work. And this is a fairly common structure of creating ownership. You will later see also some contracts out there define this, and also the default workspace already defines an owner functionality over here. So that is the basic example of how you can make something ownable. The more advanced example for ownable smart contracts are access lists, and OpenZeppelin has actually a really good implementation of that. So if you need some more permissioning models around that, but the basic one is ownable. And our lecture over here is not even about ownable. It is about inheritance and importing and modifiers. So I hope that makes sense, how you can structure your smart contracts slightly differently by just putting everything into its own components. So you have reusable smart contracts and you don't repeat yourself, which is always a good paradigm to follow. Now it's time that we summarize a little bit what we did in the previous lecture, and I want to talk about the Solidity architecture, modifiers, inheritance, and importing, and also a little bit about the virtual and override keywords. Now, first of all, inheritance. Solidity understands multiple inheritance. You can use polymorphism, and for inheritance, it uses the is keyword that you already saw in the previous example, where we have a contract that is then extending the base contract owner or owned that we used. And it goes, if you have multiple contracts, then it goes from the most base like contract to the most derived contract. So in case, let's say, you have a contract X, and that contract is the base contract for a contract Y, and that is the base contract for a contract Z. So Z would be Z is Y, and contract Y is X, and contract X is nothing, it's just a base contract. Then for a contract A, you would have to define the most base-like to the most derived contract. That's what a lot of people confuse, and you will get compiler errors anyway, so you will figure it out. But it is in this order normally. You can use the super keyword to access the base contracts functionality, which we haven't used yet, but you will see it in the source code out there, and you probably will see it in the next lecture, where we are talking about the ERC20 token from OpenZeppelin. And if you compile a contract that is extending a base contract when inheriting a base contract, it is just one single contract that gets deployed. It's not multiple contracts, and then they are using some sort of interaction. It's just one contract. It's all just in one bytecode. There are two keywords that we have not used in the previous lecture, but I still want to talk about it. And it's really not that complicated. If you have a function, for example, the function name over here, that is used in a base contract, and in the base contract, you actually want this function in a contract that inherits this base contract to be able to override this function, then it needs to have the keyword virtual. So if I'm extending, let's say this is a contract A, and I'm extending this contract and I want to write my own name function, then this name function in the base contract must have the keyword virtual. Same as if I'm overriding this function, then I need the keyword override. So a function can also have both keywords, override and virtual, because maybe that's an intermediary contract, right? It's maybe extending already a base contract, so it's overriding the base contract's functionality, but it itself also can be overridden by a contract that inherits this contract. So then you have both. Modifiers, pretty easy once you have used them. They change the behavior of functions, and you can use them to automatically check a precondition or something. We had the only owner modifier, but there's tons of modifier you can define yourself. I always think they look a little bit like go-to statements from very simple go-to statements from BASIC or something like that. But okay, it is a modifier. You can use them. They usually, if you use them not too often in your contracts, they can increase readability, and especially they can help you with don't repeat yourself, dry. Yeah, you will see them a lot out there, especially for owner functionalities and access lists and maybe pausing functionalities, so that contracts can be used if they're not paused, if the owner is interacting with them, if certain people are interacting with them. So you can have a check of automatic preconditions. So when we're talking about importing of files, you can have several smart contracts in one single file. There's nothing against doing that. It's just not always good. Sometimes it's better to structure them, one contract per file, and the file name has the same name as the contract, but it doesn't have to be like this. So you can have several contracts per file. And then you can import file names. You can import the whole file name. You can import all members of a file name if you have several contracts in there, or you can just import specific members of a file name, very much like you know it from JavaScript. And that's it pretty much. Inheritance and importing are a perfect way to have basic functionality that you can extend upon, and modifiers are a great way to check preconditions. In Solidity, there are a number of really handy units or already predefined constants that you can use within your code. We have already used them before, but we haven't really formally introduced them yet. So it's going to be a quick lab, and I just want to quickly show you what I mean. Now, let's say you have, a modifier that asks the user, or that makes sure that the user sent between 1 and 2 ETH to a smart contract. Okay, it's a totally made up example, but just roll with it. I'm going to show you what I mean. So let's say you have a modifier between 1 and 2 ETH %, and you want to make sure that the message value is greater or equal than 1 ETH and smaller or equal than 2 ETH. Now there's there's actually 3 ways to write that. Number 1 is 1 ETH, and the message value is in way. So you would have 1 and then 18 zeros, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16, 17, 18. 18? Is it 18? Oh, it's 17. Now it's 18. And you want to make sure that message value is smaller or equal than 2 ETH, and that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, let's say this is a require without any kind of message, and then you continue with the code here. Now, obviously, first of all, that is really hard to write and really hard to read. I mean, how can you, if you're an auditor and you see that, you think like, are they going to, are they kidding me to write it like this? So there's a different way to write it. Now, one of them is obviously 1E18. Okay, so now you have defined like 1 to the power of 1 times 10 to the power of 18 and 2E18. Okay, fine. But there's an even better way. And that is to use the monetary or ether units that are already defined. So in this case, you can write 1 ether and 2 ether. And what will happen is that it takes this number literal and it multiplies it by 10 to the power of 18, because that is basically defined as 10 to the power of 18. It's just another word. So it is almost like defining a constant ether and then multiplying by it, but it works a little bit differently here. So it's just one ether. That's it. That easy. And everybody knows what's going on. There is other constants or other units that are available. There is ether, there is gwei, there is wei. And you will think like, oh, why should I define wei if it's clearly like only one? Because readability, it's much easier to read. Okay, and then there's also other things which are for time units, and they can make your life much easier. Let's say you have, I don't know, an auction contract or a crowd sale contract, and you have maybe an unsigned integer that says run until timestamp, and maybe you have an integer that says start timestamp, and you want to start this crowd sale in X days and run it for 7 days. And there's multiple ways to achieve that. Let's say you deploy this smart contract and you have to start in days. So you want to start in X days and run it until start in days plus 7 days. And you know that everything in Solidity, the timestamps are Unix timestamps, so they are in seconds. So you kind of have to make sure that you multiply everything in a way that it gets into seconds again. So the start timestamp is the block timestamp. That's the current timestamp at the time where the block is mined, plus 7 days, plus X days. So the start in days, times, well, 24 hours per day, 60 minutes per hour, times 60 seconds per minute. And then the run until timestamp is the start timestamp, and that runs for 7 days, right? So we said 7 times 24 times 60 times 60. So this way we would achieve what we wanted to have. We start our whatever it is in X days, so in starting days, and we run it until start timestamp plus 7 days. Now let me rewrite this with the predefined units for the days. Start in days times 1 days. And over here we have not even times 1 days, we have 7 days, because it just takes the number literal here and it multiplies it by, well, 24 times 60 should be 86,400 if I have this correctly in my head. But yeah, it basically converts it into days. Arguably, it's probably much easier to read that than going through the conversions and through the multiplications yourself. You can also divide by days. And there are a number of time units available. The easiest one and the most basic one is seconds. This is basically 1. Then we have minutes, then we have hours, and then we have days and weeks. There is no years. It was removed because it is, well, hard to predict the years, because there's not every year equals 365 days. And then you have days where you have leap seconds and so on. So those things, take them with a grain of salt. Those are static values that are just multiplied with whatever number is in front of them. All right, that's it. Off to the next lecture. As you know, data on the blockchain is basically stored forever, but the state itself is not, you can modify the state. And that means you can also erase information from the current state. You cannot erase it from the blockchain. You can always go back, but going forward, you can erase certain things. And in this case, I want to show you how you can destroy a smart contract from the current state with the keyword self-destruct. Now, one thing up front, there's a lot of discussion already for a few years now that they want to remove Self-Destruct. At the beginning, Self-Destruct was implemented to remove clutter from the blockchain, to make the state smaller or make it easier to do state pruning or whatever. And it turns out a lot of people are actually not using Self-Destruct, and instead it was used to exploit smart contracts because they had bugs, and it was another several $1 million issue that popped up. So use it with, with care. Be aware that it might be removed. I still want to show you what it does because right now it's in there and you can use it, and you will see it inevitably in smart contracts popping up, and you might wonder, what is this? So I have an example here that says start, stop, update example. It has one receive function, so we can send money to that smart contract, and it has a function destroy smart contract, which is public, doesn't do anything other than calling self-destruct over here. And that one receives one address, one payable address that gets the remaining money that is stored in the smart contract. One thing that is important here, self-destruct sends the money to that address no matter what. If that address over here is not my own wallet address, but another smart contract, then it will just send the money there no matter if that smart contract has a receive function, a fallback function, a payable function, or anything. It will be credited to that address. Okay, having said that, let's run with an example, because there is something that a lot of newcomers to Ethereum will surprise. Let's go over to the Send, Deploy, and Run Transactions tab. I'm going to deploy the smart contract, and I'm going to send, we are generous, we send 1 ETH to the smart contract's receive function by hitting transact over here. Now we have the value. Now we have 98.99. Okay. And now we hit destroy smart contract. And what happens is our ETH went back to our address, because whoever calls this function now can not only destroy the smart contract, obviously you want to have some control structure around that in real smart contracts. This is just an example to showcase self-destruct. Please do not use it without any control structure. So the question is now, we used self-destruct, but our contract instance is still there. What happens if we send another ETH there? Well, let's try that. Let's send another ETH to our smart contract. Why is this not working? Okay, we have sent 1 ETH to our smart contract, and we can interact with the smart contract. That is weird. Doesn't error out. And now we hit destroy smart contract. But we didn't get our ETH back. It's still 98 over here. Where is our ETH? What happened? So it turns out the state on the contract address is empty. What we did is we sent a transaction to that address, but that address doesn't contain any code anymore. So while you can interact with any address, you can send any kind of transaction to that address with arbitrary call data. Let me just paste this over here. That's the hashed function signature over here. But on that address, there is no more code running. So there's nothing that can interact with that code. So it doesn't even error out. It just does nothing. It receives the ETH, says thank you, but you will never get it back because now it's locked in that address because there is no code running. So be careful with the contract lifecycle. If you're using self-destruct, maybe you use it with auction contracts or with wallet contracts, or you give users some initial contract functionality that you deploy on a separate address. Be careful with self-destruct. There is also a way to redeploy smart contracts to the same address. It's not in this course. I have a separate small mini course about that. You can find it on ethereum-blockchain-developer.com in the mini course sections. It's called Upgrade Smart Contracts with proxy contracts, where I'm talking about 2 ways. The one is create2 with a create2 keyword. The other thing, which also uses create2, is so-called metamorphosis smart contracts. It's very advanced. It doesn't fit in here for purely learning Solidity right now. But if you feel like, head over to the advanced mini courses section on ethereum-blockchain-developer.com. It's free. And you can have a look at this. Before we are heading to the ERC20 token and the ERC20 token sale, I want to talk about one last thing, and that is source code verification. I think it's important to verify source or smart contracts on Etherscan and maybe also other block explorers. There's a couple of reasons for that. I mean, obviously you don't have to, but the bytecode is already out there, and is a lot more transparent for other people to possibly interact with your smart contract. Your smart contract could potentially handle multiple millions of dollars. So if you want anybody to trust your smart contracts and have it, in the open, in a transparent way, it's considered good practice to, open source the source code as well. Now, it also lets other people directly interact with the smart contract. And I'm going to show you now how that works. I have prepared an example over here in Remix, and we are going to deploy this to the test network where you have any Ether. Maybe at the time of recording this, I'm going to deploy it to Kovan. Kovan is going to be shut down, and I think there's another test network coming up for ETH 2.0. So please, whatever test network you have, use that one. Okay, you don't have to use Kovan exactly. Maybe you can use Gurley. So I have this smart contract over here. It's a very, very simple smart contract, and I want to show you two things here. Number one is it has a transfer function. And what it does is it transfers, like we had it before, in that mapping from the person who is interacting with that contract to another person some value. The person who is deploying that contract gets 100 balance, whatever that is, maybe a token or maybe something. And then it has another function, and that has some cryptic function name. And can be any function name that is maybe not known to Etherscan yet. Because what will happen in Etherscan is you are going to deploy that smart contract, and then we are going to interact with the smart contract. But Etherscan can guess the function name based on the function signature, because other functions or other contracts which are open sourced, where the ABI is known, have the same function name with the same function signature, and then based on the signature hash, it can already guess what function was used to interact with the smart contract, but it cannot guess it over here. So let's run with this, and we'll see in a minute what I mean. First of all, let's head over to MetaMask. If MetaMask is locked, then unlock it. And then we are going to deploy that contract. Just make sure that you are on a test network over here, not on the mainnet, because that could get expensive. So over here, there will pop up view on Etherscan, so you can open Etherscan. The transaction is not even seen by Etherscan, and now it's success. And then you will see from over here, we deployed a new smart contract. And what you will see next is that the contract is already known. And why is that? Because I was running an example before where I just wrote down the documentation for this video, and I verified the very same smart contract. The thing is, it even says it's a similar match source code. This contract matches the deployed port bytecode for the source code for contract on this address, which I used before to write the documentation. So let me change this source code slightly. Let's make this not a view function that returns anything. Let's make this a rogue function that sets the balance to 5 for a specific address. Now let's deploy this function, deploy the smart contract, and it will, Etherscan will not know what this contract is because the bytecode drastically changed because I changed the function name. So let me hit view on Etherscan again. And you have to change your smart contract a little bit that you use to verify this on Etherscan if you want to run with this lab on Ethereum-blockchain-developer.com. Okay, now we go there to the smart contract, and you see there is no little green check mark next to the contract, and it's just bytecode, and it asks you, are you the contract creator? Verify and publish your contract's source code today. Before we are doing that, I want to interact with these two functions, the transfer function and the some cryptic function name function. Let's start with the transfer function first. Let me just see, is the 0x9a, it's this smart contract over here. First, we are going to transfer to our second address over here in MetaMask one of the tokens. Let me just select copy this address over here to one token. Okay, confirm this transaction. View on Etherscan. Might take a moment, and then we see over here, if we look at the details, the input data, function transfer. And why can they know that it's the function transfer? Because other smart contracts have the exact same function, and it's the exact same function's signature. So, the hash, it has no collision. It was once hashed, and they just look in their centralized database for that method ID or function signature, and they find its transfer address to uint 256 value. And we send to this address this value. What about the other cryptic function name? So let's hit that one with the same address. And let's have a look at this transaction. It's still indexing. If we click to see more, so one thing that I also need to change is the some cryptic function name address over here, because I used it also before. So I will just call it some cryptic function name ABC. So I have not used this before in my previous contract that I verified on Etherscan. Let me quickly redeploy this smart contract. Otherwise, if I send a transaction now to this address, to this function, some cryptic function name, it will also obviously know the function signature from my previously verified smart contract. Just waiting over here. And then I will quickly interact with this some cryptic function name ABC. Function name ABC. Let's interact with this one, and then let's open the transaction on Etherscan. And you see here the input data. It doesn't know anything about this input data. All it knows is, well, that's the function signature, and there's maybe an argument sent in, but what it exactly is, without the ABI, without knowing the data type, it cannot decode this. So how are we going about verifying this smart contract? First of all, you have to be logged in. I'm already logged into Etherscan. And yeah, if you're not logged in, then you have to go to Etherscan and log in over here on the top right corner, or register. It's free. You don't have to, do anything or pay anything. You just have to sign up with your email address. Then you go to your contract, and you go to the contract source code and hit verify and publish. From over there, you select the compiler type, and you will later see, we are going to do this once manually, but you will later see how a script or from Truffle, Hardhead, Foundry, you can do this basically from the command line. Right now, I just want to do this once manual and just show you around in Etherscan, because it's pretty cool. So we're going with a single file. We are selecting the compiler version. It's 0816 that we used. So if you use a different compiler version, then select the appropriate compiler version and select the license. It doesn't parse the license from the SPDX license identifier file, at least as far as I know. Select the appropriate license for your contract, and then head over to Remix, copy the source code, paste it over here. Well, we had no constructor arguments. We are the tractors. Well, you have probably a different captcha. The thing is, there is another optimization over here on the top right corner. You have to have a look in your Solidity compiler in the advanced configuration if the optimizations are enabled. If they are enabled, you have to hit optimization yes. If they are not enabled, well, optimization no. And then verify and publish. Well, that takes around 30 seconds. And once that is verified, you can see over here successfully generated bytecode and ABI for contract. You can scroll down, there's the contract bytecode and the contract ABI. And now Etherscan knows your contract and it has read contract and write contract buttons, which is very convenient. So with the read contract buttons, you can directly interact with the getter functions, with the view functions and pure functions. With the write contract section, you can connect your MetaMask, which will on your side pop up with allow connection and so on. I've already done that. And then you can directly interact with MetaMask. So I could over here send a transaction to my smart contract to this some cryptic function named ABC directly from MetaMask the way I'm doing it in Remix as well. Now, sometimes that is very handy. You don't need any sort of front end or whatever to interact with smart contracts if they are verified on Etherscan. So let's talk about the mother of all tokens. Basically, the first one that got really famous a few years back, the ERC20 token. You know where the ERC20 name actually comes from? It has an interesting history. Maybe you came across the RFCs in the world of traditional ID, RFC and then a number. RFC stands for request for comments, and it is the traditional way to ask in the IT. You have a standard and then you post it somewhere and other people, other peers can comment on this standard until it's actually becoming a standard. And ERC is the early version of this for Ethereum request for comments. And the number 20, which I have over here, the ERC20 token standard from the Ethereum.org website, is the 20th request for comments that was posted by someone. And these someones are not anybody's. This token standard was posted by Fabian Vogelsteller and Vitalik himself in 2015. And what they wanted to do is they wanted to have a token that represents basically any fungible thing like reputation points, lottery tickets, fiat currencies, an ounce of gold, anything that you can think of, maybe a coffee. So maybe we go with coffee in this example. And those things are fungible things. So it doesn't matter if you have token number 1 or token number 1 million, very much like doesn't matter if you have a euro note or a dollar note with the serial number X or serial number Y. It's always going to be worth whatever denomination is on there. So internally, those tokens, they do not store any serial number. They are indistinguishable from each other. So how does that interface look like? If you scroll down a little bit on that page, then you see a couple of methods and events. A token has a name, it has a symbol, it has a number of decimal places. As you know, Ethereum doesn't have any decimals or cannot work with floating point precision or whatever. So you just put the decimal point at a reasonable high number so you can work with decimals as well. Has a total supply, so how many tokens do we have? It has a balance, so a user has a balance, which we already had in our sample tokens, very similar, but a little bit different. Transfer from, approve and allowance. And then there's also 2 events that are emitted during transfer and when you approve somebody else to use tokens in your name. Now there's a web Python example, which I'm not going into now. I'm instead opening the EIP20 token standard over here, just to go through these again. Some of these functions are marked as optional. most of the ERC20 implementations have those functions all implemented. So when we are opening the OpenZeppelin implementation, and don't open the implementation from this website, because this one, if I open this now, this links to a very old version. It's like Solidity version 0424. It's a very old commit. But if we open a recent version of the OpenZeppelin contracts, OpenZeppelin is a company, I think it's a spin-off from Consensus or a subsidiary. I'm not sure about that. But they provide audited versions of their smart contracts, of smart contract token standards and so on. So it's a very good idea sometimes to get at least inspiration when you want to develop something yourself from them. So this one is the current one, which is in the current master branch. Maybe yours looks a little bit different. Essentially, it's the same thing. You have a constructor, you give the token a name and a symbol. Yeah. And it returns the name and the symbol. The decimal places are now fixed at 18 decimals. I think that represents IEEE standard for floating point numbers, but don't nail me down on that. Just remember, it has 18, can go to 18 decimal places. And some older contracts have a variable number of decimal places, so don't take this for granted. There's a total supply, balance off, transfer allowance, something which we didn't do yet. So you can give somebody else allowance to spend tokens in your name. Transfer from, if you have the allowance to do that, and increase, decrease allowance. And then you also have mint and burn, which are internal functions. So in case of OpenZeppelin smart contracts, they are fixed. They are fixed supply. So if you don't add your own mint and burn functionality, they are fixed supply. If you add them, then they are variable supply. So because you can mint and burn more or less tokens. Now OpenZeppelin also has a contract wizard, which I want to go into in a second. First, I want you to pay attention to that contract. Most of those functions are virtual override. So there's a base contract somewhere. I think it's the ERC20, which defines the base functionality, and then they are virtual. So all of those functions can be overridden from a contract that inherits this, or that uses this contract as a base contract. And that is exactly the idea behind those OpenZeppelin contracts. They have in docs.openzeppelin.com/contracts, there you find the docs, and as a second point, they have a new thing, which is a wizard. And you can click your own token together if you wanted to. For example, you could have an ERC20 token with a token name and a token symbol. You can make it mintable. You can give it special roles or ownership. You can even make it upgradable with transparent proxies, which you didn't do yet, or you can change the license type. So all of that is something that you can click together. So let's go through those things one by one, and I will explain a little bit what happens here. So first of all, let's go, and let's remove this. This is the very basic version of a ERC20 token contract. So let's say you want a token contract that is called my token and has the symbol name MTK. In this case, just copy this, and I could go over here to remix, and let's say sample token. That's all. Nope, not like this. Copy to clipboard. Okay, the copy to clipboard version won't work, so let's copy this one over here. Okay. So what happens is it will import the OpenZeppelin contracts token ERC20 Sol from the NPM library. That happens automatically in the background with Remix, and that is very convenient. So now I can just go ahead, well, deploy this because my no, not this one. I want to deploy my token. Be careful that you select the right one from the dropdown. Deploy this one. And when I hit name and symbol, I get the right ones here. Now the problem is, right now we have no supply. We have 0. So somehow we can pre-mint maybe 1,000 tokens. Then we will get automatically in this wizard, it's calling automatically the mint function for us. And we are getting 1,000 and then times 10 to the power of the decimals. So with 18 zeros behind. This is where you have to be careful a little bit, because everything is denominated in like without any decimals. You have to put the decimal place where it actually belongs to. Now let's say we don't want to have a fixed token supply. We want to have a variable token supply. Let's not pre-mint anything. Let's make this mintable. Automatically, it will choose the access control ownable. So what happens here is that it will import the ownable smart contract from OpenZeppelin, make this one ownable as well, and only owner can call the mint function. Now, see over here, it is the mint function without the underline, and it's a public function, visibility public, so you can call it from the outside. Whereas the mint function with the underscore in the front is an internal function, so it can only be called internally from your smart contract. Then burning works a little bit different, because burning is something that the user can do himself. If we add burnable, then it will import this OpenZeppelin contracts token ERC20 extensions ERC20 burnable.sol. And if I open this one, then you can actually have a look how that looks like. It is implementing two functions, burn and burn from, and that here depends. If you are calling this yourself, then you can burn tokens. If you are calling this from somebody else, then you need the spending allowance again. Now let's remove this here, and let's quickly talk about the difference between ownable and roles, because there's quite a lot of people just use ownable. And I personally, I'm a huge fan of roles because they allow for a lot more flexibility. And in this case, what happens is that the wizard here will automatically define a minter role for you, which is basically the Kazakh hash of the word minter role. It's a constant. And then it will extend the access control smart contracts from OpenZeppelin. And what they are doing on the very basic level is, instead of having only one role, which is the owner, it can define several roles. So for example, I can grant myself here, the person that is deploying the smart contracts, also the minter role. And then I can look here for only role, minter role. So if the person that is interacting with this mint functionality must have the minter role. It's actually quite straightforward once you used it, but it allows for a lot more flexibility, because now you can also define burner roles or payment roles or pauser roles. So if you make this pausable, then we can say this smart contract can only work, like you can only transfer tokens here when it's not paused. And you can only pause it and unpause it if you have the pauser role. With the owner, you only have one role, but now you suddenly have several different ones, fine-grained access control for your smart contracts. So why don't we deploy a smart contract now? Very simple one. Maybe a coffee token, maybe something that represents a coffee. So let's just remove this one. Let's call this coffee token, maybe CFE. Bring this over to Remix, copy and paste. And let's have a look what we want to do here. Now, first of all, we want us to be able to mint tokens. So somebody's coming to our cashier and he wants to buy a token because he wants to have a coffee. Maybe, it's one of these festivals where you have the cashier somewhere else than the actual person, the actual barista. So in this case, the person comes to the cashier. He's paying $2 and the cashier is going to mint a token for his contract address. Fine. And then he's going to the barista And the barista is going to make a coffee, but he needs to pay somehow. So we want maybe to have another function that is buy one coffee. And over here, we are going to burn from the message sender. And this one is only a helper function. It's the same as message.sender. It's coming from the context. So don't be surprised by the underscore message sender brackets open, brackets closed. And we want to buy one coffee. Not an unlimited amount, just one. But maybe we also need to emit an event. Coffee purchased. For that person. So we are going to emit coffee purchased for the message sender. And maybe that person can also give other people the allowance to spend coffees in his name. So why don't we just add also a function, buy one coffee from then we take the spend allowance function. We are spending from that person. It's calling an internal function, spend allowance from the ERC20 token contract over here. From the base contract. You can see it also in the transfer from function, from who is going to spend it and the amount. So if somebody's calling the increase allowance first, then it will increase the allowance and later you can spend it. So you need to decrease again. Then we are going to and then we are just burning from that account one, but then we are also, let's just extend this event here. Indexed buyer. Coffee purchased, address, indexed. So we are spending it from this person. And over here, we are spending it from ourselves. What am I doing? Okay, let's give this a try. You see in our drop down over here, we already have a lot more tokens, a lot more smart contracts now. Let's make sure that you choose the right one. Deploy this one. We can, well, for us, let's mint one token for the second contract address. So we click on this one and go back. Let's mint 10 coffees. So he can go. Actually, imagine it like this. It's not a barista that is standing there. Let's say it's a coffee machine. So you go with maybe your phone, you have MetaMask on your phone, and you are scanning that QR code on that coffee machine, and you want a coffee. And the coffee machine will have a QR code that is encoding a transaction, so it calls buy one coffee. And this buy one coffee function from your smartphone will then burn this thing, burn the token, and emit a coffee purchased event. And the coffee machine itself, connected to the blockchain, will listen to that coffee purchased event and then simply make a coffee. This is how this can work. Okay, now we have our second account. We have given him 10 coffees because we are very generous. Let's see if he really has 10 coffees. He has 10 coffees. And now let's simply say we want a coffee. I want to buy a coffee. Let's see if he has now 9 coffees. Yeah, and the coffee machine is working. I can hear it in the background. Of course, it's not really a coffee machine. But this is how you can actually connect hardware, and the hardware itself would know what to do because you already purchased the coffee. It's very much the same as with money. You put €1 in or $1 in, and you get something out. And the same is here. You just have it in a digital wallet on a shared ledger. Now, obviously, the last thing that we want to try and avoid is that somebody needs to come to our cashier and give us money. So we want some sort of functionality to give out a number of tokens to people when they purchase them for a specific price. And that's what we are going to do in the next lecture. We are going to implement our ERC20 token sale. In the previous lecture, we were integrating this coffee token, and in this lecture, I want to integrate a token sale smart contract, which is not directly integrated into the token contract itself. What we are going to do instead is we are going to give this token sale contract the allowance to spend tokens in our name, and this token sale contract will transfer tokens to someone if he's going to give us let's say 1 Ether. It's going to be an expensive coffee, but I think it's going to make the point clear that if you can, give other smart contracts the allowance to do something in your name, then they can actually also work with those tokens and do something with it. So let's get started. Well, first of all, we need to have a contract called token sale. Okay, and over here we are going to define a token price in way, and we are just going to make this 1 Ether. Obviously, you can make your coffee price as small or as big as you want to. I'm rolling with 1 Ether now, so that's 10 to the power of 18. Don't forget that. And then we need somehow the token, and we could do several things now. We could define, we could import the other token contract, or I'm just going to define a contract over here that is called ERC20 with the most default functions from over here. And I'm just, what do we need here actually? We need to transfer tokens. Actually, we need to transfer them from I think we have to make this abstract now. And then that one virtual. And then we also need the decimals. That's what we need. Decimals. View public virtual view uint8. Okay, and we are going to define this as ERC20, our token. And then we are going to constructor. We have an address for the token. Oh, obviously we have an address token owner. So the token owner is hopefully the message sender. I'm just assuming this here. And the token is an ERC20 token running under this token address. Okay, fine. Let's make this public so we can actually see this. We can work with this. Okay, and then we want to have a function that is basically called purchase coffee. And this is a payable function, payable. And we are going to, first of all, require that the message value is larger than the token price in way. Not enough money sent. And then the person can also send, more than 1 ETH. And we are not really enforcing anything here. The only thing I kind of want to do is, if he's sending 2 ETH, then he's getting 2 tokens. But if he's sending 1.5 ETH, then he's getting 1 token, and we send back the remainder. So it's basically a simple calculation. That is tokens to transfers the message value divided by the token price in way. So we know how many tokens we need to transfer, and the remainder is the message value minus the tokens to transfer times the token price in way, if I'm not mistaken. I think that should do the trick. So now we are going to transfer token.transfer from, we are transferring it from the token owner to the message sender. We are going to transfer tokens to transfer. And then we are going to send the remainder back. Payable transfer remainder. Send the rest of the money back. Okay. So let's give this a try. First of all, we are going to deploy our token. I restarted Remix in the meantime, of course. So we have to start from scratch here. Coffee token, deploy that one. And let's say we are going to mint for this address over here. We are going to mint 100 coffees. Okay, that person purchased 100 coffees. So now this one should have a balance of 100. Well, that is obviously not the right amount. We made a mistake over here. We have to mint actually times 10 to the power of decimals. And I think that was my mistake here. Oh, not the amount. Very tricky, very tricky. 1 times 10 to the power of decimals. Otherwise, we're sending like 0.00018 zeros tokens. And it's a pure coincidence that the decimals here are 18 decimals. So you could actually write 1 ether. Just remember that. Times 10 to the power of decimals. I think that should do the trick. So let's just redeploy this. Coffee token, deploy. I already have this in my clipboard, this address. We are going to mint for this person 100 token. So let's check the balance off. Now that looks better. That's how the balance actually should look like. Because every front-end Etherscan, if you deploy it to any network, and if you verify the source code, it will divide the balance by the amount of decimals. Okay, so now we have our token contract deployed. Now we need to deploy our token sale contract. So over here, we obviously also need to multiply this times 10 to the power of token.decimals. Now it should work. Okay, let's see that. We have our token contract running on this address. So we are going to paste this over here into the constructor. Hit deploy. And then we need to give this smart contract the allowance to spend tokens in the name of the person who just got the 100 coffee tokens. So let's do that allowance. We are, no, this is, where's increase allowance, increase allowance is here. So we allow this person to spend let's say you can spend 5, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. The other way you could do this is web3.utils.twoway and then in quotes 5 ether. So you get the correct number. So, and now we can maybe go to the third account and send 1 ether to the purchase function. What happens? Insufficient allowance. Did we send the right gift? Did we give them the right allowance here? Who sent this? Now let's check the allowance. Where is the allowance function? Owner is this one, and spender is this one. What do we have here? We have this allowance. Insufficient allowance. Oh, I think we used the wrong token owner. I think we used the wrong account to deploy the token sale smart contract. So I'm going to use this account now to deploy the token sale. And I'm giving this token sale contract the allowance to spend money. And now we can switch over to the new account and send 1 ether to the, why is there no, you have to be careful. Sometimes in Remix, the value is 0, even though I clearly put in 1. So look at this. Maybe it's the scroll event. And now we have our token coffee purchased. So let's have a look. If our account now over here, copy this account address. What is the balance of this account? It's 1. We have purchased 1 token. Now, obviously, we cannot do this repeatedly more than 5 times because the token allowance is just 5. So let's try to purchase. Look at this. Maybe somebody from the Remix team sees this. Purchase 5. And it doesn't work because we have insufficient allowance. But if we purchase 4, then we can purchase the remaining tokens that are still available. And that's my attempt for a simple token sale. Obviously, it's not an English auction. It's not a Dutch auction. It is not any kind of time-based auction. All it does is it is a fixed price auction that runs forever until the allowance is depleted. But it's still hopefully showcasing the architecture where one smart contract can do something with another smart contract, and it's all address based. All right, that's it. I hope you could, well, get something from this lecture, and let's wrap it up, and I'll see you in the next one. I know a lot of people having quite an aha moment after developing their tokens. It's not as sophisticated as it looks like from the outside. And after knowing most Solidity functionality now,
I'm sure you can read and write all kinds of smart contracts out there. Now that you have a token sale going on, well, of course on a test network, why not post it on your LinkedIn or wherever you're active? Make sure you have published your code to Etherscan and also put your content on GitHub. Then maybe tag me on LinkedIn. I'd love to see your progress. Well, if you're not on LinkedIn, doesn't matter. Join our Discord or maybe just tell the progress to your friends and colleagues. Not a lot of people know how to develop an ERC20 token in this world. In the next section, we are going one step further. We're going to develop an NFT using the ERC721 token standard. But instead of developing everything manually, we're going to take an audited contract template from OpenZeppelin as a starting point. It is the last big Solidity section before moving off-chain. So why not take a break before moving on and maybe recharge your batteries a bit? But now enough from my side. I will see you in the next section. I know, the NFT craze, it's somehow over, but another craze will start definitely. The question will be, are you prepared? Have your knife sharpened and the tools ready to succeed? Or are you going to look into the right tools only when it's too late again? In this section, we are taking NFTs or the ERC721 token as an example implementation for learning Truffle, Hardhat, and also Foundry. You will learn about ERC721, ERC777, and ERC1155 tokens. You will dive deep into each of the development frameworks, Truffle, Hardhat, and Foundry. If you hang around on Reddit or on other forums, you will come across a lot of polarizing comments. They suggest Truffle is cool, or Hardhat is bad, or Hardhat is cool, but Truffle is bad. Now, Foundry fans suggest Foundry over everything else. I'm not buying into this, and neither should you. Because each of the frameworks or toolkits has its very own strength, and some of them also have weaknesses. As a blockchain developer, you will inevitably come across all three of them, and I think all three have a very specific place in the developer landscape. Let's get started by deploying our own NFT manually and showing it on OpenSea before moving on to offline development. Before we are now getting to the actual implementation, let me get the elephant in the room out of the way. That is understanding the ERC721 token. Now, if you've already looked into the ERC721 token, then there's probably nothing new that I'm going to tell you. It's basically an ERC20 token where each of the tokens has a unique ID and can have an URL for more metadata. Now, if you look at this EIP 721 on the ethereum.org website, then the simple summary actually summarizes it all. It's a standard interface for non-fungible tokens, also known as deeds, because it actually has its roots in real estate deeds, which is a big misconception that like the NFT metadata, for example, should be immutable. It should not, because when you are looking at real estate deeds, then they can change. So the metadata needs to change. And it's just who owns that particular apartment, real estate, or whatever it is transferable, but the metadata then also needs to update or maybe can even be extended. A good practice is to put the metadata, which is just a regular JSON file, somewhere on a regular host, but it doesn't have to be. It can also be immutable if your token requires that. So it's up to you to actually set that. You see here the standard ERC721 interface. You see probably a very familiar transfer approval events. They just have an additional token ID at the end. So everything that belongs to a specific token, like transferring it or allowing it to spend, is for a specific token ID. It's like deploying a separate ERC20 contract, which is then just having one token to a separate address, but instead of having several different addresses, you just have it in one address with one smart contract who can deal with token IDs. Now, the other token, which we are going to discuss probably another day, is the
ERC1155 token, which is then an NFT where each of the tokens can have several amounts in addition. Like each token ID can have several ones of the same token ID. But let's stick with the ERC721 token for now. The other thing which is confusing to a lot of people is the token ID itself. The token ID, if I can find it, the token ID is identified by a unique uint256. So it has to be a uint256, which shall not change for the life of the contract. So you cannot just have a token ID 1, which suddenly becomes token ID 2, which also means that the pair address and token ID is then a globally unique and fully qualified identifier for the specific asset on the Ethereum chain. It doesn't have to start with 0. It doesn't have to start with 1. It doesn't even have to be consecutive numbers, but it may start with the ID 0 and simply increment by 1 for each new NFT. But you shall not assume that ID numbers have a specific pattern to them. It's important to understand that. The other thing is the metadata choices with the metadata extension. It's a mechanism to have metadata URIs or URLs associated with NFTs. The image sizes are taken from the image sizes from Instagram at that time, so that might have changed now. So you're not really bound to that. It's more like a recommendation, and the URI may be mutable. It doesn't have to be mutable, so it can change from time to time. They have considered an NFT representing ownership of a house, and it might be metadata of the house, like an image, occupants, that can naturally change. Now, enough of the theory. Let's get into the practice. Let's have a look at one sample NFT. So I have OpenSea opened here, and I have the artifact collection, which was, I think, recently bought by Nike. And I have token number 4 here. The way you identify this is OpenSea.io/assets/Ethereum, and then the token address, and then the token ID. And number 4, when you look at this, you have a couple of properties over here. And one is you have an image or a video in this case. You have a name, belongs to a collection. You have a description. There's some properties like artifact socks, collection genesis. And then you have an about section of the artifact collection itself. And then some more data like sales data, which is unique to OpenSea. Now, where's the data coming from? If we are opening that very address on Etherscan, which I have here, and then we are going to read the contract, and then we are looking at the token URIs for token number 4, then you will get an IPFS hash. IPFS, we haven't really talked about it yet, but IPFS is a distributed file system that is immutable in this case. So when you upload a file, it will create a hash of the file contents of itself, and then you get this back as a URL. IPFS is a protocol, but there are gateways, so you can actually read that without installing any node. And one of them would be IPFS.io/IPFS, and then the whole URL as over here. And what you get back then is a JSON file. And the JSON file has the exact same contents as the content over here on OpenSea. This is where OpenSea pulls the information from. It's as simple as that. Now, in order to create our own NFT, I was thinking about, giving you instructions to upload the JSON file somewhere, but then I thought, come on, we are Web2 developers. You probably have seen JSON files before. You can probably upload them. For convenience, I'm just going to host a couple of JSON files and a couple of images. So I created 4 images with DALL-E. This is number 1, spacebear 1, 2, 3, 4, and you're going to create a new token called spacebear token. So I'm also hosting the JSON on Ethereum-blockchain-developer.com / this current project / NFT data. and then spacebar underscore 1, 2, 3, 4 dot JSON for token number 0, 1, 2, and 3. How do we create these tokens? There's a couple of ways to do that. And the easiest one is probably to use the contract wizard from OpenZeppelin. Now, if you open the contract wizard on docs.openzeppelin.com/contracts/4.x/wizard, over here in the wizard section, then we already worked with the ERC20 token. Now let's get the ERC721 token running. We could name it spacebar, and then maybe call this SBR. And then as a base URI, we have HTTPS Ethereum blockchain developer.com / what I just told you, the whole URI without the spacebar 1 JSON. I just paste this over here. It's going to be mintable, so the only owner can mint. There's also auto increment IDs, what I said before. The ID doesn't have to start with 0, but for convenience, it's going to start with 0 and it's going to be incremented every time we do a mint. And it has an URI storage, and the URI storage over here just allows you to specify during the safe mint URI for the one token that you're doing. Otherwise, it would be this URI, so the base URL /1 without, or /0, actually the token ID. But if we want to have a different token URI for each token, then we can do this that way. So that's it. So we are going to copy this to clipboard. We are going over to Remix, and we are going to create a new file, and we are going to call this spacebar.sol. And let's paste this. This doesn't work. I know this. This didn't work before, and now it still doesn't work. You could open in Remix if you want, but then this will open the HTTPS Remix, and I don't like it. So I'm just copy and pasting like this. And then we need to deploy this somewhere and mint the token and then see if it pops up correctly on OpenZ. Okay, it's compiling correctly. That's a good thing. Now let's head over to the Deploy and Run Transactions tab. Let's keep it in the Remix VM. Just quickly test everything if it's working. Deploying and then minting. And let's mint a token for myself. Save mint. And then the URI is going to be spacebar_1.json. And then let's see if the token URI for token 0 is the right one. Yes, that's the whole URI. Just copy and paste it over here just to see if it really works. Yes, it works. And then from the metadata, it's going to get the image, which is this one. And then it's going to display it on OpenZ, at least in theory. Let's see if that works in practice. So OpenZ has 2 testnet implementations, at least at the time of recording this video. The one is for Rinkeby, if I'm not mistaken. The one is for Rinkeby, which doesn't work very well. And the other one is for Girly, which works better. I know in the previous videos, I have used Kovan to deploy smart contracts, but Kovan at the time of recording this video after ETH 2.0, after the merge, is going to get deprecated. So, and it's going to be shut down probably. So I'm recommending at this point to use Girly going forward. If you have no test ETH for Girly, then go back please to the test ETH, get test ETH section. I'm trying to have a faucet in there which actually works. If you still cannot get it done, then ping me somewhere and maybe we get something up and running. I also have only limited amount of Girly ETH. I'm usually trying to get them from somewhere. I have 0.47, more than enough to deploy this token. So if you're going to deploy this token now, deploy on Girly, send the transaction.
Takes a little bit. Let's view this on Etherscan. It's still pending. Okay, we have our transaction done, and now let's mint one token. Well, for myself, I like to have these tokens to myself. Space bear1.json, hit transact, and sign that transaction. And then we can take the contract is not going to be verified here, and I'm not going to verify this contract. But what we can do is we can take the contract address over here, copy it, and then you go to testnet.io/assets/girly/your address/0. I mean, not your address. I meant the token address, of course, not your own address. And what will happen is that it will pull the metadata and it will pull the image from the Ethereum-blockchain-developer servers based on the metadata URI that is in the token. And it will show it on the website. And now you could sell it, basically. That's how it works. There's a lot more to it, of course, like secondary sales commissions, and I have a separate section on that as a free mini course on Ethereum-blockchain-developer.com, which is not part of this tutorial. It would exceed what we actually want to achieve. We want to achieve to bring our development environment offline, and we are going to start with Truffle now. Before we can go crazy with Truffle Hardhat and Foundry, we have to install a couple of, well, prerequisites. Truffle and Hardhat are both JavaScript-based tools, and I tried to summarize all the prerequisites on the labs side here, so you can go through them and you can see if you have them, and if not, then install them. And I want to walk you through a couple of things now before getting started with Truffle. Now, the first one is, as you have noticed, I am developing stuff on Windows, but I usually do it in WSL. So the way this works, if you have never noticed it, is that you can actually run a Ubuntu or any other Linux distribution inside Windows, and it looks and feels very native. It is actually native. It just shares the kernel. So the way you get this, at least on my machine, is if you open the Microsoft Store and basically just type in Ubuntu and you can install it. I'm running on, I'm going to execute all the scripts on Ubuntu 20.04. It's an LTS, long-term support. I think it's going to run just fine also on Ubuntu 22 or any other Linux distribution that you can get, like a Debian. If you have it installed, you can also install the Microsoft Terminal. It's a nice application, but you don't have to. And you get this tabbed view and stuff like this, but you can just open Ubuntu from the start menu and it will launch into the Ubuntu distribution. And there you need to install a couple of things. This is Node.js. If you have it installed, you can check this by just typing in node-v. Make this a little bit bigger. I have also screenshots over here. I currently have Node version 14. You can run with Node version 16. I think you can even run with Node version 18. It will just work fine if you want to follow along exactly with this tutorial. Install Node version 14. I'm probably going to upgrade to Node version 16 anytime soon. And I have worked with Truffle before and Hardhat with Node version 16. So there wasn't a major difference. There was nothing that really did not work. You need the Node package manager, which you reach with npm. It's getting installed with Node together. And I'm going to show you in a second how you can do that if you don't have it installed. And you need Git. And Git is a source code versioning tool. If you are a web developer, there is a 99.99% chance that I empirically just made up that you know Git already. If you don't,
I would learn it anyway. It's not, learning Git is not included in this course, but there's tons of resources out there, and it's worthwhile your time, believe me. So how do you get these Node.js things if you don't have them yet? The one is either if you are working in PowerShell, you get it on Windows. You just download the Windows build. Better would be the LTS, the long-term support build. It's going to execute a setup procedure. And if you're on Windows, then please make sure that you automatically install the necessary tools. This will automatically also install Chocolate, but it also installs the build tools which you need in order to compile stuff with Node.js. And that is, if you install Truffle or Web3.js, it will try to compile the crypto libraries. And on a Ubuntu, you can basically run a script which downloads the setup_16.x for the Node.js 16 and then executes it with bash with sudo rights. So if I'm going to copy this and then paste it over here, it will download it. It will ask you for your password, which I entered before already, so it has cached this, but it will ask you for your password, and then it will just install it hopefully correctly. Give it a little bit of time. So I still have Node version 14 because I've installed it before, but you would probably have Node version 16 now installed. And if not, then close the terminal and open a new one so that your path is updated. Let me see if that works now. It's still 14 for me. And I have to look what is going on there, but you should have Node version 16 installed now. Git, you can download and install Git from this page. If you download it for Ubuntu, you run through or depending on your operating system or in your repository, you basically just, on Ubuntu, you add the repository and then you update apt and then you apt install Git. So it will have Git installed. So the other thing which I recommend is installing VS Code as a code editor. It is of course not necessary that you install VS Code. I will have VS Code throughout the rest of this section because I'm very much used to VS Code and it's a pretty good code editor. But if you don't like Microsoft, or you just like, I don't know, another editor, or you come from an IntelliJ background, fine with that. As you know, Solidity files are plain text. That's it. There is a couple of plugins that I'm using or extensions that I'm using for VS Code, and I'm trying to, if I have more, I'm trying to add them over here in this section. I've opened up my VS Code and the extension section. A couple of them I can recommend. Number one is the Solidity Visual Developer. That is this one. It's by consensus. There's another one which I haven't tried myself. It's this one by a guy named Juan Blanco. Has a lot more installs than the other one and is highly recommended by a lot of websites. What I'm after is syntax highlighting, and that's what I get with both of them. I don't really need the rest of the stuff from either of those. So that's the one. The other one which I can recommend, because we are probably going to work with .env files, is this .env extension. If you haven't used .env files, these are the ones that can save configuration files. It's just a nicer looking highlighted, syntax highlighted way for .env files. And the third one is if you're wondering what kind of theme I'm using here for VS Code, it's the Dracula theme, which you can get from Dracula official on the draculatheme.com/visual code website. So that's all. These are my basically prerequisites. Probably you don't even have to do anything because as a web developer, you already have Node and Git installed. So you could have skipped the lecture. Glad you didn't, and you're still around. And let's get started with setting up Truffle. So in this video, I really want to get started with installing Truffle and get our project set up so we have kind of like a file structure. Now I've already opened the terminal over here, and the way you install Truffle, there's actually two ways to use it, and I prefer the one that installs Truffle globally on the system. So every time you are in any kind of folder, you just have to type in Truffle then, and it's there like any other command. You can also install it in as a node dependency directly in the whatever project folder you have. But I think it's not really the standard way how Truffle is used. So I'm going to install it now globally. This is by npm install-g Truffle. And what it will do, it will download Truffle from the node package Truffle. Will download all the dependencies, and then you have it in the global node directory. In your home directory, there's probably a .npm-global directory in /lib/node-module/truffle. There's an executable file, and you can start it from anywhere in the system. Let's wait until this is done, and then I'm going to continue with the video. Okay, that's done. And the next one is how we structure the project. And I think we are just going to do like one main folder, and inside there we do one Truffle project, one Hardhat project, and one Foundry project. And you can do the whole thing. Then you can put it on GitHub, or you can share it with whoever you want to. So the way I want to get started is by, making a folder. Let's make a folder, and I'm just creating a subfolder, NFT project /Truffle. And then we are loading this into our VS Code with code and then the folder. And what will happen is that VS Code will open up with a totally empty folder, hopefully. It might also gonna ask you if you trust this source. You can simply hit yes if it's going to ask you. So the first thing is to understand what VS Code can offer us, because I don't want to go back and forth between the terminal and VS Code. You can start a terminal in here. Just go to terminal and new terminal. And you have a terminal that's exactly the same as the one from the Windows terminal. So how do you get a Truffle project started? That is by simply typing in Truffle init, not eit, init. And what it will do is it will download like a scaffolding project from GitHub and give you a default folder structure. So let me show you how this folder structure looks like. Make it a little bit bigger so it's easier to understand. So into the contracts folder, there go the contracts. Well, that's probably less surprising. There's also a migrations folder, and that's what some people really confuses. What's this migrations folder for? Migrations are there to deploy the smart contracts. The idea probably was that the blockchain acts like the database, and migrations are changing the database, so they need to migrate from one state to the other. And that's what this migrations folder is for. It contains JavaScript files that instruct Truffle how to deploy the smart contracts. And then we have the tests over here. Those are, for unit tests. And you will see later that it uses internally Mocha and Chai, but it uses an overlay to make it easier to deploy those smart contracts every time you run the tests. Whereas in Hardhat, you would have fixtures to reset a chain. In Truffle, it redeploys smart contracts every time it runs the tests. Okay, before we are doing anything else, I also want to add our NFT and get the project kind of like ready for, well, a standard web project that you would have in there. So the first one is probably to just init a package JSON, because we are going to add a couple of NPM packages in there, and we want to have reproducibility. So somebody who's downloading this is just need to do npm install and then have all the packages ready again. And because we are putting everything on GitHub, we also add the node modules folder to the git ignore, which is a file to instruct Git to ignore specific directories or files. Okay, as you have seen, also there's a Truffle config file. This is pre-populated with all kinds of documentation, which you can also get from this reference over here. And we are going to work through this until the end of the section, where you then need know basically everything that is to know in there for a production ready setup. So as said, we are going to import our NFT, and our NFT is using the OpenZeppelin smart contracts, and OpenZeppelin smart contracts are also available via npm. So npm install --save /at OpenZeppelin/contracts. And that will put the OpenZeppelin contracts into the node modules folder, into the contracts folder, and then you can access it from there. Now I said we are going to import our smart contract from Remix that we built before. So let's open that again. So we open our space bear contract, and I'm just going to copy this, and we are going to paste this into a contracts folder. We create a new contract called space bear sol and paste this over here. Great. You have to be careful over here. If you created the smart contracts with the Open in Remix functionality from the OpenZeppelin wizard, then there is a specific version over here for the npm package. Then you have to remove that version, because this import line should correspond to the node modules package over here. So if we import at OpenZeppelin/contracts/tokens, then there is a node modules OpenZeppelin contracts token ERC721 ERC721 Solidity file. So that should correspond to this file structure. This is how it resolves the files and the folders. Okay, the next thing is simply go to the terminal and type in Truffle compile and see what happens. Ideally, it will start to download the Solidity compiler, and then hopefully compile everything correctly. Well, it's a little bit of a terminal bug here, but well, it compiled everything correctly. If it doesn't compile everything correctly, because maybe there is a version mismatch or anything, open the Truffle config file, scroll down to the very bottom, almost to the bottom, where it says compilers, and check the version of the Solidity compiler that it tries to download. It tries to download it based on the config file, but make sure that it actually matches up with the somewhere of your Solidity file. So if you, use 084 and this compiler is going to be 09, that's not going to work. So either you bring down the compiler version over here to the version of Solidity that we are using, or you, migrate the smart contracts over to a new Solidity version, which might work quite easily if OpenZeppelin is going to use a new Solidity version, or it might not work, and then you just have to bring down the compiler version. Okay, what happens next? Now you compiled the smart contract. Suddenly a new folder appeared. That is the build folder. And inside the build folder, there's a contracts folder. And inside this folder, there's JSON files for each and every single smart contract that was in the chain of compiling the space bear contract. So it goes through all of the different contracts that are like imported, used, extended from, and so on, and compiles each one of them. And then at the end, it also gets to the space bear contract and puts it into the JSON file for the contract. It's called the contract artifact. What does it contain? It contains an well, contract name. It contains an ABI array that goes pretty far. Let me go until here. You can see that in the small little, where's it? It contains some metadata, it contains the bytecode, and it contains an AST, an abstraction syntax tree, which is a representation of your code in another format, which makes it easier for linting and for checking and so on. This is pretty long. And then if you scroll to the bottom, pretty much at the end of the file, actually go from the bottom to up, it also contains a couple more sections. And this one is kind of important over here, the network section, which is currently empty. Every time it deploys the contract to a network, it will put the deployed the address and the configuration for that network into this network section in the JSON file. So then you have all the addresses together in one JSON file. And that's the magic. That's how the magic of Truffle works. It will put everything neatly arranged in these JSON files. Also has a couple of more keys and values for documentation and so on and so forth. But that's not really important. So the question is, how do we get Truffle to deploy something? Well, that's something we do in the next lecture. So as I said before, in Truffle, you are not really deploying smart contracts, you are creating migrations. And that's basically the same as deploying smart contracts. But we are calling them migrations, and we are putting them into the migrations folder, and they are JavaScript files. So let's create one that is a new file, and let's call this. They are with a number. They start with a number, so you know, like Truffle knows how to execute them in which order. And then let's call it space bear deployment.js. And as I said, they are JavaScript files. So what you import over here, or what you do over here, is you're exporting a default function with module exports. Module.exports is a function. But this function, so Truffle is going through the single migration files, the JavaScript files, imports the files, and tries to call the default function. And the default function, it will not only call the default function, it will give it a couple of parameters. The first one is the deployer. So it will give it a deployer function when it's calling the default function of this module. And this deployer function can deploy smart contracts. Now the question is, how does it get these smart contracts? We have to import them with another function called artifacts, which is globally available. So in case of the space bear, we say artifacts.require space bear. What is inside here is all the necessary code and all the necessary information to deploy and access and work with the space bear smart contract. It gets this from the JSON file. So it's basically loading the JSON file space bear into this variable. And what we can do with the deployer, we can say deployer.deploy space bear. That's what we could do over here, but there's a little bit more to it. But basically, that's the basic function. So if we want to deploy this somewhere, then Truffle comes also with an internal blockchain, very much like Remix comes with an internal blockchain. And the way to access this is by doing Truffle develop. And what you get then is kind of like a shell or an interactive command line where you can type in commands. So the first thing that you see over here is Truffle is starting a blockchain at localhost 9545. And when you're looking through some of the code, then you will probably come across a JavaScript package called Ethereum.js VM. And I think that's integrated over here. So it basically starts a blockchain. And then you can interact with it. And it's also starting a console, which is then directly connected to this blockchain. And then you can type in migrate. You could also type in compile over here to compile the smart contracts and then migrate, but migrate will compile your smart contracts anyway, and then it will deploy the smart contracts based on the migrations script. And what you see over here is it's running through the first file, 01 space pair deployment.js, and then it is using the deployer to deploy the space pair over here, and it's telling you even some additional information. Now there is also more information that you can load over here. That is the network and then accounts. So if you're going to console log over here, the network and accounts, then you should actually hopefully see that. No, should reload this 01 space pair thing. Yes. So it's the develop network, because it's called develop, this whole network thingy environment. And it's giving you the accounts that it finds through web3.eth.get accounts, or the ETH get accounts RPC call against this networks node. Okay, let's remove this again. So in case you need these, those are the parameters that are available. Question is, what if your token actually contains constructor arguments? What then? Currently we have no constructor arguments. There is not even a constructor, or there is one, but what if there's constructor arguments? Well, you only add them by doing just in a comma, and then add the arguments over here as second, third, and fourth argument for the deploy script. And what if you want to change how or from which account it is deployed? Well, as a last optional parameter, after all the arguments for the constructor, you can have a configuration object that is very much like a Web3 object, where you can give it other accounts, you can influence the gas amount, and so on and so forth. So you can do several other things. And as you have seen maybe already, when I typed in migrate once, then it was deploying space pair. And when I'm typing in migrate the second time, it was replacing space pair. And there is an actual replace option, which is true by default. But you can set it to false, then it will not replace it. And you can also make it network dependent. So for example, when you say network is developed, then this will become true. Otherwise it's false. For example, if you don't want to redeploy smart contracts on main chain, because you're just adding a new contract and you're running migrations again. You can also run select migrations, but that's going a little bit too far. Yeah, for us, this is more than enough to know, but I do think that the develop blockchain is not the most powerful one. It is there to quickly execute stuff, but I personally actually like to work a lot better in Ganache, which is the blockchain that comes with the Truffle suite as a bundle, more or less. It's just a separate tool. So that's a lot of people confusing. Why do we even use Ganache? Because it can do a lot more things like mainnet forking, like influencing how blocks are mined and so on. So I do like very much to install also global Ganache. So that will take a while. That's a tool that is downloaded. And then you just simply type in Ganache and it will start. Also based on, I think it's based on Ethereum.js/VM, the same engine, looks exactly the same, but is a lot more powerful under the hood. So if I'm just stopping that and I type in -help, you have a lot more options to influence how the chain behaves. And we are going to use this a little bit later, but let's just roll with Ganache for now. And the question is, how can you instruct Truffle to deploy to this new Ganache network? So how do you get to that? Well, you have to define it in the Truffle config file. And if you go a little bit up in the Truffle config file to the networks section inside these curly brackets, then you see there's a couple of networks already defined, and we are going just to define like they're commented out, but I'm going to define one now with a key. So we have a host is 127.0.0.1. A port is 8545. And then network, actually the network ID is a star. Don't confuse the network ID with the chain ID. The chain ID is 1337, but the network ID will be a random number. So every time you restart Ganache, Truffle will not look in the networks section. Let me show you this in a second. So just put Ganache, host, localhost, port 8545, network ID is star. And then you can directly on the bash without opening Truffle console or anything, you just do Truffle migrate network Ganache. And then you can see on that when you scroll down with Ganache, then you see that it actually runs these commands to deploy the smart contract. Now, if you're opening this build artifact of SpaceSpear again, and you scroll to the very bottom, then you see now in the networks section that for our network 166.367 whatever, which is the network that Ganache just created for us with a random number, the address of the smart contract is 0x1ADE. And for the other network, which is the Truffle develop network, which is 5777, the address is 0xBE511 and so on. So it stores the addresses over here. Yeah, so now we have deployed our smart contract. Fine. How do we interact with it? Well, there's a couple of ways to do that, and we're going to do that in the next lecture. Now we have deployed our smart contract in Ganache, and if you close the window in the meantime, then reopen Ganache and retype in Truffle migrate -- network Ganache. But the question is, how can you interact with those smart contracts? And the way, or my preferred way on the lower level, is to open the Truffle console. The Truffle console is a JavaScript interactive console where you can type in commands and interact with your smart contracts. And we are going to connect to the network Ganache. And then you will see the prompt will change to Truffle and then the network type, very much like the develop network before, just this time with Ganache. What can you do here? So it gets a lot of things already injected magically. The one, for example, is Web3 connected to the right node, which is in this case the Ganache node. So if you do web3.eth.get accounts, then you will see the accounts from Ganache because it's executing the ETH accounts RPC call, and Ganache answers with the accounts. So how do you mint an NFT now using this console? But because Truffle knows in the artifacts the address for this smart contract based on the network ID that is connected to, and it also knows the ABI array of the smart contract, it can interact with the smart contract. And it can load this very much like a magic function into a variable as a contract instance. So if we do, for example, a SpaceSpear instance is await SpaceSpear deployed, then it will take the injected SpaceSpear artifact, which it automatically injects, mind the capital letter, and it has a magic function deployed. And this function returns a promise. So that's why the await keyword. So we wait for the promise to resolve. And if the promise resolved, means that it found, or it loads the contract running at the address under the address in the right network where it's connected to. So it basically just loads this contract address with this ABI into this contract instance. So if you do spacebar instance dot name, then it will return the name spacebar, because it will go into the smart contract and it will make a call, which is a reading function, as you remember, and then it will just return well, the name. And based on the ABI array, it knows it needs to return a string here, and it will decode the string that it gets ASCII encoded from the smart contract or from the blockchain node. We can also do writing transactions. So for example, if we load all our accounts and we want to mint one account for account number 2 in our accounts array, then we do web3.eth.getAccounts, and then we do await spacebar instance dot save mint, and you see I can use the tab here to actually complete the code. I have code completion. Accounts 1, and then we have to give it the URI that we have for this token, which is spacebar_1.json. And don't forget the await keyword, because this one will be a writing transaction, and the writing transaction needs to be resolved as a promise. So we wait for the promise to be resolved. So if I'm hitting that, then I see on the left side it sends a transaction. First it estimates the gas, so it knows how much gas and so on. So it fills in all the missing pieces of the puzzle to actually send this transaction. And then it sends the transaction and it returns a transaction receipt or a transaction result. And inside there you have the logs and everything. So how can we view this now? Well, spacebar instance owner of must be the same as our accounts 1, hopefully, which is the same. And the spacebar instance dot token URI of token 0 is our correct address, which we had before. But instead of typing in those things and making sure manually that it's correct, wouldn't it be much better to do that in an automated way? That's exactly where unit tests are coming in. So let's write our first unit test for Truffle in the next lecture. So now that we have used the Truffle console, it's just a tiny step to understand how the unit testing framework works in Truffle. Testing in general consists of 2 different components. The one is to execute a transaction like a function call and so on, and then to compare either the returned result or the state on the blockchain to an expected value. For example, if we mint an NFT for account number 2, then we expect the owner of function to return account number 2 for that NFT. Can be as simple as that, or maybe much more complex, like executing several different transactions and then comparing the results to something that you know beforehand that it's true. Now let's get started with a first unit test, just a very simple one that we are doing in JavaScript. Now, Truffle can do tests in JavaScript or Solidity. The problem with the Solidity tests with Truffle is they can't really influence much of the transaction structure. You can't choose the account you're sending the transaction from in Solidity. You can't modify anything on the chain. You can't listen to events and so on. And you will later see when we are going with Foundry what I mean, where you can actually do something on chain with Solidity tests. Now, I'm going to stick with JavaScript tests for this one, and this one I'm calling spacebar.test.js. Okay, very much like in the migrations, we have artifacts that we require, and then we have a special function that you probably know from Mocha tests if you did them before in another framework. If not, then just bear with me for now. So the first one is we are going to require our artifacts like we did it in the migrations. Const spacebar is artifacts.require spacebar. That will give us the spacebar artifact. Now the question is how we are going to use it. There is no migration to do here. When we run the test, Truffle is executing the migrations automatically. So it's giving us a deployed instance. If we want to, we can also deploy a new one. In Mocha, you usually start tests with the describe function, and then you have a description, and then you have a function that does something. And Mocha is the framework, the testing framework that runs behind Truffle. You can use that. But Truffle gives you another magic function that is, instead of describe, it's called contract. And this one will automatically inject the accounts over here. And it will also deploy the smart contracts for you beforehand, so you don't have to do the before all functions that you might have seen somewhere in the test and so on. So this one, if we say contract space bear, you can name this whatever you want. In this case, I'm just giving it the same name as the contract. It will deploy the contracts, all of them, run all the migrations for a random test chain, and then it will give you the accounts from the test chain. And then inside, you have a function that is called it. It should do something. For example, it should credit an NFT to a specific account. And over here, we are having an async function because we want to use async await because it's easier to read. You can also use promises, but I think async await is much easier to read. And then we are doing what we did before. Const spacebar instance is await spacebar dot deployed. So that one gives us the instance. Then we are going to save mint one of the NFTs for our second account in the accounts array. Starts with index 0, so the second one is index 1, and with spacebar 1.json, and then we are console logging just for now the spacebar instance owner of the first token. Now let's run this. So if you want to run this, you have two options. First of all, go into the right folder if you started from scratch like I am here, and then you can run this on the Truffle development chain, or you can run it in Ganache or something like that with the Truffle console. So if you type in Truffle test, it will use a network called test, which it creates itself. And then it will compile, and then it will say that we have a typo over here because it's called contract and not construct. So let's do the Truffle test again. And then it should run through this test and console log the owner of. So this one gives you back a promise. And we forgot to await over here. So now we have the owner of the account, and we could do something with this, or you start your Ganache, and then you Truffle console network. We called it network Ganache, so it connects to the Ganache network. And then over here, you can simply type in test, and you will see the account will obviously be different, but it will be, where are we? F07, and if we scroll up a little bit, it should be F07, the second account in our accounts list. So account with the index 1 is the second account. Now, obviously, you see it's passing and you see console log output. Normally, you don't want the console log output, and you definitely don't want to compare it manually. You want to compare it automated, and we want to make sure that only tests are passing if the expected value is the same as the returned value. Now, the way we are doing this, we are going to change the console log into an assert.equal. This will make the first value, compare it to the second value, and if it's not equal, then it will output an error message. Owner of token 1 is not equal account 2. So if you're running this test now, And you can have a look here on the right side. You see that Truffle is redeploying the contracts every time you run the tests. So it gives you a clean room. So it gives you basically clean instances every time you run the tests. It still passes. Now, what if we are going to change this to make the test fail for sure? How does that look like? It looks like this. It's failing the test. It tells you all the events that were emitted during that test case. It tells you the expected value and the actual value. So you know what's wrong, or you can pinpoint it. So let's make this test pass again, and let's move on to the next case. The next one, what I can suggest you is use a helper library called Truffle Assertions, because I personally found these assert equal things, especially when we talk about events, very cumbersome to use. Let me show you an example. So if we say our SafeMint is actually in a transaction result, if I console log that transaction result, then you will see what I mean. In the transaction results object, there is a transaction hash, a receipt, and the logs. So if you want to make sure that the logs are, well, equal to something, then we would have to do the following, right? We would have to assert dot equal tx result dot logs 0 dot event is called transfer. So we want to make sure that the first event that is emitted here is the transfer event, and then event is not the transfer event. First, actually, we have to make sure that there is an event. So not only there is a log0.event, but there is an event, but I'm skipping that here. Then we have to do an assert equal transaction result dot logs 0 dot args, the one that is omitted here. If I would output that, it would have all the arguments from the transaction event, and here would say from, and that is the 0 address. Let me quickly copy this here inside. From is not the 0 address, and so on and so forth. So we would have to take all of the different fields of the event and compare them to an actual value. Now, is there a better way to do this? Yes, there is. So first of all, let me run this just to make sure that it's actually working what I'm doing here. And then I'll show you a better way, because we are by far not finished. There's a couple more arguments that we can check. So it's passing, fine, we have compared the right values. So if you're going out of the console, then I want to install another library. It's called Truffle Assertions. And the way you're using that is with Truffle Assert is require Truffle Assertions. And you have this Truffle Assert functionality. So instead of doing these assert equal on the logs, you can use Truffle Assert event emitted. And here you can give it just a transaction result object, or the result object of the send of the SafeMint. And then you are looking for a transfer event. And you want to make sure that a couple of the arguments are there. First of all, the from, that one should be from, that should be the 0 address. The to, that should be accounts 1. And then we have a token ID that I didn't show you before. I'm going to show you this in a second. That must be the same as a web3.utils.2pn of a 0 string, so it actually compares big numbers to big number objects. Yeah, it's that one is a little bit confusing, and I'll tell you in a second what's behind that. Just let me run this test real quick and see if we did it right. Yes, it's still passing. And if we are changing this, that it's not passing, let's see if that works too, just to be sure. Yes, it's failing. It says assertion error, event filter for transfer return, no results, event emitted, and so on. It tells you what is emitted and what you were expecting and what is wrong. So you can pinpoint that. So the token ID. Yeah, the token ID is a little bit tricky. So if you are console log tx results.logs0.args, then you will see what I mean. The arguments from the events that were returned are the arguments that are, well, in the event itself, either as index or as named arguments. And the token ID is a big number because that is defined as an unsigned integer 256. The problem is between the unsigned integer 256 and JavaScript. JavaScript can do integer representation with IEEE 754. That doesn't really need to tell you anything, but what you have to keep in mind that an integer in JavaScript is pretty much maxed out with precision at 2 to the power of 53. Problem is, Solidity unsigned integers range to the power of 2 to the power of 256. So there's a lot more numbers available that you have no precision arithmetic operations over in JavaScript. And it will basically just error out. It will not just error out, it will give you the wrong results. So for a lot of Solidity libraries or Solidity interaction in JavaScript, they created big number libraries that can handle these large numbers. This is why we have a BN library here. There's a couple of them, and it's quite confusing even to me which one is in use now. Web3 uses BN. Some others use bignumber.js. Sometimes they're interchangeable, sometimes not. Sometimes it's a little bit of fiddling around. The point is, when you compare Truffle assert events, and you have a big number here, then you need to compare it to a similar big number object over there. Otherwise, it will just fail. It will not auto-convert anything. So we have the token ID, and we want to compare it to a big number with the number 0. Well, it's useless to have a big number with the number 0, but it needs to be an object of that kind of type. So this is why we are converting this. Now enough with the big numbers and everything. Let's see if we can deploy our smart contract with Truffle. And I want to show you 2 really cool methods. Now, so far we have worked with Ganache, which is basically 2 things in one. First of all, let me just open up the Blackboard over here. We have a wallet component. And then we have a chain or blockchain component. And when we send a transaction, we have this send transaction method. And that one sends this unsigned transaction object with, with 2, then the data field, and then potentially from, and the nonce, and so on. But that one is not signed yet. And in order to get something onto the blockchain, you need to send a signed transaction. And Ganache is basically 2 things in one. That is a wallet or a key store or something that can make out of this transaction object a signed transaction object with a specific account. So if we say we want to send this from account number 1, then whatever we send there to Ganache will take the private key from account number 1, sign this whole transaction, and then we have also the RSV values in there, plus a nonce that is added beforehand. and also a chain ID for a specific chain and potentially some other parameters. But the point is here, the signature values. And so it's taking the accounts object, it's running them through this signature generating function, and it adds the RSV values based on the input objects as well. And then we can send signed transaction onto the blockchain nodes or wherever we want to. Now, in very, very previous versions of when we wanted to interact with a blockchain, Geth also had a wallet included, and you can also create your own private keys with Web3 and so on. When we want to deploy a smart contract with Truffle, then we either need to connect to a node that understands how to sign transactions, or we need to provide the private keys directly to Truffle, or, well, the seed phrase. And in the first method that I want to show you now is where we use a Truffle component, a JavaScript component, which takes the seed phrase and then signs a transaction and then sends it off to a hosted blockchain node from Infura. And in the second part, I want to show you the same, but using MetaMask, much more secure and much easier. I want to still show you both because the other method, the newer one, is not very widely used yet for, I don't know, whatever reason. So you have to know both. You have to know, if you open up any kind of Truffle project out there, know what's going on with the seed phrases and with the Truffle HD wallet provider. But I also want to show you the new method, which is much easier, much faster, and much more secure. So I'm sorry for my handwriting, but I still hope it was helpful to understand what's going on here. And we will anyway review this later on with the theory lecture. Now let's get started using, well, deploying with Truffle, the HD wallet provider, and Infura. The first one is we are going to sign a transaction using the HD wallet provider. And for that, we are going to install a component called @truffle/HD wallet-provider. And then I'm going to create a couple of empty files. One is called .secret and the other one is called .infura. And for the .secret file, we are going to add our seed phrase from MetaMask, where we have our test ETH for a specific chain. And for the .infura, we are going to create an Infura API key by signing up to Infura. It's free and you don't have to pay anything. So I'm going to install the Truffle HD wallet provider over here. And then we are going to touch.secret and touch.infura. And then we also want to make sure, in case you want to add this later on to GitHub, we don't want to check that into GitHub. So we add this to the git ignore and also the Infura to the git ignore. So in our git ignore, we have now the node module, secrets, and Infura. Great. How do we use this? We use this inside the Truffle config file. And there's already an example over here, which I don't think is very good because you need to store the mnemonic inside your Truffle config file. I don't think it's a very good behavior. And also not in the env file, because sometimes if you use front ends like React, they are going to parse the whole env and add it to their build. And then you end up with your seed phrase in your build. It's not a very good thing, or you need to be extra careful. What is working though is, first of all, we are using the HD wallet provider from the HD wallet provider. And then we are going to get the mnemonic, seed phrase, and the Infura project ID from the file system. So the file system is require fs, and the mnemonic phrase is fs.readFileSync.secret, and then we are doing a toString, and then we are also doing a trim just in case we have any white space. So on there. And the other one is the Infura project ID ifs dot read file sync dot infura to string dot trim. Now we need to use this somewhere. And how can we use this? Now we already have our Ganache network over here, and there's a couple more of them. And if we just uncomment, for example, the girly network, we have a comma missing over here. So the girly network, then you can already see how this works. We have a provider. Instead of a host name, we have a provider with the mnemonic phrase and the Infura project ID. And this is the network ID 5. So if you use Coven, use the right network. If you use another test network, which might be superseding girly, then use that network ID. Please check the network ID by simply Googling it for it. We wait for 2 confirmations. There's a timeout, which you can set, and we can also skip the dry run, which you saw before. It's first trying to deploy and then actually deploying, which you don't need for public networks over here, or you can leave it on if you want to. So the question is, where do we get the Infura ID? The Infura ID is something that you can get from infura.io. There is a free trial for 100,000 requests per day, and you can simply sign up with your email and a password. I already signed up, and then you need to create a new key, which I already did, and then you can manage the key, and you end up on a page like this, where you have an API key and getting started, and all kinds of other things which are absolutely not important for you right now. All you need to do is copy that API key and paste it into the Infura part. Now the question is, where do you get the secret phrase from? The secret phrase you get from your MetaMask. So if you are in MetaMask, you need to log in. And then you need to click on your little blocky or account icon, then into settings, and then security and privacy, and then reveal secret recovery phrase. Enter your password again. Scroll down a little bit, copy to clipboard, close this, go back to your project, and paste the secret key. Great. And now you can interact with the girly network. For example, Truffle console network girly. This should make a connection to Infura girly. And for example, you can see which accounts you have. Those accounts should be the same as the accounts in your MetaMask, probably just the first one. But in general, if you create new accounts in MetaMask, then you will create them one by one based on the index, based on the mnemonic seed phrase. Well, and if you type in migrate, then it will try to deploy the smart contract based on the seed phrase, based on your migrations file. So because we said we want to wait 2 confirmations, it's waiting now for the second block confirmation. And there we have it. Now this is the long version. There is also a short version for that. And that is with 2 different terminals or, well, command lines. On the one hand, you open Truffle dashboard, which will open 2 things. Number 1 is a dashboard running at localhost, well, some port number. And the other one, RPC endpoint running at localhost port number /RPC. If you are opening that in your browser, then you will see, well, this kind of page. Maybe the design changes a little bit. First of all, you need to confirm that you're on the network. Then you need to connect your wallet over here. Right now I'm already connected, but it says connect wallet, and MetaMask will pop up and ask you to connect. And then you are connected to the wallet, to girly, or to whatever network you are from the dropdown over here. Okay, so if I change to Rinkeby, it will ask me confirm the network to Rinkeby. If I change to Girly, now I'm connected to Girly. And the best part is I'm using MetaMask to, well, send and sign transactions. So if I'm going back over here and I'm opening a second terminal and I'm typing in Truffle migrate network dashboard, be careful that you type in dashboard. And mind, we didn't define anything here in our networks tab or networks object. It will compile the smart contracts and then it will try to deploy the smart contracts. We'll try to replace the space-bearer smart contract. And what happens in our Truffle dashboard is there is a new transaction popping up that says, well, a new thing popping up to confirm that says ETH send transaction. And if I hit confirm, then MetaMask will pop up, which is then our key store, which is our wallet to sign transactions. And I can confirm that. And when I go back to my project over here, then I already have a transaction hash and it's waiting a couple of blocks until it is successfully replacing my space-bearer smart contract. It could be that easy. So this is my second method, much more preferred. No copying, no accidental check-in of seed phrases, no need to sign up with Infura or anything else. The other thing is, if you run into the problem that cannot read property of null, then you need to go into your migrations and you need to make sure that you add here network accounts, and then you just say, we are going to deploy this from account 0. So in case you have problems with that, then it needs to be specific from which account you are deploying this smart contract. Now, the last part for every migration, for every deployment I want to do is source code verification. It is not very hard with Truffle. We are going to npm install -d Truffle plugin verify. And we are going to use this plugin in our Truffle config. On the very bottom, like right after compilers, we can use plugins, and that is an array. Truffle plugin verify, it's called. And how do we use this? We need to have some sort of API key over here. I can't change this, so let's touch Etherscan and then echo Etherscan to the git ignore. So where do we get this Etherscan key from? If you go to Etherscan and you sign up with Etherscan, it's for free. I already signed up. Then you can find in your API keys an API key over here. And I'm just going to copy this one. Going to my Etherscan, save this, and then we can use this the same way we did the other things over here. Where's my Etherscan Truffle config? Keys fs read file sync to string trim and then after the plugins we have API keys, then we have the Etherscan key over here, and then what we can do is Truffle run verify spacebar network girly, and hopefully it's going to verify this now, so we don't have to send any kind of source code somewhere. We don't have to flatten anything. Everything happens behind the scenes with this Truffle verify plugin, and it's also working for other block explorers, not just Etherscan. There's a lot of them out there. And it verified. So if you're going to this address now, then you can see the contract is verified, and we have our contract over here and all the other child contracts to children, or the extended contracts and so on and so forth, and we can interact with them. Perfect. That's it for this one. In the next one, we are going to see how we can debug and, well, develop small features and get more insights into what's happening on chain. Okay, in this lab, I want to show you basically two things. The one is debugging smart contracts while you develop, and the other one, debugging smart contracts after they are deployed, because those are very different things. When you develop, you might iterate over the code, you change the code, you deploy the code, and so on. And if you come from JavaScript, you probably know it. Something isn't working, and the next best thing is just to put a console log everywhere to figure out why something isn't working as expected. Now, if you come from a more sophisticated language, you might start a step-by-step debugger with some breakpoints and so on. But what are your options in Solidity? Now, let's get started with debugging while you develop. While developing, especially complex contracts, you sometimes run into unexpected states. And let me just simulate this. Let's say you want to extend this ERC 721 contract to return the token URI based on the token ID. So the token ID is numeric, we know that. And as you remember, we set the first token over here in this URL and added a spacebar underscore 1.json. And then for the token ID 1, we added a spacebar underscore 2.json. So our token IDs start with the index 0, but our spacebar JSON start with the index ID 1. But furthermore, you want to also allow people to purchase tokens. And that one maybe comes with, let's say, a simplistic thing. The first token goes for 0.1 ETH, the second token goes for 0.2 ETH, and so on and so forth. So I want to show you these two examples, which are classic examples of an ERC 721, where token URIs are automated and purchasing happens directly in the contract, for example. Now, the first one is we have here this ERC 721 URI storage, and for our example, we just want to remove all of those because we are calculating, or we are generating the token URI based on the token ID. So we are not taking the token URI, we are not adding any URI over here. And our token URI contract, instead of token URI, we are going to return a string over here. So it's a total automation here. We are returning a string, and then we ABI encode packed, for lack of a better way, to concatenate strings. And then we take the base URI, and then we are going to, well, first of all, this is something we're going to remove over here. Then we are going to add spacebar underscore, and then we are going to add the token ID +1. And then we are going to add a .json. And then we are closing the brackets. Well, let's see if that compiles. Let's see, Truffle, and then Truffle compile, just to make sure if everything still works. We have no typos over here. Okay, that is still compiling. And now the second part, and that was just a distraction over here, as you can imagine. Oh, I didn't save it. Let's compile this again. Of course, there's another. Here's it, 721 URI storage. And then we probably can make the token URI function pure, because it is not even reading anything from state anymore, because the token ID over here is the only variable that is used. And this one is pure as well. Okay, now it's compiling. And now let's put in a second function where we can purchase a token that is then minted. So let's call this function buy token, make it public payable. And then we said we are going to have the token ID is token ID counter current. And we are going to purchase the current token for, like the first token for 0.1 ETH, the second token for 0.2 ETH, and so on. So we require that message value is token ID times 0.1 Ether, wrong amount of funds sent. And then we increment the token ID counter. And then we are going to save mint token ID. Well, great. Let's give this a try. Let's see if this compiles. Let me just start Ganache over here. And then let's do Truffle console network Ganache. And then it's okay. Then we migrate, and then we are going to get the space pair instance. Let's run this migration first. Deploying, and then a const space pair instance is await space pair deployed, and then we are going to await space pair instance by token and the value of, because it's the first token, we say web3.utils.twoway 0.1 Ether. Be careful that this must be a string because the two-way function requires either a big number or a string. Oh, what's happening here? Wrong amount of funds sent. Why is this not working? And that is a very classical example of a normal web developer or blockchain developer running into the same things as web developers do every single day. Just a small mistake. And now we need to wait to find out what is wrong there. Now, because the code here is very tiny, it's very easy to figure out what's wrong. It's the token ID, classic example. But what options do you have as a smart contract developer over here? And it turns out in Ganache and in Hardhat and in Foundry, you have a way to actually dig into the code with console logs that work very similar to the JavaScript versions of console log. And what I'm going to do now is I'm going to install another NPM package, which is actually a Solidity smart contract, which then translate console logs into special opcodes, which are unused by the EVM actually. But Ganache and Hardhat and Foundry can, well, observe the transactions or the bytecode for these specific opcodes and then directly output console log statements here in this log window from the actual nodes, which is very convenient. Now, let me just close the Truffle console over here and let's type in npm install at Ganache/console log. And I'm not sure if they are intercompatible. That's something I actually haven't tried yet. I just know that console logs, these functions, exist for Foundry, Hardhat, and now Truffle and Ganache as well. So how do you use this? Well, that's actually very easy. You have to import it over here. Import at Ganache/console log/console Solidity. And what you can do now at any point where the transaction is still running, so you cannot do it after the require, but you cannot do it before the require. You can do console log, and then maybe I got here some message, and then the token ID because you want to know what's going on, and then the message value. So let's see how this works now. Truffle console, network ganache, migrate, space per instance, and then by token value web3.utils.2way 0.1 Ether. Now I'm running this like this now, but it will still not work. And the reason for that is if you have a look here on the right side, it is actually running an estimate gas function first before it actually sends the transaction. And this is a Truffle, more or less a Truffle speciality, or because we actually didn't provide any kind of gas amount. So it tries to understand how much gas will this function use, and then use that gas amount to then send the transaction. Now, because the gas is already erroring out, it knows that there's going to be an error, so it doesn't even have to send the transaction anymore. But if you want to kind of like force the transaction, then we also have to provide a gas amount like, 3 million. And now you can see that the transaction is actually sent. Before it didn't really send the transaction. There's nothing, no data sent here. Nothing sent. But now it sent the transaction. Where's the status? Status is false, so it didn't go through. And the reason is wrong amount of funds sent. But if you pay attention to the right side, then you can see here that our console log is outputted over here. Actually twice, which is interesting. But definitely once it's from the transaction. So now you have another tool in your toolbox to debug or at least dig into what's going on with transactions during development. You can also deploy this in a live environment. It will be ignored. It will cost a little bit more gas to run transactions, but it will be ignored. But I want to show you next a way to debug smart contracts which are either already running or in your Truffle environment with the Truffle debugger, which is really convenient and saved my life a couple of times, figuratively speaking. Now I want to show you another tool in my toolbox for debugging smart contracts, and this is both true for during development and also after having deployed smart contracts. Now, in this lecture, in this particular example, I want to dig into the transaction that didn't work in the previous lecture. So I want to start Ganache again, and I want to start the Truffle console again, and then we are going to migrate, and I want to start the exact same transaction and just see if we can get a little bit more into the reason why this didn't work. It's deploying, and then we are having the same problem as before. We just need to add a gas amount again over here. Okay, now we actually have a transaction that errored out. And here's a transaction hash. It's the same as this one over here. And with Truffle, you have a tool that is the debugger. And you can either reach it on the console, just typing debug and then a transaction hash. Or if you are outside of the console, then you have to type in Truffle debug and then also a network as we started the console. So instead of console, you just write Truffle debug. Now, if you are in the console, you just type in debug and then the transaction hash. And that should actually start a step-by-step debugger. The question is it going to work now? It sometimes takes a while. So I will pause the video now and be back when the debugger started contracts are compiled and so on. Okay, once the debugger is started, it took a little bit longer than I expected. It will show you basically a simple command line interface for running a debugger, and it will highlight code that is affected by the current instruction. Now, with the return key, you can simply dig into the next instruction. With H, you can show the help, and for example, with V, you can print the current variables, which is extremely convenient in my opinion. So you not just have any console log statement somewhere, you can actually dig into the code step by step, like you saw it with Remix before, where we debugged one smart contract, but it is kind of different here. And I think it's much more powerful than in Remix, because with a combination of ganache and also forking of chains, you can actually dig into running smart contracts that are out there. And then I'm going to show you another function from Truffle. We don't even have to have the source code locally, so you can directly start debugging transactions. Now, if you remember that we deployed our smart contract, then how can you get to that? And you can get that with forking. So if I stop our ganache and I stop that debugger over here and also the console, then if we do a ganache-h, nope, this was not it. Ganache-h. Help. Then you have here a fork parameter. And if you are not giving it an URL, if you just say you want to fork.network the mainnet, then it will automatically connect to Infura and will try to fork the mainnet. How this works is it will start from now on adding transactions to its own local cache. But if it needs to have data, it will load this from the Infura service from an existing node. So if we want to have our ungurly deployed smart contracts, we could say ganache fork.network girly. And now it's starting the RPC server. And it is a location, is Ethereum girly via Infura. The block is this one and the network ID is this one. And now we could go in and we could have a look at our, where is it? Build space per JSON. And if we scroll all the way down, then we find the addresses. Of our girly network, which is network ID 5. Just need to find it. Network ID 5, events, and this was probably the time we deployed the smart contract. So over here is the transaction hash that deployed the smart contract. And if I am moving this, having a look at this in Etherscan, then we created a new smart contract on this address, and we have no transaction so far. Let's directly dig into the transaction hash of our deployed token. So the way we can do this is with Truffle debug transaction hash network ganache. So what will happen, or what should happen, is that our Truffle is now trying to debug this transaction hash with the network ganache, and then ganache is trying to load the data from Infura. And the reason why I like this is because Infura, or the nodes that you usually get from any hosted network provider, doesn't have a specific opcode. And that is the debug trace transaction opcode, or this RPC call. And with that one, you can actually, well, the Truffle debugger actually gets the trace of any kind of function call, and then can show you where in the code it actually deployed, which part of the smart contract is currently called, and so on and so forth. So that is the RPC function that you're actually after if you want to debug something. And that's an extremely expensive, computationally expensive operation on the node, and most of them have simply turned it off. So now we just have to wait. And when Truffle has compiled the smart contract and then ran the debugger, and then at some point we will see debug trace transaction, and then it will start to gather information about the project and the transaction, and that takes a little bit. So we have to be patient over here. I will pause the video, and once that's done, I am back. Actually, it's much faster than I expected. Well, it cannot find the source code because I changed the source code. This is not the same source code anymore. But, well, we have our source code already verified. So is there a way to actually get the source code from Etherscan over here that we have uploaded? And turns out there's actually a way to get that too. And that is with another command, which is called fetch external. With this one, Truffle will download the source code that is on that address on Etherscan. And let's wait again, pause the video, and I'm back when this is done. Yeah, well, to my surprise or not so surprise, it cannot find the source code from the contract deployment. I will quickly mint a token, and then I will run this again and show you how that looks like. So I will pause the video and I will quickly do that, so you know what's going on. In the meantime, in the labs document, you can find an actual, hopefully working example. It's a little bit finicky, I have to admit that, because sometimes the nodes from Infura are not giving the right code or just not reacting. So I had to try this a couple of times. But if you are ever in the situation where you need to debug something that is running on mainnet, where some user just reported a bug in your contract that has multiple $1 million of Ether worth stored in it, I believe it's okay to just retry this 2-3 times until it actually works. Yeah, that's my take on it. And it's a tool in the toolbox that can help you on your daily life as a smart contract developer. So let me just mint the token and then run that transaction ID. Okay, so I redeployed the smart contract and I ran SafeMint one time. I also verified the smart contract, and I did this with the Truffle dashboard. Took maybe 3 minutes. So now I'm going to run exactly the same thing with Ganache Fork Network Girly, and I am going to show you how that looks like with the transaction hash Truffle debug this transaction hash network Ganache over here. So we are connecting to our local Ganache, and Ganache is actually connecting to Infura. So let me just see if that works faster now. Okay, now like we have it locally, I can just dig into the different kind of positions in the code. I can have a look at the variables that are, well, sometimes showing and sometimes not. But if you dig into a specific function call, then you can see exactly where we are. So I'm just hitting return, 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 and we are just running line of code after line of code. So I see token ID is 0 now, and the 2 is my address that I used to mint the token to, and so forth, and so on and so forth, until I maybe hit a require statement that evaluates to false, or I can see, the variables that are there, which I think is incredibly powerful. And if you have a set of smart contracts which is complex, where it's not immediately visible what's going on, like either trading or DeFi or any kind of, the prediction markets that are out there, or anything that's coming in the future, where you have a lot of contracts that are inherited from, or functions that are called, it is a lifesaver sometimes to have this kind of debugger. And that is one of the major reasons why I'm still advocating for learning Truffle as well, besides Hardhat and Foundry. Okay, enough said from my side. Definitely give the debugger a try. You can set breakpoints and so on, but it's way beyond what I want to show you here. It's a tool that you should have at your disposal. All right, now it's time to summarize what we did in the Truffle section. It was pretty intense. We went through basically all of the moving parts of Truffle, and I showed you around with unit testing, migrations, consoles, and whatnot. And now it's time to basically summarize what we did. Well, first of all, we installed Truffle, and you ran this npm install-g Truffle command, which installs Truffle globally on your system. And then it's just running through the packages over here, installing them. And then you have Truffle available globally in your system. If you're wondering where it's getting installed, it's in your home directory in the npm global directory as a binary. So it's sitting there, and that directory is in your path. And then you can just access the Truffle executable file anywhere from the system. Now, what you do then is Truffle init, and that one will initialize a new Truffle project in the current folder where you're in, and it will create a couple of subfolders. It will create a contracts folder, it will create a migrations folder, and it will create a test folder. And then it will also create the Truffle config.js file where the Truffle configuration is in. What we did next is, because we wanted to add additional node modules in there, I did an npm init-y. So the -y is just initializing everything with the default values. If you just do npm init, you have to run through the configuration of the package.json file, which is then created. And then we just made some precautions that the node modules that we are adding later is not checked into GitHub. So we added it to the git ignore. And then we installed the Open Zeppelin smart contracts over here. So this one's over here. And that basically just downloads the Open Zeppelin contracts and installs them in the node modules folder, where they are not really Node.js files, they are Solidity files. But then we can use them inside our smart contracts. So what we did next was we added our smart contract. The way we did this is we basically copied it over into a new file in the contracts folder. Just be careful over here. I highlighted it in yellow. If you use the link to open the Remix editor from the labs website, then it will add from the contract wizard. Then it will add over here, I think, the contract version or the npm package version. You just have to delete it. If it's not there, then you can just copy and paste all of the content from Remix directly into Truffle. And Truffle itself will take care of resolving these folder structure into the npm into the node modules /Open Zeppelin /contract /token /ERC721 /ERC721.sol file, and we'll take care of resolving this during compilation of the smart contract. Yeah, what we did next was we spun up a test chain that comes together with Truffle. It's basically the internal Truffle network, which works very much like Ganache that we used later on, but is a little bit less powerful. For testing internally, it works just fine. It opens an RPC interface on port 9545, gives you 10 accounts, I think with 100 ETH each, which is more than enough to test everything. And then it opens also a console directly connected to the test network, which isn't on this screenshot here. But then you can interact with the smart contracts. We then started our first migrations. Migrations are files that are either deploying smart contracts or configuring them online. We imported an artifact. An artifact is a simple, a sole smart contract, can be in one of the files. It can be, if there is only one smart contract in your file that has the same name, then it's loading this smart contract. If you have several smart contracts in one file, you just address it by the contract name. It's loading this artifact over here in this variable, and then we deploy this smart contract. There's a couple of things that will happen under the hood. If you run the migrations command, it will first of all compile the smart contracts, which means it will create this build folder. And inside this build folder, it will have the JSON artifacts, and it will have one JSON file for each smart contract it can find anywhere in your contracts folder. That also means that if in your contracts folder you address other contracts from outside of your contracts folder, it will resolve them too and add them into the build file as a JSON artifact. And then you can interact with them. And then it will try to deploy it to the network it's connected to. In this case, it's connected to the development network or the develop network, and then it tries to deploy the smart contracts over there. And once it has done this with the contract address over here, it will write the contract address back into this JSON file as well. So everything is in there that you would need. You don't need to take care of storing your addresses anywhere separately. If you use the Truffle migrations, the magic works under the hood. It's all in there. Well, next we installed Ganache and then started it. If you start Ganache, well, it looks very much like the internal network from Truffle. It will give you 10 accounts, in this case with 1,000 ETH each. It will open automatically an RPC interface on port 8545. By default, you can configure that. And it has a lot more options to configure Ganache. It has where you can deploy, or you can give it your own mnemonic. You can change ports. You can change the mining behavior. You can do forking, which we used later on for the debugging session. You can change the whole behavior of how Ganache works and where it's getting its data from and so on. So it's a lot more powerful than the internal network of Truffle. So we installed this globally. It is not part of Truffle, but it's part of the Truffle suite somehow. It's like their official version of a test network. So how do we use it? We use it by, first of all, defining a network in the Truffle config.js file over here. And then in the networks section, you define a new object with a host, a port. Well, and the network ID is a star by default because Ganache will give you a random network ID so that when Truffle stores the migrations over here in the builds folder, that you're not accidentally, after restarting Ganache, having clashes, because every time you stop Ganache, it is destroying the blockchain. There's nothing persistent. When you restart it, everything starts from scratch. And then if you have already a network ID over here in your build JSON artifacts, then Truffle will think there's already contracts deployed and might, not work correctly. So Ganache will take care of creating a new network ID, and it's not going to be static, but you can configure ganache in a different way. I just never made use of this. I think it's pretty convenient to have a new network ID every time I start ganache. Then we use the Truffle console. The Truffle console is basically the same as this Truffle develop network console that it gives you, just that you can connect to a specific network and it gives you an interactive console. You can get a contract instance and then work with this contract instance as if it was just a regular JavaScript file. It will just resolve this into so-called Truffle contract library under the hood, and this one will go back to Web3. And the whole problem with this, what it tries to solve, is that when you want to interact with a smart contract over here, that you can directly interact with the function name without needing a special specification, if that's a method or an event or whatnot, because with Web3, it will then under the hood map this back to the contract dot methods dot name dot, in this case, dot call. So instead of needing to do all of this, it will just, you can just easily interact with this. Now the problem with this is Truffle contract is not really the grand standard of convenience libraries to interact with smart contracts. It is still Web3. It is just inside the Truffle console, much easier to interact with the smart contracts. You can, of course, use Truffle contract also in your JavaScript files or in your JavaScript projects, so it becomes more convenient. Usually, I've seen people only use Web3, and then you need to default back to this kind of very long way of calling, but very definitive way of calling smart contract functions, or sending transaction is .send with the configuration object over here, which is an optional configuration object as last parameter in Truffle contract. So this is the way it tries to map things. The result is the same. You get back the information from the smart contract, and it prints out over here that information. Web3 is also magically inserted into this Truffle console, so you could do Web3 low-level calls if you want to skip the Truffle contract abstraction altogether. Yeah, the same goes for sending a transaction. If you want to send transactions, then, for example, SafeMint, you don't need to do any sort of .send or taking care of any kind of accounts that you want to send it from. This is taken care by Truffle contract and by the injection into the console itself. So all you need to do is SafeMint takes two parameters, a to and an URI. So all you have to do is specify the to and the URI. You don't need to specify any kind of from or any kind of nonce or any other things. You don't need to do that over here. It just magically works out of the box. Well, after writing your first contract interaction on the Truffle console, it is just an easy step to then write your first unit test. It works exactly the same way. You import an artifact, but then you are starting with the contracts function, and that contract function is a magic function that is used in the Truffle testing framework to deploy or redeploy smart contracts. So you always get a clean room. It's not going to take already existing deployed smart contracts. It is redeploying the smart contracts every time when you start with the contracts function, in order to give you a clean room environment. Then it's injecting accounts and into this function body over here. And here you write your test cases. So for example, it should credit an NFT to a specific account would be a test case. And then you write your test over here. You create your contract instance. And that contract instance is now getting the deployed instance from the test network. And then you can, interact with your contract instance like just we do it normally. There you have the assertion library Chai. You can use all kinds of API from Chai. You can use the expect API. You can use the Assert API, or you can use the should API or interface, or however you want to call this. We use the Assert API and we said assert dot equal, and then value A must be equal to value B, otherwise output the error message. So this is what we did. Now you can also obviously console log over here. This is going to be a real JavaScript console log. So after the call is returned. The thing is with this simple assert, it is for my own needs a lot of times just not powerful enough, because when it comes to testing failures, testing reverts, testing events, I really wanted to have something better than that. So I usually right now use a library called Truffle Assertions. Truffle Assertions over here, the required Truffle Assertions. It's an npm package. You can just install it, npm install Truffle Assertions, and then use it in your smart contracts. And we used it, for example, to test if a specific event transfer is emitted during the safe mint. And this test passed. So yes, the transfer was emitted. And we also did the reverse test, see if it fails if we just give it an arbitrary wrong event. And I very much like this library because you can test the most important things. You can test if an event is emitted. You can test if an event is not emitted over here. You can test if a method call fails for a specific reason that might be out of gas, a revert, an assert. You can test if a method passes, and that's the most important things for my needs for testing smart contracts. And I think it's much more readable than having try-catch statements and so on. So it's abstracted away, and you can easily read the smart contracts as an outsider. Now, the last thing is we deployed our smart contract, and we did two ways of doing that. The one is the HD wallet provider. The HD wallet provider needs a seed phrase or a private key, and it needs an endpoint like an Infura hosted node, or if you have the resources, a local Geth node or a local Bezo node, or if you have Alchemy or any other hosted provider, there's tons of them. And I have a link to the Ethereum website that actually lists those hosted providers. But we started with Infura. We signed up with Infura. It's 100,000 requests currently at the time of recording for free. So that is fine. And then we exported our seed phrase from MetaMask into this secret seed phrase file, loaded it from the file system, and then migrated our smart contracts into the Goerli network. Now, obviously, those two files must not be checked into your GitHub. So please be careful that you never share this or import this somewhere. It's really important. And I also don't like to put them in an env file, because sometimes when you have React in the same project folder, then it will just take the envs and just build it into your front end, and then you have it on your front end. And that would be absolutely fatal. Don't do that ever. And I don't want to always take care of just looking at it. So I just put these in separate files. The other way, which is much better in my opinion, is Truffle Dashboard, which basically just connects to your MetaMask. You don't need to export anything. You don't need to sign up anywhere. It just works. It's just that this is very Truffle specific and it doesn't work with Hardhat or Foundry. The way this works is you start one console with Truffle Dashboard. We'll open a web browser where you can connect your MetaMask. And what you run then is migrate -- network dashboard. And you don't need to actually define that in your Truffle config. There is no need to define that. Truffle will out of the box know this one is the dashboard network. And it will try to connect to the dashboard that is running, and it will show you the pending transactions on the dashboard website, which you need to confirm with MetaMask. So it's like one whole flow that makes sense. The last thing that we did is debug our smart contract with two different ways. The one is the simple one, console log, and that is a console log out of the smart contract into the log window of Ganache. And the other one is actually starting the Truffle debugger, which I think is a really powerful tool, which you should definitely add to your tools that you use when you work with smart contracts, even though you don't like Truffle because it's kind of slow, or you don't like the migrations, or you don't like the workflow. Have a look at the Truffle debugger. It can be used standalone. Okay, so the Truffle console log, the way you use it is you install the Ganache console log package as an NPM package, and then you import this over here, and then you basically just console log whatever you want to console log in your smart contracts, but before it errors out. And every time it hits this console log, it will output a message into the log window of Ganache. This looks like this. So you have you run your smart contracts. Be careful that you're not running just a transaction. You have to give it a specific gas amount so it doesn't estimate the gas and error out before it actually runs the transaction. But once it runs the transaction, you see over here in the Ganache log, not in the Truffle log, in the Ganache log, that it comes to this error or console log messages. And the other thing is the Truffle debugger, which you start with Truffle debug and then a transaction hash. And then you can also fork the mainnet with Ganache. I have this in the next slide. And then directly connect to your local Ganache. And you can even fetch external, which means it will download the source code from Etherscan if it's a verified smart contract. You don't even have to have it locally in your machine anymore. So you can directly debug stuff out of Etherscan whenever it happens. We'll download it. It will take a while. It takes a little bit, but the important part is that Ganache offers you this debug trace transaction call. So the debugger can actually find the trace and run through the source code over here. And then you have the commands. You basically just have to type in enter. And what I also found very useful is adding a breakpoint. So you can add breakpoints over here with B and then your source file .sol and then the line, whatever it is, where you want to set the breakpoint. Then just hit C until you hit the breakpoint. It will run, and then you can print the variables there, which is the V command. If I can find it over here, V, and then you print the variables. I found this extremely useful. It saved my life a couple of times, so maybe it saves yours too as a developer. Now Ganache, why Ganache? Why I find Ganache really cool is it can fork main chain test networks, and you don't even have to have an URL where to fork from, because it's coming from consensus, and Infura is coming from consensus, and it's basically built in Infura. Might change. Right now it's for free. Ganache then downloads the code, and then it offers this debug trace transaction RPC call, which non-blockchain nodes do not offer because it's quite compute intensive. But with Ganache, very easy to do, and it looks like this. says forking from mainnet via Infura, and then you can basically just connect to localhost 8545. But internally, Ganache will connect to the mainnet and download whatever it needs to download. From there, the way you do this Ganache -- fork chain ID 1. Just be careful that it's also giving it a chain ID 1. That's interesting. Should have been 1 here. Maybe an old screenshot. But chain ID 1. Yeah, that's it. And now off to Hardhat. Okay, let's talk about something that confuses a lot of new people that are coming to the Ethereum ecosystem with all these different tokens. In this video, I want to talk about the difference between ERC20 and ERC777 and ERC721 versus ERC1155. Now, the first one, the ERC20 token, is something that we extensively talked in our course. It's representing fungible tokens. The tokens, they have no kind of serial number or running number. All the tokens are equally worth something, like you own $1, except some collector's editions. If you own $1 from today, it doesn't make any difference from owning $1 coin yesterday. They're all equally worth $1, no matter how they look like. Same as with these ERC20 tokens. It's basically just a number in a database. There's functions to send, transfer, approve, maybe even mint and burn things. They have a transfer event and an approve event. There's a couple of benefits and drawbacks. Well, the first benefit is obviously it's extremely easy to use. It can represent anything from loyalty points, money, like casino chips for poker or something. So anything fungible can be represented with these ERC20 tokens. And furthermore, you can not only transfer them, you can give allowance to other people to spend tokens in your name. It's very convenient. Now, the drawbacks are you can accidentally send tokens to other contracts, and then they are basically locked in forever if those contracts do not have any ability to send tokens back or interact somehow with this. And there has been a confusion around the decimal points. Right now, they are pretty much fixed at 18 decimals, but still there is confusion. I think USDC coin only has 8 decimals. So every time you work with these tokens, you have to take care of the decimal places. Also, I was talking about the mint and burn functionality. That's not standardized at all. You can have any kind of mint and burn functionality somewhere in your smart contracts. There's not even a standardized mint and burn event as far as I know. The only standardized events are for transfer, allowance. And that's it. And if you receive tokens, you cannot really react on it. You basically just send tokens from one address to another. It updates the internal balance mapping, but that's about it. You cannot do anything. And this is exactly where the ERC777 token comes in. It's the same. It's a fungible tokens. It's backwards compatible with ERC20. Can be backwards compatible. Doesn't have to be backwards compatible, but there's backwards compatibility. The receiving smart contracts, if you want to send tokens to a smart contract address, they potentially need to implement and expose the ERC777 token sender interface. That's a special interface. You can have a look at the Open Zeppelin example. You need to expose this interface. And then you can add hooks to call smart contracts when tokens are transferred. And this token standard has standardized mint and burn events. Problem with this token standard is it's not very wide in use yet, which is one of the major drawbacks, besides being harder to implement. And the fallback override to send tokens to receiving contracts is sometimes also necessary. Now, the good thing is it's backwards compatible to ERC20 tokens, potentially, if you deactivate a couple of features. And that's the most important thing. It can prevent accidental transfers so that the tokens are locked in other contracts, because that one has caused millions in damages already where people accidentally sent tokens to their online wallet and the online wallet couldn't even interact with a smart contract. And then that's it. Tokens are locked in. And it has hooks. So you can interact with other smart contracts from that smart contract and basically call other smart contracts once a token is transferred. Now, the other thing that we did, or we are going to do in this course, is ERC-721 tokens. It was the first real non-fungible token standard that came out. It's very much like ERC-20, but here every token has a separate ID. You can imagine it, you saw it probably already, but you can imagine it is like deploying an ERC-20 token with a supply of 1 over and over again. And instead of running each ERC-20 tokens on its own address, you have one address that has many tokens with a supply of 1. And there is one and only one token with a specific ID. There is send, transfer, and approve event functions like ERC-20, but for each ID separately. So you can approve that somebody spends token 1 in your name or so. There's a transfer event and an approve event. So everything that was in ERC-20 is just extended that it works with IDs. Now, the ERC-1155 token standard came out because it was necessary to have more than one token with a specific ID. And that is like marrying the ERC-20 token standard with the ERC-720 token standard. Now, an ID can have a balance or a supply. Now, there is no standard implementation. That's a big problem. For example, there is an OpenSea example implementation where you create a new token ID, and then you can mint that new token. You can mint tokens with an existing ID. And in OpenZeppelin implementation, you can mint an amount of tokens for a non-existing ID. And so it becomes very vague. I think the reason is because this token standard, it became interesting to work with it, but it was never really caught on with getting real major support for one exact standard implementation. The result is always the same. You have the standard interface, but how you get to your tokens is always different. And there's transfer events for transferring single tokens, transferring a batch of tokens, and so on and so forth. So this is what I was talking about. This one is the OpenSea implementation, where you can create your first create a token, and then internally you mint a token, and then you mint more tokens for a specific token ID. Versus the OpenZeppelin version, where you just mint something for a new ID that doesn't exist yet, and then it gets created with the amount of tokens attached to it. And then the last example, what I wanted to show you is the difference between the balance of for the ERC-721 token versus the balance of for the ERC-1155 token. Here you have a balance of a specific account for a specific token ID. So the token ID itself gets a balance. And here you just know how many tokens does an owner hold of any kind of ID. I don't know which IDs. There is no enumerable thing. You just know this owner holds 4 tokens. But here you know this owner holds 4 tokens of this ID. And you don't really have a way to determine how many tokens in total the owner holds unless you are programming it yourself. All right, now it's time to get started with Hardhat. Hardhat is the second tool or framework that we are going to try. And since you already have some experience with Truffle now, we can also make some comparisons to Truffle. Let's get started with the setup before playing around with the smart contracts of Hardhat. And then I'll show you around in the folder structure and so on. And then we're going to add our NFT token again. So the first thing that I want to do here is create a new directory, Hardhat, and cd into the directory. So the directory is empty. And unlike Truffle, you install Hardhat usually, at least I've seen that so far, as a dev dependency in a specific project. So because we have no project or no node package module or whatever here. The first thing is we have to initialize this empty npm project, and then we are going to install Hardhat as a dev dependency. Great. Hardhat will here install itself, hopefully, into the node modules folder in a second, and then we can run Hardhat with the Hardhat wizard. Okay, Hardhat is installed, and how we run this is with npx Hardhat. So this one will start Hardhat from the node modules folder and run this little wizard. One thing that you immediately see here is Hardhat can create a TypeScript project, and that's one of the things where the TypeScript folks really love Hardhat for it, because with Truffle, you're basically stuck with JavaScript as far as I know right now. I think they're working on a TypeScript support, but Hardhat had TypeScript support, I think, out of the box since version 1, and people loved it. Now, these two will create a scaffolding project with a sample smart contract, a sample test, and a sample deploy script. And this one would just create an empty Hardhat config.js file in this folder. And you guessed it already, Hardhat, very much like Truffle, works based off a config file. And in Hardhat, the config file is called hardhat.config.js, unlike Truffle, where it's called truffle-config.js. I'm not sure if that's configurable, but definitely out of the box, it's different. What we are using here is we are going to create a new JavaScript project now. I'm going to select this one because I want to keep it low level for people that have JavaScript experience. If you have TypeScript experience already, then I assume that you also know JavaScript. And I think you can easily start with a TypeScript project and you can follow along. It's not going to be that different. Just in JavaScript, you don't have the type support. And in TypeScript, you have the type support, but you have to do something for it. And in this case, it's about using Hardhat. It's not about learning TypeScript. So I'm going with JavaScript. The next question will be, where is your project root? And our project root is in this case the folder where we are in by default. So I just accept this one. Do you want to add a git ignore? And I will select yes, because I want to add the node modules folder to the git ignore. And later on, when we add this whole folder structure to your GitHub, then you definitely do not want to check in the Infura and secret and Etherscan files that we also need in Hardhat, or the node modules folder and so on. So yes. And the last question will be, do you want to add the Hardhat toolbox? And we want to add this as well, because then we have all the goodies that Hardhat has brings under the hood. It's in the Hardhat toolbox. So we want to do this one. So it's going to start building or installing this now. When it's done, I will explain to you the folder structure. All right, the project is created. We have a README file over here that we can open and have a look at. Not going to run this now. I'm going to explain to you how this is run later. We have a couple of folders. The one is the contracts folder with a sample smart contract in there. It's called lock. What it does is it can lock until a specific unlock time is met, and the unlock time is given in the constructor. So keep that in mind. We have a scripts folder with a script called deploy.js. So the big difference here is Truffle has migrations, and in Hardhat you script everything or you write tasks, but there's a minor difference, but essentially you script all the functionality that you want. In this case, and I will explain to you the deploy script a little bit later, it's simply a function that is called and then runs through the deployment procedure. And then we have a test folder with tests. Unlike Truffle, Hardhat actually uses the low-level describe functionality from Mocha and uses by default the expect interface from Chai. You can use whatever you want. Over here, you can use expect, assert, or should. That makes no difference. The only thing is, since you have a couple of additional functionality over here, and I will talk about this also later on when we talk about unit tests, is Hardhat is expanding the chai assertion helpers or expect helpers with some more helpers to understand if a transaction is failing, if a transaction is going through, what events are being fired, and so on. So you can have a look through this sample JS file, but I'm going to delete it and we're going to write our own. So how do you run the things over here? The first one is fairly easy. You just type in npx hardhat test and you run the unit tests, for example. So it will run the describe block, and then it will run the deployment, and then it will test all the stuff, and then we'll run withdrawals, test all the stuff, and so on and so forth. How do you compile smart contracts? npx hardhat compile, and this one will create, well, I already did before because we ran the tests, but compile creates this artifacts folder, and inside this artifacts folder there are two folders, a build info folder and the contracts, and then a folder for the contract, and inside there are two JSON artifacts. The one is the ABI, bytecode and everything you would need to deploy it with Web3.js or Ethos.js. The other one is pointing back to the build info, and the build info has a copy of the source code, has a copy of the bytecode, and I think that's it pretty much. So few more meta information. But the big difference is it doesn't have any sort of management for addresses or whatever. You have to do this on your own, or you use one of the Truffle helpers. Truffle has dozens of community packages and official packages that help you with deployment, with interaction, with tasks, and so on and so forth. So definitely check those out. But out of the box, it doesn't have any opinionated deployment or migrations framework or workflow. How do you deploy with Hardhat? Yeah, that's a good question. Hardhat comes with a sample node or development node, very much like Ganache, and you start it with npx hardhat node. Then it will run this and it will give you 10,000 ETH and 20 accounts each, and open a port on 8545 localhost. And if you are running one of the scripts, for example, this deploy script, which does nothing else than getting the contract lock and then deploying the contract with the unlock time as the first parameter of the constructor, gives you back an instance, capital L lock, smaller L lock, and then it's deploying it. Wait until it's deployed, and then you can access the address of the instance with lock.address. So if you're running this, npx hardhat run network localhost, so it's connecting to localhost, scripts / deploy.js, then I'm going to scroll down here so you see the output over here. It's deploying this script, or it's deploying this smart contract to the development chain over here. So why don't we just add our NFT now, and just let me close this one, and then basically start over. Start with empty contracts folder, empty scripts folder, empty tests folder, remove the artifacts, and the cache. The cache is a local cache. You can basically ignore it for now, and then start over. So we are rm contracts, rm scripts, rm test, rm rf artifacts, and rm cache. So we start with empty folders. The first thing that we want to do is add a spacebar Solidity file, and we are going to paste in the exact same that we have from Truffle. Now, if you run npx hardhat compile over here, it cannot compile because it cannot find Open Zeppelin. So over here we have again npm install at openzeppelin/contracts to install the contracts, and then we can run npx hardhat compile, and it compiles the files successfully. Now, one thing that you might have seen here already, and I know it's pretty much the end of the video, but if I run hardhat compile over here, it's basically 1, 2, 3. It's basically done in 3 seconds. If I go to Truffle and I run Truffle compile 1, 2, 3, 4, 5, 6, 7. Well, it takes a lot longer in Truffle than in hardhat. And that's the second reason why a lot of people like hardhat over Truffle, even though Truffle is getting a lot faster recently, and I think they're still working on making it a lot faster, but hardhat always had an edge over Truffle in terms of speed. And you will see in one of the next lectures when we talk about unit tests that is really a big difference when you have to test a lot. So off to the next lecture where we are talking about hardhat deployments. Okay, now let's talk about deployment with hardhat, and well, let's write our deploy script manually. So in the scripts folder, right click, create a new file and call this deploy.js as it was before. Now here's a major difference between what was already there and what I'm going to write. They wrote a function that then gets called via as a function main or deploy, and they also imported the hardhat runtime environment. You have to do this, or you can do this if you want to use the deploy script in a larger JavaScript environment. I'm not intending to use this, so all I'm doing here now is I'm writing a very simplistic main function that gets called as soon as the script is run, which is async, and then I am wrapping it in a try catch block that console error E and process exit code is 1. So if the exit code is 0, means exit is correct. If exit code is non-zero, it means something went wrong. And over here, what we are going to do is we are getting the contract factory, and I'm going to talk a little bit more about the hardhat runtime environment in a second. And then we are going to deploy the contract, call the deploy function, and then just outputting the address. So the first one is the space bar is await HRE, and HRE that is already injected into this deploy script, because when you run it with hardhat, it will inject itself, the hardhat runtime environment, into the script. If it's not there, then you need to require the hardhat runtime environment if you want to use it outside of this hardhat console environment. Then we get ethers. So we use ethers.js over here, and that one get contract factory, and here we get the contract factory spacebar. And then we are calling spacebar.deploy and get a spacebar instance. Spacebar instance is await spacebar.deploy. And now we need to actually deploy that on chain. Await spacebar instance dot deployed, and then we are just console log deployed contract at spacebar instance dot address. Great. If we want to run this, npx hardhat node, we have to do this exactly as we did before. npx hardhat run network localhost scripts deploy.js. See if that is running. Yeah, it's running. It's deploying our contract on an address, so it's pretty straightforward. how can you deploy this to Goerli? Well, for this, we have to use the, guessed it, Infura, your seed phrase, and the Hardhat HD wallet provider, which is already included in the Hardhat toolbox. So if we open up our Hardhat config, it looks pretty empty so far. So what we are going to do here is we are going to define a network section. And over here, the comma, and over here we define a new network called Goerli. And inside here we give it an URL. For example, https goerli.infura.io/v3/ and then some Infura project ID that we still need to import from somewhere. We also give it an accounts object inside the Goerli network. And that one can use all kinds of configurations. And we are giving it a configuration so that it takes a seed phrase with a path and uses an index of that accounts index of that seed phrase. So first of all, we give it a mnemonic. Then we are giving it a path, and that is the deviation path for that mnemonic. So we are getting M44, then a single quote, and then /60 single quote /0 single quote /0. There's actually no spaces in between. So that is the deviation path for the mnemonic that we are giving it in a second. That can be public, that the path, not the mnemonic. Then the initial index is going to be 0. And well, we create a number of accounts, like 10 accounts, but we don't really need them to inject them. So the question is, where do we get the Infura project ID and the seed phrase from? Well, we already have it from our Truffle project, and we can use the exact same thing that we did before. We are going to require it from the secret file and from the Infura file. So the mnemonic is the fs.readFileSync secret toString and then a trim, and then the Infura project ID is fs.readFileSync.infura.toString.trim. And now all we have to do is we have to copy our two files over here. So now I copied the Infura and the secret from our Truffle project into the Hardhat project folder. And if we want to deploy this now, then we run the exact same script just for the Goerli network. So let's see if that works. And we have an address for our contract. And if we are going to look on Etherscan, then we should see in the Goerli Etherscan our contract. But it's not verified. So how do we verify that contract with our Hardhat over here? Well, turns out it's pretty easy. Because Hardhat already has an Etherscan verifier integrated, all we need to do is we need to give it the Etherscan API key over here in a separate section. Etherscan API key fs.readFileSync Etherscan.toString, and then just trim it just to be sure that this is working. And we are copying our Etherscan file into the Hardhat folder. And now all we need to do is npx hardhat verify. Network girly, and then our contract address. So this takes a little bit. And now our contract is verified on Etherscan. Let me just open the window real quick. Reload. And you can see it has the little check mark and everything is there as it was. Same with Truffle verify plugin. Just in this case, it's already integrated in Hardhat. So the next question is obviously, how can you test stuff in Hardhat? And that's exactly what we're going to do in the next lecture. Now let's have a look how we can test our smart contracts with Hardhat. Hardhat works like Truffle with JavaScript-based tests. They also use giant Mocha just like Truffle, but there are some differences under the hood. For example, there's a custom chai helper, and they also work by default with the expect API or the expect version of chai, not with Assert. But before talking too much, let's try and mint an NFT and see if the owner is the right one. We are going to add into the tests folder a new file, and we call it just spacebear.js. And inside there, we have a const expect is required chai, and we have an Hardhat runtime environment that is require Hardhat. You can also add this to your scripts if you want to, in case you are actually using those scripts as imports from other scripts, for example, and not directly in Hardhat, not starting it with Hardhat. Then you get the Hardhat runtime environment in your scripts as well. So the first thing that you will see now, the difference is that we are actually using describe here and not contract, how we do it in Truffle. So describe spacebear, and over here we have a function, and then we are closing this. Yep. And in here we have it is possible to mint a token. And then we have an async function. And in here we get from Hardhat ethers, const spacebear, the contract artifact or the factory, hre.ethers get contract factory spacebear, and then we are deploying that. Const spacebear instance is await spacebear.deploy, and then we are getting two accounts from our signer. So we get two signers. One is the owner and the other one is maybe another account. Ethers get signers, and then we are going to safe mint one of the tokens into the other account. Spacebear instance save mint, that will be automatically executed from the owner, from the first account, and we want to have it for the other account's address. And then we are expecting that the spacebear instance owner of the first token, we expect that to be to equal other account address. So all we gotta do now is we are going to go into the Hardhat folder and type in npx hardhat test, not text, test. So it's going to deploy the thing, and then it is going to run the test. So why don't we now simulate a transaction, and we simulate it from someone that is not allowed to actually send this transaction. So we're going to add another test. It fails to transfer tokens from the wrong address. It's again an async function. And over here, we are going to deploy the same token, and we are also going to mint the same token. So we basically can copy and paste this part. Now we can actually copy and paste the whole thing here. And then we are going to await expect. And this is the big difference. More on that in 1 second. Space pair instance dot connect. And here we have another account over here, which is not the NFT owner. So we are going to use not the NFT owner now to send a transaction. And we are going to transfer from the other account dot address. And we are trying to transfer it into the not NFT account address. And we want to transfer the 0 token. And here we are expecting this to revert. So to be reverted with, and here it should revert with the error message that is from OpenZeppelin token ERC721, ERC721, and here we have a transfer from ERC721. Caller is not token owner nor approved. This is the error message that we are expecting. Great. Let's run this again. Both are passing. Just make sure that we are, well, not having passing tests that should actually not pass. Yeah, so it tells us actually the error message is here wrong. I just added an S just to make sure that we are getting an actual assertion over here. Now you can see here that is basically more or less the same test, or at least the beginning of it. And it has then some additional things over here in the second test, but we deploy the contract and then we get some signers and we safe mint the token. That is actually handled with fixtures in Hardhat, while in Truffle you obviously have the migration scripts. So how do we work with fixtures in a second? The other thing that you see here, there is one time expect await and one time await expect. And the expect await is a normal assertion. So it is waiting for this value to resolve, for this promise to resolve, it gets back an address. And then it is just using the normal expect API or this expect function from Chai to compare it to another function. You could also do an assert.equal over here the same way as we did it in Truffle. The other thing is await expect. So here it gets interesting because this one will actually return a promise. And the reverted with is a Chai network helper from Hardhat that will take this promise, resolve it, and then it will do something with the resolved result. For example, it will see if that reverts with something or passes or has an event and so on. So very much like the Truffle assert library that I showed you earlier. Now to the fixtures. How do we use fixtures? There is another network helper that is called load fixture, and that is in require atomic foundations Hardhat network helpers. This is where it's in there. And the way you use this, first you define a function over here that is maybe an async function, deploy the space pair and mint token fixture. And over here we are taking like the whole thing. And first of all, we are getting the contract factory, then we are deploying it, and then we are safe minting one of the tokens. What we then return back is a space pair instance. And how do we use this fixture over here is instead of all of that, well, not exactly all of that, because we still need the accounts over here. Here we just say const space pair instance is a load fixture. And then we give it as an argument the function that is deploying this fixture. And the same goes again over here, where we are deploying the same fixture. And it is not just redeploying the smart contracts, it is rolling back the chain to where the fixture started. What did I make wrong here? Oh yeah, of course, it must be an await over here in order to resolve this promise. Let's try this again. Yeah, and this is basically how you use the fixtures. The other thing that I wanted to show you in this video is how you use the console log from Hardhat, which was basically the first project that had these console logs, and it's just recently being integrated in Ganache. So let me just show you how you can console log something over here in the contract. So the way you do this is you import from Hardhat console.sol, and then in your code, you can just use it like anything else, like any other console log. So for example, console.log, we got here, and that is the token ID, for example. And maybe also the message value. Let's run this, see if that works with a test. Well, we didn't buy any tokens. Maybe we should output this over here. And you can see, first of all, the console log is over here. And you can also obviously use it in the Hardhat node, npx Hardhat node. And then when you run this node over here, well, there's a script somewhere. I think we are. No, we are not. We are actually not doing anything with the contract. But if you had any script, if you were running it directly in the node, then you can see the output as well. I'm not extending this now, and you can try it yourself. It's essentially the same as with Truffle, and it's going to be the same again with Foundry that I'm going to show you next. All right, now it's time for the last one in our list of frameworks or toolboxes, which is Foundry. And I'm going to get started with this by creating a new directory. Okay, dear Foundry, and then we are CDing into that. Now, the big difference between the other frameworks is Foundry is not JavaScript based. It's a complete from scratch rewrite, and it not only not uses JavaScript or is not JavaScript based, it also works like with different libraries, not with Node.js, not with NPM. It works with Git submodules, and it's blazing fast. And it has a couple of features which are really handy. It's just the cheat codes and so on. But let me get started by installing it. And the way you install Foundry is you get a bash script, and the bash script is then installing it in your system. So you're going to curl https foundry.paradigm.xyz, and then we are giving it to the bash, and this will run a couple of settings, and it's basically installing Foundry up, which is a binary, and you can do this after running source home Thomas bash rc, or you start a new terminal. So the path is actually then, and you can then run Foundry up to install it. So it's downloading the latest versions of Forge, Cast, and Anvil. Forge is the tool to do something with smart contracts. Cast is a tool to do something with transactions. And Anvil is a tool that is basically, Ganache or a Hardhat node clone, just better. Great. I'm here having the versions Forge 020, Cast 020, and Anvil 010. And it's all done. Yeah, if you want to get started with Foundry, all you do is Forge init period. What happens is that it's downloading the Forge standard project, Foundry standard project, into that folder. It's also initializing a new Git repository over here. It's already having git ignore and git modules. There's a Foundry toml file, which is the configuration for Foundry. There is a tests folder, a source folder, a script folder, a lib folder, and well, the GitHub folder. So in the tests folder, there's a test for a smart contract, which is in the source folder. So your smart contracts are in the source folder. That is where your project lives. Your tests and your scripts are also Solidity files. So everything in Foundry is based off Solidity. Let me walk you through this sample smart contract over here, which is written in Solidity 0813. It's a counter. When you deploy it, nothing happens. You can call increment. That increments a number. When you set the number, it will set the number. And there's a public getter function number for this variable unsigned 256. In the tests folder, what happens is that there is a setup function, which will be called, well, for setting it up. It will deploy the smart contract and will set the number to 0. And then it has functions that start with test, which are then the actual tests that are running. And then there is a scripts Solidity file, which calls automatically run when you execute it. You will see this later. And it does something with the VM. And this is where Foundry actually comes in. It has this VM cheat codes, or you actually operate on the virtual machine level of the chain that it's executing. Now that's pretty cool. Let me get started with just executing the tests. The first command that I want to execute is building the smart contract. So in this case, forge build, which will have a look in the Foundry toml file, and then it will build the smart contracts based on the wherever the contracts are. In this case, they're in the source file, and it will place them in the out folder. It also has a cache in order not to recompile everything all the time. But you saw it's pretty blazing fast. That's all there is to say. The other thing is forge test, which will run through the tests, and you see it's just blazing fast. Great. In the next video, we are going to basically remove everything, and we are going to add our NFT. Perfect. Let's get started by adding our NFT and creating a unit test for it. The first thing is to just basically remove the Solidity files from the source folder, from the test folder, and from the scripts folder. Script folder, not scripts folder. So we have nothing in the source folder, we have nothing in the script folder, and we have nothing in the test folder. And because we ran Foundry before, we can also remove the cache and the out folder as well, because that is going to be recreated from our SpaceBear smart contract. So why don't we add our smart contract now from Hardhat, basically just copying it over to Foundry. And what we see here is we have the Hardhat console, which we don't want in Foundry. And we also want to remove the console log over here. I'll show you in a minute how it works in Foundry. And then let's basically just try to compile it, even though it fails because we need to install OpenZeppelin. Now here you already see the first big difference between Hardhat and Truffle, which are JavaScript based on NPM packages, versus Foundry is not. It is based on Git submodules. So what happens here is if I do forge install, then I would need to give it the repository, the username and the repository name that I want to install, versus with Truffle and Hardhat, you would have to give it the NPM package name. So in this case, we want to install from OpenZeppelin, the OpenZeppelin-contracts. And this will fail because now we are in a Git repository, and this one has modifications. And when we are installing something with Foundry, with Forge, then it would just directly commit the submodules, which it cannot because it's not a clean working state right now. So what we have to do first is we have to basically we added the space pair contract and remove the initial contracts. So now we have committed our changes in our Git repository, and now we can install the contracts. What happens is that it's going to download those contracts, hopefully. What's going on here? This normally works instantaneous. Now we have them. Okay, it took a little bit. Now they are installed. If it doesn't work, just Control-C, stop that and just try to reinstall it. Now, if you're trying to build this now, it still fails because it cannot find @OpenZeppelin/contracts, because they are called differently if we directly use the GitHub repository from the OpenZeppelin contracts. So what we would need to do over here is use the OpenZeppelin-contracts and then token OpenZeppelin contracts /access and OpenZeppelin-contracts /utils. So now we can build it. The compiler ran successfully, and you see it's blazing fast. And in our out folder, we have our space pair JSON file, which contains also the bytecode, which we now can use to run some tests. And I would say we are going to do this right now in the next lecture. We are going to add unit tests for our smart contract, and I'm going to show you how these VM cheat codes work. All right, we have our smart contract now compiled. Let's add a test. And for this, we are going to create a new file in the test folder, and we call it spacepair.test.sol. Now, because it's a Solidity file, it exactly works like other Solidity files. We need a pragma line, and we are going to use, what are we going to use here? Anything bigger than Solidity 084. And then we are importing from Forge standard /testsol, and we are also importing our spacepair Solidity file. Now we are creating a contract, and we call it spacepair test, and this is extending from test. And over here we have two functions. The one is setup, and then we have a test function. So let's write our setup function first. When we want to run this test, we want to create a new spacepair instance every time. So in this case, we are going to have a spacepair, and in the function setup, which will be called every time a test is run, we are going to create. No, this should be a lowercase over here because it's an instance. And spacepair is new spacepair. We don't have any constructor arguments for our contract because it's automatically using an ERC721 and giving it the name spacepair and the symbol SPR. So why don't we test for this name now? For example, we write a function. Test name is spacepair. And then we are basically just asserting assert equals spacepair name must be spacepair. Let's run Forge test and see if it works. It's compiling, and then it's running, and it's passing this test because it's the test name spacepair. Let's just make the test if it fails. If it's not the right name, it failed. Problem here is you don't know where it failed. So if you want to know where this failed, you have to add some verbosity to the log output, which is -v for verbosity level 1, -vv for level 2, or level 3, level 4, and I think there's 5, I'm not sure. Usually 3 is enough to understand where this test actually fails. So it's it's failing here in get name, this is space pair, but then it's asserting the wrong name. It's actually, it's expecting space pairs, but it's actually space pair, and then it's failing over here. So, oh, that was wrong. Now we are just testing this again. Fine, it's passing, everything is fine. So why don't we try and test if we can mint our NFT? Function test minting NFTs. And that is only possible from the owner. So why don't we just space pair, save mint, and we just mint it to ourselves. And then we assert equals space pair owner of must be the message sender. Run test again, and it's passing. Now let's also test if the token URI is correct. Token URI 0, and that one should be HTTPS Ethereum blockchain develop.com /2022-06 NFT Truffle hard hat foundry /NFT data /space pair _1.json. That's the URL that we are expecting. Let's test this one. Oh, wait a second. I have a mistake here in my syntax. I need a semicolon at the end. Can compile. Assertion failed. That's weird. We expected this URL, but we got this URL. What is going on here? But it works fine in Truffle, right? That is so strange. So it actually took me a while to figure out how to fix it and what is going on here. As it seems, when we are returning the ABI encoded string casted return value over here, it will just in Solidity swallow this to a non-existent string. Plus we have here, we forgot here the space pair underscore. But this one will just be gone. And I actually don't know why, but I found the workaround, and I think you should use that workaround too. So there are string utils from OpenZeppelin, which are there to actually convert a uint 256 to a string. So if we import the strings utils from OpenZeppelin and do here a strings to string 1 and then run this test, then it passes. So this is now all fine and good because we are using the message sender only. But how can we test something with a different address? And that is exactly where these VM cheat codes or the pranking comes in. Let me show you what I mean by actually purchasing an NFT with an address that is not the message sender. For example, the 0x1 address. Function test purchase NFT. And let's say we have an address, purchaser is address 0x1. So we have the 0x1 address that is actually buying this NFT. How can we now test this, and how can we give this address some ether? After all, we are just starting a transaction to this, well, test smart contract with a specific message sender. That is where the VM pranks come in. So VM.startPrank will instruct the underlying virtual machine to from now on run every transaction with the address that I can give it here as an argument. What means is that if I am going to, well, let's say we are going to SafeMint over here, which is not the owner, right? The owner, like the message sender here on setup, did deploy the smart contract. So the message sender is the owner, and the message sender is now 0x1 or the 0x1 address. So if we are going to now do a SafeMint for myself, and then we do a vm.stop prank afterwards, meaning after calling stop prank, it will not use the purchaser address to run these transactions. If you are going to execute this, then this should fail, right? We would expect here a revert, because the require statement in spacebar in the SafeMint only owner function is not satisfied, and it fails. And it fails with the test unless we are going to do a vm.expect revert, and we can actually give it here the revert reason. So now our tests are passing again, and we are actually using a different address, which also means we can now test if we can purchase an NFT. But actually, this is now the wrong function name. Let's call this NFT creation wrong owner. And let's call this test NFT by token. And it's the same thing, vm.start prank. Let's use the 0x2 address just to get some variation in here. Purchaser, and then we are doing a spacebar.buy token. And then we are doing a vm.stop prank. If you just have one single instruction, you can just do vm.prank. This will only take the next call and use this address for the next call, and then just directly stop prank. But I like to be very explicit about these things, so I usually do start prank and stop prank, and then we assert equal that the spacebar owner of the 0 token is the purchaser. Let's see what happens if you're running this. Oh no, buy token, of course, I buy token with this address. Yeah, everything is passing. So the question is now, how can we deploy this token? This is where I want to use the scripts now. You could also use cast for that, but I'm not going to use it. I think the scripts are much more useful and predictable. And in the next lecture, we are going to deploy our token to the girly test network. Now the question is, how can you get your smart contract deployed to an actual network? And we already have our Infura keys. We already have our seed phrase in specific files. And in Foundry, at least for the seed phrase, some parts also for the other things, there is a way directly from Solidity scripts inside Solidity to parse files from outside, because you can use exactly the same VM cheat codes that we also used for the tests to prank, but there are other cheat codes where you can actually read a file and then work with this file from within a script. Now, let's get started by, well, basically just copy your secrets from Truffle or Hardhat over to Foundry. The secret file. And the other thing you would have to do now, at least I didn't find a way, is to create an env file with your girly RPC URL and the Etherscan API key in order to verify the smart contract. So let's right click over here, create an env file. The first one is maybe a girly RPC URL, and then an Etherscan API key. So the girly RPC URL is https://girly.infura.io/v3/your key, and the Etherscan API key is the Etherscan API key from the .etherscan file in Hardhead or Foundry. So let me copy that in. So I've both copied in there. I'm going to save this file. Don't forget girly_rpc_url and etherscan_API_key, which is a hotkey for Foundry to understand what this Etherscan API is. So how can you run a script now? Let's create a script. New file. Let's call this deploy.sol. And then we are having here a pragma line. Let's make this the same version pragma as our smart contract. And then we are going to import a couple of things. The one is forge standard script.sol. And then we are also importing our spacebear.sol. And then we are having a contract. Spacebear script is a script. And here we have a function, well, set up, which is empty. And we have a function run, which is run from the scripts runner from Foundry. And over here, we are going to import our seed phrase and generate a private key from it. Memory seed phrase is vm.read file. And we are going to read it from the secret over here. Now we have our seed phrase inside Solidity. It's like a blockchain oracle of some sort. And then we are going to create a private key out of this, which is vm.derive key from the seed phrase. And we want to have the first private key. And then we are going to vm.start broadcast with this private key. And over here, we are going to do a spacebear. Spacebear is new spacebear. So we are creating a new spacebear contract. If you had any other commands over here, you would add them over here. And then at the end, you do a vm.stop broadcast. And that's it. Now we need to run this script somehow. Don't forget to save it. So how do you run this script? Okay, in order to deploy that, you need to do a couple of things. The first one, Foundry, if you just start forge script like this, it will not find the girly RPC from your environment files. So the first thing that you have to do is you have to actually load your environment files into your current environment. The next thing that you can do then is to run forge script, and then you give it a script, not source, script deploy, but you also have to give it the actual identifier of the contract inside this deploy script with a double point, spacebear script. And then you want to broadcast this, you want to verify it, and the RPC URL is the girly RPC URL from your environment file. Let's see if that works. And it should not work. Yes, the reason for that is inside our script, we want to get the contents of the secret, but we have to allow that specifically in our Foundry TOML. So what we do over here is we have another key here, fs permissions is an array with an object inside, which is access is read, and the path is /. And if we store this one and run this again, then it should actually hopefully work. Script ran successfully, and now it's trying to find the transaction confirmations, and it's going to store these transactions in a broadcast folder inside the folder of the script name and inside the folder of the network ID, and then in run-timestamp or run-latest, which is the latest run, and there you have everything that you would possibly need, including the contract address. And if you have several contracts that are deployed, then you find several contracts in there with the contract name. You can filter them in a JavaScript environment, for example. The other thing is it is going to directly verify the smart contract. Might sometimes take a while because Etherscan, is scanning the blocks, and sometimes it's a little bit behind. So you need to wait a little bit longer here sometimes. But overall, it should just work out of the box. Let's just verify this. Let me go to Etherscan, paste our contract, and we have the contract over here, which also means you can interact with the smart contract over here. You could now mint a token if you wanted to, or if you already know that you want to mint the tokens during the deployment, then you can do this directly in the script before the stop broadcast, because it will use the address of this private key to create or to interact with the smart contract over here. Yeah, that's it from my side. The only thing that I can suggest to you is inside the root, before Foundry, Hardhead, and Truffle, you add a readme.md. You add some details about what this repository or project is about, because I think it makes a really good showcase project in your GitHub. I can provide you with a sample readme in our course docs, and you upload it to your GitHub in order, for you to have a reference and for other people just to have a showcase project, what you did with Hardhead, Foundry, and Truffle. All right, that's it from my side. I will see you in the next lecture.
What a massive section! You have now not only built your own NFT, you also have tested it offline with unit tests in all free frameworks, and you have deployment scripts ready. This enables you now to build, pretty much any project you want. If you want an example of a project that is any project, just have a look at the smart contracts of the company I work for, the Morpher protocol. It's a complex scenario of using smart contracts outside of any standards. We even did an implementation with proxies. So if you want to have a sort of template ready how to use Foundry in combination with Truffle, you can use our repository as an example. Other than that, that's probably not much of any use to you. But do you know what's of great use to you? If you take the whole NFT project directory, place a nice looking README inside, and push it to your GitHub. Well, that's definitely eye-catching for any HR or tech who is interviewing you. Thanks so much for watching this course. In the meantime, I hope I can offer you maybe some additional materials next, either in form of mini courses or maybe other courses to take. Also, if you want to stay up to date on our course updates and so on, please don't forget either to subscribe to our newsletters or to our educational announcements, but depending on the platform where you consume this course. Well, thanks again. I hope I can welcome you in one of my other courses. In the meantime, have a nice day, and I'll see you maybe in one of the next lectures. Thank you so much for enrolling. Let me tell you, both Ravinder and I feel extremely honored to be able to be on your side throughout this journey. By taking this course, I really want you to succeed with blockchain development. I want you to know how blockchain development works at the very core and deep dive into the fundamentals and advanced topics with hands-on examples. We will spend quite some time together during this course. So why not have a quick look together? What is waiting for you inside this course? It is an Ethereum developer course, so there is no way around learning Solidity. I will walk you step by step through the whole Solidity stack until you feel confident answering the hardest questions. Obviously, you will also write plenty of decentralized applications along the way in exciting labs and challenges. By the end of the course, you will be able to evaluate and build your own decentralized applications from start to finish. You will know how to use things like Solidity, MetaMask wallets, private keys, mnemonics, public and private networks, Truffle and Truffle boxes, unit testing with Mocha and Chai, and many more nitty little gritty details that are unique to blockchain development. At the end of the course, you will also receive a certification, and you will definitely be able to add this course and the projects we are building to your CV. But what are we doing exactly? Let me tell you about everything you will learn in this course. And don't worry if there is a topic you have never heard about yet. I am sure at the end of the course it will all be crystal clear. In section 1, we are talking about the fundamentals of how blockchains operate. We will download MetaMask, use it as a wallet, get some Ether, play and tinker around, and take a look behind the scenes. I will explain exactly how things like hashing works and how blocks are linked together. In section 2, I will walk you through Solidity in a labs-based way using the Remix IDE. We are starting easy with simple variables and get gradually into the most advanced topics like libraries, structs, gas calculations, debugging, and many more topics. If you are thinking, this sounds like a boring presentation style only, then don't worry. For each lab, there are comprehensive hands-on PDF sheets to download and follow along. After knowing about Solidity, we will go through local development using Truffle. In section 3, I want to introduce Truffle to you and some advanced topics of Solidity, such as low-level functions. Then, in section 4, we talk about blockchain nodes. This includes building your own private or consortium network. You will learn how to start your own blockchain from scratch and create a Genesis JSON file. In section 5, I will do a full walkthrough of a real-world project. We are building a sort of supply chain solution that's shared among several people with access rights and front end to use. This will deepen your understanding of events and event triggers. The final project will be a tokenization of real-world assets using audited smart contracts from OpenZeppelin. We will build upon those smart contracts, deploy our own voucher solution on top of it, and write a simple front-end to interact with this. You will deepen your knowledge about accounts, deployments, and best practices for unit testing, teams, and local development. If you ever get stuck at any point, rest assured you will not be left in the dark. As a student of this course, you can always ask as many questions as necessary to successfully complete this course in the course forum. The blockchain space is an ever-evolving ecosystem. Make sure to subscribe to the educational announcements and become a member of our Facebook group. We're sending frequently news, course updates, and other relevant information via the educational announcements or our Facebook group. Now, that is definitely enough from me. Let's dive directly into the course and get started.
In this video, I want to talk about the one big benefit that blockchains actually bring in a real-world example, and this is why in this video I want to talk about what are transactions in a step-by-step way. And for this reason, I chose to use two people, and we call them Alice and Bob and the stapler. And we are passing on, or actually Alice is passing on the stapler from her side to Bob's side. Now, what happened here? The first thing is the possession changed from Alice's side to Bob's side because she gave him the stapler. But also another thing changed, which might be the ownership, because she's not only borrowing the stapler to Bob, she's actually giving the stapler to Bob. So we have two things which are in this case the same thing, is Alice and saying like, here Bob, I give you my stapler, have it, good luck with it, I have a second one, you can keep it. We could decouple those two things and track ownership in a ledger and possession obviously in the real world as an item. So in the ledger, we would track on the left side Alice, on the right side Bob. Alice has 1 stapler, Bob has 0 staplers, and then we make a new transaction, and Alice has then 0 staplers because she transacted 1 stapler from her side to Bob's side, and then Bob has 1 stapler. That is the new state of the ledger. And I mean, this is not a really good real-world example why we would want to track possession of a stapler in a ledger. But if we think about real-world examples, then we maybe talk about stocks, or we talk about real estate, where it is not so easy, to keep your apartment in the pocket all the time. This is where clearly possession and ownership has to be separated. Now, tracking any of those things, especially monetary items such as stocks or cash on a bank account, tracking those items in a ledger very well can introduce malicious actors on the ledger, which are sending another transaction from Alice's side to Bob's side, or manipulate the ledger in one way or another so that Bob suddenly has 2 staplers, 2 times the money he had first on his bank account, more items, more apartments, or more square meter in an apartment building, and so on. So we see this in the real world, and it's called a double spending problem, where another transaction is sent and it can be spent by someone. You maybe remember back Dolly the sheep, which was cloned, but we cannot really do this with real world items. You cannot just clone your apartment building. We can do it with digital items. We can just copy them, and this is where the real problem comes in. All right, what did we learn from Alice and Bob here? The one thing that we learn is when the stapler was passed on from Alice's side to Bob's side, she gave Bob the stapler, then we had possession is the same as ownership. There is a peer-to-peer transfer, there is no middleman in between, there is no bank, no broker, no nothing, only Alice and Bob. Here you have the stapler, that's it, done. The same we have with cash. If I have $100 or 100 euros or whatever cash value country you live in, and you give it to your friend, then you have a peer-to-peer transfer. That is as easy as that. But we can also track ownership in a ledger. This is where maybe you put your money on the bank, or you get shares in a company, or you buy a house. This is where ownership and possession is decoupled. And that introduces the double spending problem, because somebody, potentially a malicious actor, can come along and manipulate the ledger in one way or another, which introduces the problem of who keeps track of those records. And in the real world, we have auditors, we have controllers, we have companies who are taking care of those people who are taking care of the ledger. And then we have other companies who are auditing those companies who are auditing those people who are taking care of the ledger, and so on and so forth. So we have this huge amount of management structures where the blockchain really comes in and shines, because it introduces this one solution to this problem, which is the double spending problem, and inherently has trust in the data. All right, enough talking from my side. What are the key takeaways here? Ownership can be recorded on a ledger, doesn't have to be the same as possession, and also actually we can track other things in a ledger, more on that later. And blockchains solve the double spending problem in a very trustable and meaningful way. All right, I will see you in the next lecture. The first problem you will run into when you start developing Ethereum applications is how to onboard users. When Ethereum started, or when I started with Ethereum in 2016, there were just limited options. The ideal case at that time was you somehow replicate the blockchain on the end user's computer, because a blockchain node downloads all the blocks locally on the computer, and then you start using the Ethereum blockchain. This is very cumbersome. This takes a lot of time. You need to download all the blockchain. It's about, at that time, it was around 30 gigabytes. Now it's a lot more. I think we are close to 80 or 90 gigabytes. And that is not the way to go anymore. This is why in this video, or in this and the next video, I want to introduce MetaMask to you, which is a kind of a wallet, and also a plugin for Chrome to onboard new users. And this is kind of the first thing I want to introduce to you, starting with blockchain development, because it makes onboarding to Ethereum very, very easy. Now let's get started. I'm here on MetaMask.io. This is the website where you can actually download MetaMask. You will see this little fox. And MetaMask is a browser plugin, so you would need to download it for your browser. If you have Chrome, you get the Chrome extension. If you have a Firefox, you get the Firefox extension, Opera, and so on. I guess you get the idea. All right, I will get the Chrome extension, add to Chrome, add the extension. It will download the extension here, and then it will install the extension. And it's installed, and it will open the walkthrough. Now, let's get MetaMask set up. I just walk through this setup wizard. I'm new to MetaMask. Yes, I'm new to MetaMask. Well, you can help improve MetaMask or not. I usually agree here because they are not collecting anything. Then you set a very strong password, please. This password is here to encrypt the private keys. We're talking about private keys a little bit later. Set the password to a strong password in case somebody gets access to your computer so he cannot decrypt the private keys. The private keys give access to all the funds that you have on your account. So I will choose a strong password here. I agree to the terms of use, and we go to the backup phrase. You should reveal this and save this somewhere. I will not do this. I will remind me later because I actually want to get started using MetaMask and showing you around. So I'm here in the main window, and this is seldom that I'm here. This is a wallet. You can see I have an account and I can deposit and send funds and so on. I will skip this step here explaining to you exactly what you see here. I actually want to start using it. The second thing that you see is on the top right side is this little icon, the fox icon here, and a pop-up. So I'm very rarely inside here. I'm actually closing this because mostly I'm working with this pop-up here. All right, I would say we go and get some Ether into our account. And you can see this drop down here. You can switch to a different network. And the main network is where the ethers cost real money. But because we are developers, we actually just want to test some applications. We just want to get a feeling for the blockchain, see how it works. This is why there are test networks. And these test networks, I also want to talk about them in depth a little bit later. But suffice to say, you can get test ether on a test network. This is a separate environment, totally separated from the main network. Those are usually networks where developers can either test the applications, or actually network developers can test new consensus algorithms, can test their nodes and so on. So they are tests on different levels of the whole Ethereum development stack. We are mostly interested in getting test ether for testing applications. So for this one, I am usually on the Robston test network or on the Gurley test network. And I will show you on both networks now how you can get test ether. First start with the Robston test network. And I'm showing you both because sometimes those so-called faucets that we're going to use, sometimes they are not working. So switch to the Robston test network, deposit ether, get ether. You are redirected to faucet.metamask.io, and then you hit request 1 ether from faucet. A faucet is kind of a website that gives out free ether for you to test. And if everything works, then you see here a transaction, and you can click on it and you will get to a block explorer, and you can actually follow your transaction. As soon as it's mined, it will pop up on your MetaMask wallet that there's something. Now, unfortunately, I have to be honest with you, sometimes the MetaMask faucet isn't working, then a red arrow is popping up here, and this is why I want to show you the other one as well, the Gurley test network faucet, which is just another test network where you can get test ether and deploy your smart contracts. From the point of view from a developer, there is no difference between those two. You can deploy your smart contracts on both of them. You can onboard beta users on both of them. You can play around on both of them. And actually for the Solidity section, we are not using any of those. We are going to use it later in the course for local development and for testing transactions on a real network. Okay, I see there was something done. I see status success on the block explorer. And when I open my wallet, then actually you should see 1 Ether here. Now I switch over to the Girly test network. Again, totally different environment. And on the Girly network, which is kind of another database, I have 0 Ether. So I'm doing kind of the same again. I deposit here, test faucet, open that one. And you see the faucet from the Girly test network looks different. So I have to enter my address here. I open MetaMask. I click on the account. So I copy this to the clipboard and then I paste it over here. And then I hit another robot and I request 0.05 Girly Ether, GOETH. And after a while, there should this pop-up come and it says success. And I can also open the Block Explorer and I see there is a transaction sent off to the network, but it's not reflected yet. And when we are reloading this, then we see success and we open MetaMask and we should see our 0.05 Ether here. All right, this concludes our first lab that we were running. Don't forget, you can download this lab as a resource download, as a PDF attached to this lecture. And in the next lecture, I want to talk a little bit about the theory side of what happened in the background, because there are a lot of things happen that are maybe not so clear for a beginner. And I just want to cover them, and I'll see you in the next lecture. Now let's talk about how this transaction that we actually did in MetaMask came about, because there's quite a bit of things that are happening in the background. First, we opened MetaMask, we installed MetaMask, we opened MetaMask, and we did some kind of magic that made MetaMask interact with a blockchain. And we selected the blockchain from this dropdown. But what exactly happened there in the background, and why can MetaMask read data even though we don't have a real blockchain node installed or anything else? Now, that all isn't so much magic. There is an actual service in the background that is called Infura, where MetaMask connects to. And Infura is a blockchain as a service provider, and they internally have blockchain nodes running in the background. And as you can see here, we are installing MetaMask. MetaMask is actually interacting with Infura. They are hosting Parity and Go Ethereum nodes, as far as I know, and are opening a RESTful API in order for MetaMask to interact with the blockchain through a blockchain node that they are hosting. Now, the next thing that we did is we opened the faucet, like the MetaMask faucet here in the picture, or maybe another faucet. It doesn't really matter. You open the browser, you hit some button, and the browser, through some magic, interacted with the blockchain node, and 1 Ether or 0.05 Girly Ether appeared in our MetaMask wallet. How is that possible? What happens here in the background? There is also, it's not a rocket science, what is happening in the background. The browser is interacting with some sort of backend, and the backend is interacting with the blockchain node and sending off a transaction. The important part here is that the key, the private key, in order to sign this transaction, and we are talking about transaction signatures in one of the next lectures, the key is stored on the backend of that service that is providing this faucet. And this has access to the funds. They are sending off a transaction from their address, which is stored on the blockchain ledger, to the address that is stored in our MetaMask wallet. And now, as you can see here, the ground truth is the blockchain, where MetaMask via Infura, via a blockchain node, has access to the blockchain data, and the browser via the backend, via the blockchain node, has also access to the same blockchain data. So we have one shared ledger across those two services. Now, every time when we made a new transaction, we opened the Block Explorer. For the MetaMask Block Explorer, we were on the Robston test network. That was robston.etherscan.io. They are running a Block Explorer. And on the Girly test network, it was girly.etherscan.io. It's the same Block Explorer. Also, no rocket science there. Etherscan is interacting and hosting their own blockchain nodes and having a copy of the blockchain locally on their data center and processing this blockchain with all the transactions and showing us the result in a browser window. Now you can see here already
every time we want to interact with the blockchain, we need a blockchain node, and the blockchain is the single source of truth underlying the data having stored there. Now, you can imagine there's a lot more going on, and a lot other nodes are interacting with the blockchain node. We can actually download our own node, which is Ethereum or Hyperledger Besu or Parity. And they are all doing pretty much the same thing. They are connecting to the blockchain and starting to download the blocks locally. And in order for us to avoid this downloading for now, we are going to do it later in the course, but for now we just want to get started doing something with the blockchain. We can use services like Infura to interact with the blockchain via a hosted blockchain node. All right, what are the key takeaways here? The first thing is you need a blockchain node to interact with the blockchain. This can be a hosted node or your own node. In our case, it was a hosted node. The blockchain is the single source of truth in the whole system, where we have a shared ledger across all participants, which can get access to the same data. And there are infrastructure providers that abstract this running a blockchain away from developers, from users, and make onboarding quite easy. All right, that's it for this lecture. And in the next one, we are talking a little bit more about cryptography and transactions. Now that we have installed MetaMask, why don't we just actually send a transaction? Because so far we have received a transaction, we have received some Ether, but we didn't really send anything anywhere. So let's create our first transaction together. In MetaMask, it is quite easy to do that. I'm still on the Gurley testnet, and depending where you are, if you're on Robston or on Gurley, or maybe even on the mainnet, you can easily send transactions between two different accounts in the same wallet. Now, before we actually send the transaction, we have to create a new account because we have just one account right now. So the first thing you would have to do is you click on this round icon here. You say create new account, give it a name. I just call it account 2 for now. And we see that in our second account, there is 0 Ether. Now I am going back to my first account. Again, this little round icon here, select the first account, hit send, transfer between my accounts, and I want to transfer to the second account I have here. I could also transfer to any other address or anywhere on the network within obviously the Gurley test network. But for now, I really just want to transfer it to my second account, which has this address here. We're going to talk about addresses in, I think it's the next or after the next lecture. So just stick with me for a while. I'm hitting the max amount here. So I'm transferring everything, and you can see that it's not transferring 0.05 Ether. It has to deduct a little bit as a transaction fee. It's also called a gas fee on Ethereum. And then I hit next and I hit confirm. Now you see the transaction is pending, and I can actually open again Etherscan, because Etherscan, even though it's a totally separate service, they have access to the same blockchain, the same underlying data. They see the transaction was sent to the network, and they can track and trace the transaction until it is mined. And then when it's mined, it's obviously baked in a block, and it is persistent forever on the blockchain. Etherscan is automatically reloading as soon as the transaction status changes. So it's now success. I see in which block it is. I see when was the transaction mined. I see from which address it came, to which address it was sent. I see the value, and I see the transaction fee, the gas fee, and I can add this to up. It will add up perfectly to the 0.05 Ether that we had in our wallet. We see more. I'm going to talk about this in one of the next lectures in more of a theory style presentation. More importantly, we see that in our account number 1, which we have selected, there is 0 Ether now. And in our account number 2, we have 0.0499, actually 0.049874 Ether. This concludes this lab. Again, you will find this lab as a resource download attached to this lecture, and I will see you in the next one.
Now that we have sent our first transaction, I want to talk a little bit about in depth how Ethereum transactions work and how the Ethereum blockchain makes sure that a transaction is authentic. And this is why in this lecture, I want to take a step-by-step example of the transaction that we sent and then tell you what is happening in the background so that the blockchain ensures the authenticity of a transaction. Now let me start with a screenshot. This is MetaMask, how it looks right now for me. We see that there is a transaction happening. There is a from and a to. So we see from which address it was sent, to which address it was sent, and we also see the amount, and we see a couple of more parameters. If we look at any library which can be used to programmatically send transaction on the network, for example, the Web3.js library, which we are going to work later, or Eth.js, or any other library, you see that it takes a transaction object. And this transaction object has a couple of parameters that you can set. Some are optional, some are not optional. Let's have a look at a classical transaction object from the transaction that we sent. We mainly set three things in our transaction object. This is the from, the account where we send the transaction from. There is the to, the account where we send the ether to. And there is a value that is an integer value in way. How many ether did we send? So in our case, we sent 0.0477 ether, I believe. And in way, you have 1 ether is 10 to the power of 18 way. So the smallest unit on the Ethereum blockchain is actually very small. And we are going to talk about this in another lecture. In addition to that, we had some sort of transaction fee, which is regulated through the gas and the gas price. Also talking about this in another lecture. And then we had a data field, which was not set, which is used for smart contracts when they are deployed to the blockchain. And the nonce field, which we are also talking about later. But just to give you a brief idea, the nonce is an integer that gets incremented every time a transaction is sent in order to avoid replay attacks. Now, these three fields are the fields that you usually have when you send a transaction. And when you look at the classical block explorer, then you again see these three fields here, from, to, and the value field, which are quite important to make sure that the transaction is authentic. But okay, I mean, now we know that the transaction somehow is, sent off to the network and there's a value and so on. But how does the blockchain know that it is not a malicious actor? Why can't I send the transaction in your name? In other words, how does the blockchain know that it is really allowed to send funds from your account to my account, from your account to another account, from my account to your account, and so on? Why does this work? And the answer is quite simple. The answer is we are using signatures for this. And signatures have a couple of interesting properties. But before we talk about the signature, let me walk you through step by step how these are built up. Let's follow along why we want to have a transaction signature. In any language, in any library that you are going to use, you have some sort of a function that says sign transaction. In Web3.js, that is web3.eth.sign transaction, same in Eth.js, in other programming languages, I don't know, but the point is you usually have a function that signs a transaction and that takes an account which needs to be unlocked. Remember that the account needs to be unlocked. So there must be access to a private key, and then it can create a transaction signature. How does a transaction signature look like? Now, first we had this from, the to, and the value field, no data and gas and so on. And when we run this sign transaction function with the transaction object, then we get an output. And that is more than we had before. This is a V, a R, and a S. And it's very important to understand those three things that we get in addition, because with these three parameters, we can authenticate that a transaction is not from a malicious actor. Let me walk you through this step by step how this works. First, we have the classical transaction object. And I'm taking here the actual transaction object that was sent from MetaMask. We have the from field was my account 1. We have the to field, which was my account 2. And we have the value, and then we have a nonce and the gas price. And then we have this transaction, and in addition, MetaMask stores a private key. So MetaMask as a wallet, like every wallet, has private keys in the background. You will usually not see them, and you will usually not access them. A private key is 32 bytes long and is a randomized, hex, 64 hex character string. So you have 32 random bytes that are stored somewhere. You can actually create those private keys yourself in a notepad if you want. The point is, it should be as random as possible. So you might want to use a computer for that who has a safe randomizer. Okay, so you have the private key, and this is generated by the user. So every private key is hopefully different. Then the private key is sent through a function which is called elliptic curve digital signature algorithm. And this ECDSA function gives you a public key. And the public key has a couple of properties. One of the most important property is you can create the public key from a private key, but you cannot go back. If you have a public key, without trying all combinations, you cannot find the private key. So you would have to brute force it. And because it is fairly long and there are a lot of options, this makes the blockchain so secure. So you have the public key, which is known in the public, but you cannot go back to the private key. But you don't know yet why this is so important. So let me walk you a little bit further. Now, we take this public key and we create an Ethereum account. The Ethereum account is the KZAG hash of the public key and then the last 20 bytes of that. So when you take a public key and you create a KZAG hash, you take the last 40 hex characters or the last 20 bytes. This would be the Ethereum account. This would be the from field that you would see in the transaction. So we have the private key, we have the public key, and we have the account. So you can go from private to public to account, but you cannot go from account to public to private. And while it wouldn't it wouldn't be so bad to go from Ethereum account to public key, the important part is you cannot go from public key to private key. This is where it gets important. Now, back to the signature. Now we have the transaction, and the transaction gets signed with the private key. And the signature would be, the signed transaction would have additional fields. This would be these VRS fields, where the signature is the R and the S. But from here, we don't know yet why is the Ethereum transaction authentic. The important thing is, with the R and the S, you can run it through a so-called EC recover function, and it will output you again the public key and the Ethereum account. So with the signature, and this is what makes sure that the Ethereum transaction is authentic. With the signature, you can recreate the public key. You can't recreate the private key, but you can recreate the public key and therefore recreate the account and make sure that the account that was used in the from field of the transaction is the same account that has the underlying private key that was used to sign the transaction, create the transaction signature. And this is why the blockchain and every participating node can very easily verify the transaction is correct. Now again, from the transaction signature, you cannot go back to the private key. From the public key, you cannot go back to the private key. So the private key remains the one single source of truth for you, which you possess in order to sign transactions and in order to create an Ethereum account. In other words, the private key has to be kept safe under all circumstances. It is the one thing that can make transactions from your account, which is the reason why when you lose your private key, when somebody hacks your computer and your private key is not encrypted with a password, it can be used to transfer funds from your account to any other account. From the private key, you can go to the public key, from the public key to the Ethereum account, but you cannot go back. Go to the takeaways. It was quite a lot. So let me tell you the few things that you should take away from this lecture. The transaction signature is the one thing that ensures the authenticity of a transaction. So without a private key, you cannot introduce malicious transactions on the blockchain. The private key is the one single source of truth. So signatures are generated from a private key, public keys and addresses are generated from a private key, and the private key is the thing that you have to keep safe. This is also why when you use MetaMask, you should use a strong password in order, let's say you lose your laptop and somebody gets access to your laptop, that he cannot use MetaMask and your private keys from MetaMask in order to send transactions. And that's it, what I wanted to talk about. I hope I didn't lose you here. It will get hands-on very soon. Just stay on a little bit longer and bear with me. Before we continue to the next lecture where we are going hands-on into Solidity, let me talk a little bit about cryptographic hashing and give you a quick intro, because it's important to understand how the blocks are actually interconnected and why this is so secure. So this is a cryptographic hashing quick intro into why hashing is so important for a blockchain. So what is a typical hash function? A hash function is a function that takes an input and outputs you a digest. And for example, if we have a hash function and you input hello Rome, then you would get this kind of hash or digest, 3, 9, 8, and so on. And if we have a hash function and an input hello Rome exclamation mark, then you will get a different, totally entirely different output, a so-called digest. Now, if we are taking this picture, I think it's from the Wikipedia, then you see that you have an input and we have a hash function and a so-called digest, and we input fox, we get this kind of digest. We input the red fox jumps over the blue dog, then we get this kind of digest. And if we just change one character, one little thing in the input, we get a massively different output or digest of the hash function. That is very important to understand. So in general, the ideal cryptographic hash function has 5 main properties, and these are quite important. The number one is it is deterministic. That means if you have the same input, it will always deliver the same digest or the same output. If you have fox today, then it will deliver you the same output today, tomorrow, or after tomorrow. It doesn't matter. You will always get the same output. It is very quick to compute this output. So you can have a very long hash or a variable hash, and it doesn't take much time to compute the digest. It is not possible to go from the digest back to the input. And I think this is one of the most important things, where you get some sort of output, but you cannot come back without brute forcing it. The fourth one is a very small change in the input makes a massive change in the output. So the hash value appear totally uncorrelated. They are uncorrelated, and the whole output changes, not just a small bit, even though you change just a small little thing on the input value. And the last thing is it should not collide. There shouldn't be any collisions in the hash value. That means there should, for any given input, it should always produce a different hash output. Okay, let me tell you a little bit about hashing of hashes, and then you see where we go to with the blockchains. And let me make a coloring schema for this. Let's say we have a hash function, hash, which outputs colors. And we input ABC in the one hash function, this outputs blue. And we input CDE in the other hash function, this outputs this yellowish ochre color. And then the question is, what is the overlay of these two? That would be, let's say, some sort of green color. Great. And then we take this green and we add another hash, let's say 1, 2, 3, and we overlay these. So the question would be, what would be the output color of those? That would be some sort of, darker yellow. Now the question is, what if we change one of those hash values on the top? Instead of CDE, we input CDF, and suddenly the yellowish changed to a kind of purple color. But then also all the other colors down there would change. So that is very important to understand. How does this work on a blockchain? Well, on a blockchain, you would have some sort of a block and you would hash all the information of the block, and you would take all the transactions that are happening between this block and the next block, and you would add in all those and hash them again. So you would get a new hash. You would know from this block what was the previous hash. It was blue. You would know from this block what was the hash of all of this information actually. And then you would add in this information here. So what about the next block? The next block, you would have maybe transactions again, and you would generate a new block. And this new block has a hashed information of this block, but this block already has a hashed information of that block. So you cannot change this block anymore, because you would change the hash of this block, or the stored hash of this block. And when you change this stored hash of this block, you would have to change this block as well. But this block is already baked into the blockchain. Now, and so on and so forth, you see that this continues endlessly in a blockchain. So they are all linked together through these hashes. And not just on one centralized computer. There's a copy of the same information on every participating node in the network. And if you want to change something, then you would have to change it, well, on all participating nodes in the blockchain. And this is why it is so secure. You cannot just break into one system. You would have to break into all of those systems and change all of those blocks in all of those systems on all of the copies of the blockchain. So here are the key takeaways. Number one, the hashing algorithm is the mathematical foundation of the blockchain. Without hashing, there is no blockchain. So there must be a strong hashing algorithm that follows these 5 patterns, or these 5 properties. A block always has the hash of a previous block. So they are kind of chained together in a way that you cannot change the previous block without changing the current block, and you cannot change the current block without changing the next block, and so on and so forth. And if you change the information of one of the previous blocks, well, it will change all the blocks after that. So this is all I wanted to talk about. I hope you gained a lot of value out of this lecture. This is the very foundation of a blockchain, and I'll see you in the next lecture.